Right now, somewhere in the darkness between stars, invisible predators drift through our galaxy. They have no light, no sound, no warning of their approach. And if one passed close enough to our solar system, we wouldn't see it coming until it was far too late. These are rogue black holes. Stellar corpses torn from their birthplaces, now wandering the Milky Way in complete silence. Scientists estimate there could be hundreds of millions of them out there, and we've barely detected a handful. The rest remain hidden, moving through space like cosmic ghosts, bending light around themselves, swallowing anything that crosses their path. What makes them truly terrifying isn't just their power. It's that we have almost no way to track them until they're already here. And when astronomers finally developed methods to spot these wanderers, what they found was deeply unsettling. Black holes form when massive stars collapse. We've known this for decades. A star 20 times the mass of our sun burns through its fuel, its core implodes, and gravity crushes everything into a point of infinite density. What's left behind is an object so dense that not even light can escape its pull. Most of these black holes stay where they formed, anchored in place by the remnants of their stellar neighborhood. But not all of them. When a massive star explodes as a supernova, the blast isn't always symmetrical. If the explosion throws more material in one direction than another, the newborn black hole gets kicked hard. Astronomers call these natal kicks, and they can launch a black hole across the galaxy at speeds exceeding 600 kilometers per second. That's more than 2 million kilometers per hour. Fast enough to escape the gravitational grip of its birthplace entirely. Once free, these objects become nomads. They don't orbit anything. They don't belong to any star system. They simply drift through the galaxy, following trajectories set by that violent birth moment, invisible and utterly indifferent to whatever lies in their path. Here's where it gets worse. Our galaxy has been forming stars for over 13 billion years. Millions of massive stars have lived and died in that time. Each one that met the right conditions created a black hole. And a significant fraction of those black holes received kicks strong enough to send them wandering. Do the math, and you arrive at a disturbing conclusion. The Milky Way should be filled with these things. Early estimates suggested tens of millions. More recent models push that number higher, potentially into the hundreds of millions. Picture that for a moment. Between 100 million and 400 million rogue black holes, drifting silently through the same space we occupy. Most are stellar mass black holes, between 5 and 50 times the mass of our Sun. Small by cosmic standards, but devastating by any measure that matters to us. And we can't see them. A black hole by definition emits no light. It's a hole in space where light goes to die. The only way we typically detect black holes is by watching how they affect their surroundings. If a black hole is pulling gas from a companion star, that gas heats up as it spirals inward, glowing brilliantly in X-rays before it vanishes beyond the event horizon. Binary systems like this are relatively easy to spot. We've cataloged dozens of them. But a rogue black hole traveling alone through empty space has nothing to feed on. No companion star. No accretion disk. No telltale X-ray signature. It's just a gravitational knot in the fabric of spacetime, moving silently through the void. For decades, astronomers assumed these objects were essentially undetectable. They were out there, sure, but finding them seemed impossible. Then someone realized we'd been thinking about the problem wrong. Even invisible objects reveal themselves through gravity. Einstein showed us this more than a century ago. Mass warps spacetime, and light follows those curves. When light from a distant star passes near a massive object, the object's gravity bends that light like a lens. If the alignment is precise enough, the background star appears to brighten temporarily as its light is magnified and focused toward us. Astronomers call this gravitational microlensing. The technique had been used successfully to find planets, distant stars, even other black holes in binary systems. But using it to hunt lone rogue black holes required a different approach entirely. You'd need to monitor millions of stars continuously, waiting for one to brighten in exactly the right way. The chances of catching such an event are microscopically small. The alignment has to be perfect, the timing has to be right, and you have to be watching that exact star at that exact moment. In 2011, a team of astronomers decided to try anyway. They pointed their telescopes toward the galactic bulge, the dense central region of the Milky Way where stars are packed close together. More stars mean more opportunities for alignment. They monitored the brightness of millions of stars simultaneously, searching for the characteristic signature of a black hole passing in front of them. For years, they found nothing conclusive. Hundreds of microlensing events, yes, but most could be explained by normal stars or brown dwarfs. Then in 2022, they announced something different. An event designated MOA-2011-BLG-191. The light curve was perfect. A star had brightened over several weeks, peaked, then faded back to normal. But the duration and shape of that brightening suggested something unusual. The lensing object wasn't a star. It was too massive and too dark. After ruling out other possibilities, the team concluded they detected a rogue black hole. Somewhere between 2 and 7 solar masses, drifting alone through the galaxy approximately 5,000 light-years from Earth. It had passed directly between us and a background star, briefly magnifying that star's light before continuing on its silent journey. This was the first time anyone had definitively detected an isolated black hole wandering through space. Not orbiting anything. Not feeding on anything. Just moving. And it raised an immediate question. If we found one, how many more are out there that we haven't found? The galaxy is enormous. 300 billion stars spread across 100,000 light-years. Even hundreds of millions of rogue black holes would be sparse in that volume. The chances of one passing close to any particular star are vanishingly small. But close is a relative term in space. A black hole doesn't need to hit something directly to affect it. Gravity works at a distance. If a rogue black hole passed within a few light-years of our solar system, we'd likely never notice. It would tug slightly on the orbits of distant comets in the Oort cloud, maybe nudge a few toward the inner solar system, but nothing catastrophic. Pass within 1 light-year, and the effects become more pronounced. Orbits destabilize. Long-period comets get redirected. The delicate gravitational balance that keeps our solar system stable starts to shift. Get closer than that, and things deteriorate rapidly. A black hole passing within the orbit of Neptune would gravitationally scatter the outer planets. Jupiter's orbit would shift. Saturn's rings might destabilize. The asteroid belt could be stirred into chaos, sending rocks careening through the inner solar system. Earth's orbit would change. Not immediately, not catastrophically in human terms, but enough to alter our climate over centuries. Enough to make our world unrecognizable. And if one passed within the orbit of Mars, we'd have months at best. Maybe weeks. The sun itself would be affected, its outer layers potentially stripped away as the black hole's gravity pulled at stellar material. Earth's orbit would become wildly elliptical or be ejected from the solar system entirely, flung into interstellar space to freeze in the darkness. The worst part isn't the destruction itself. It's the warning time. Or rather, the complete lack of it. Current detection methods only work when a rogue black hole passes directly in front of a background star from our perspective. By the time we detect that microlensing event, we're observing something that happened years or centuries ago, depending on the distance. The light we're seeing left that region of space long before we started watching. The black hole itself is already somewhere else entirely, continuing its journey along a path we can't predict. We have no early warning system. No way to scan ahead and spot an approaching threat. Gravitational wave detectors like LIGO can detect black hole mergers halfway across the universe, but a single black hole drifting through space produces no gravitational waves. It's silent on every wavelength we can measure, visible only through the brief distortion it causes when perfectly aligned with a distant light source. Astronomers are working on better detection methods. Upcoming surveys will monitor more stars more continuously, increasing the chances of catching microlensing events. The Vera Rubin Observatory, scheduled to begin operations soon, will photograph the entire visible sky every few nights, watching for anything that changes. That includes the subtle brightening caused by gravitational lensing. But even with better surveys, we're still looking at a reactive system. We find these objects after they've already passed, not before. And the galaxy is simply too large, too dark, too filled with empty space to monitor comprehensively. The number of rogue black holes out there almost certainly exceeds our ability to track them all. Which brings us to an uncomfortable probability calculation. With hundreds of millions of these objects wandering the Milky Way, and 13 billion years of galactic history behind us, what are the chances one has already passed close to our solar system? Or that one will in the future? The distances involved are staggering enough that the risk to any individual star system remains low over human timescales. But over millions of years, over billions, the odds shift considerably. And we're not just talking about direct hits. Even a distant passage could destabilize the Oort cloud, sending comets plunging toward the inner planets. Some researchers have suggested that periodic comet bombardments in Earth's history might be explained by exactly this mechanism. A rogue black hole passing through the outer solar system every few tens of millions of years, stirring up frozen debris and sending it inward. It's speculative, but it fits certain patterns in the geological record. And it suggests these invisible wanderers have been influencing our corner of space far longer than we've been here to notice. The galaxy's structure offers little comfort when you consider the mechanics. Rogue black holes don't travel in neat, predictable orbits like planets around a star. They follow paths determined by countless gravitational interactions over billions of years. A close encounter with another star system deflects the trajectory. Passage through a dense molecular cloud changes the velocity. The cumulative effect of these interactions creates something closer to a random walk than an orbital pattern. Which means prediction becomes functionally impossible beyond a certain distance. What makes this particularly unsettling is scale. We think of black holes as massive objects, and compared to everyday experience, they are. But in galactic terms, a stellar mass black hole is microscopic. The event horizon of a 10 solar mass black hole measures roughly 60 kilometers across. That's smaller than many cities. Now imagine trying to spot something that size, something that emits no light, against the backdrop of a galaxy 100,000 light-years in diameter. You're looking for a dark marble in an ocean at night. From another continent. The only reason we've detected any at all is because space isn't completely empty. Gas and dust exist between stars, thin beyond anything we'd call a vacuum on Earth, but present nonetheless. When a black hole moves through this tenuous material, it pulls some of it inward. That gas heats up through friction and compression, reaching temperatures where it emits X-rays. Not much. Not the brilliant accretion disks we see around supermassive black holes in galactic centers. Just a faint glow, barely detectable even with our most sensitive instruments. But here's the problem with using that detection method. It only works if the black hole happens to be passing through a region with enough gas to produce a visible signature. Most of interstellar space is far emptier than that. A black hole could pass within a light year of Earth, close enough to potentially affect the orbits of outer solar system objects, and we'd see nothing. No X-rays. No visible light. No radio emissions. Just gravitational effects we wouldn't notice until something started behaving strangely. The math on close approaches is genuinely disturbing. Researchers have calculated that a black hole passing within 50 astronomical units of the Sun, roughly the distance to the Kuiper Belt, would disrupt the orbits of trans-Neptunian objects significantly. Within 20 astronomical units, orbital perturbations would extend to the giant planets. Closer than 10, and Earth's orbit itself becomes unstable over timescales ranging from centuries to millennia, depending on the exact trajectory and mass involved. These aren't extinction-level events in the immediate sense. The black hole doesn't need to hit us to cause catastrophic problems. Orbital changes of even a few percent would alter Earth's climate dramatically. Seasons would shift. The length of the year would change. If the orbit became more elliptical, we'd experience temperature swings between perihelion and aphelion far more extreme than current seasonal variations. Glaciation cycles would accelerate or halt entirely. Ocean currents would reorganize. Weather patterns would transform beyond recognition. Life on Earth has survived worse. Mass extinctions punctuate the fossil record, some far more severe than what an orbital disruption might cause. But those events unfolded over thousands or millions of years. Ecosystems had time to migrate, adapt, or collapse gradually. A black hole passage could destabilize things within decades. Too fast for agricultural systems to adjust. Too fast for species to migrate to new climate zones. Too fast for human civilization to reorganize around new realities. The truly nightmarish scenarios involve closer approaches. If a rogue black hole entered the inner solar system, say within Mars's orbit, the effects would be immediate and overwhelming. Earth's orbit wouldn't just shift slightly. It would change fundamentally. We might be ejected from the solar system entirely, flung into interstellar space along a trajectory determined by the exact angle and speed of the encounter. Or we might fall inward, spiraling toward the Sun over a timescale of centuries. Either way, Earth as a habitable planet would end. Ejection means freezing. Without the Sun's heat, surface temperatures would plummet to near absolute zero within years. The atmosphere would condense and freeze, falling as snow that would eventually cover the entire surface in a layer hundreds of meters thick. Oceans would freeze solid to their beds. Any life that survived would exist in deep subsurface environments, perhaps around geothermal vents, living off Earth's internal heat rather than solar energy. Human survival would require either impossible engineering or simply wouldn't happen. Falling inward carries its own horror. The journey toward the Sun would take time, but the end result is incineration. Earth's orbit decaying, bringing us closer to a heat source that already makes the equator brutal during summer. Temperatures would rise steadily. Oceans would boil away. The atmosphere would be stripped by solar wind. Eventually, the planet would be torn apart by tidal forces before ever reaching the solar surface, debris scattered across the inner solar system like a planetary corpse. The galaxy doesn't care about any of this. These events occur with statistical regularity across billions of star systems. Most stars will experience close encounters with rogue objects over their lifetimes. Some will be disrupted. Some will capture new planets or have existing ones stripped away. It's part of the normal evolution of galactic structure. We just happen to be conscious observers existing during a period when our particular star system hasn't experienced such an event recently. Recently, in this context, means within the last few 100 million years. The geological record shows no evidence of sudden orbital disruptions on that timescale. Earth's climate has varied, sometimes dramatically, but always within ranges consistent with predictable astronomical cycles. The Milankovitch cycles that drive ice ages operate over tens of thousands of years and result from subtle variations in Earth's orbital eccentricity and axial tilt. Not the kind of violent perturbations a black hole passage would cause. But absence of evidence isn't evidence of absence over longer timescales. Go back far enough, and the record becomes unclear. The early solar system was chaotic. Planets migrated. Giant impacts occurred. The late heavy bombardment around 4 billion years ago reshaped the inner solar system. Could some of that chaos have been influenced by a passing rogue black hole? Possibly. We have no way to determine that from current evidence. The gravitational signatures would have been erased long ago by subsequent evolution. What we can determine is frequency based on what we observe elsewhere. Studies of stellar velocities in our galactic neighborhood show occasional stars moving at speeds inconsistent with normal orbital patterns. Hypervelocity stars, traveling fast enough to escape the galaxy entirely. Some of these gained their speed through close encounters with the supermassive black hole at the galactic center. Others might have been accelerated by interactions with rogue black holes in the disk. The distribution of these fast-moving stars gives us clues about how often such encounters occur. The numbers suggest a close approach between a rogue black hole and a random star system happens perhaps once every few 100 million years within any given volume of space. That sounds reassuring until you remember we're talking about an entire galaxy containing hundreds of billions of stars. Multiply that out, and you get thousands of these encounters happening somewhere in the Milky Way right now. This moment. As you process these words, a black hole is likely disrupting a solar system dozens or hundreds of light years away. We'll never see it. Never detect it. Never know which star just had its planetary system torn apart. The speed at which these objects move creates additional problems for detection. Stellar velocities in our region of the galaxy average around 200 kilometers per second relative to the local standard of rest. A rogue black hole might be moving faster or slower, depending on its history, but it's in that general range. At those speeds, an object crosses 1 astronomical unit, the distance from Earth to the Sun, in about 2 months. It could traverse the entire solar system in less than a year. Detection, analysis, and response would need to happen within that window. Except we can't detect them reliably in the first place. And even if we could, what response exists? You can't deflect a black hole. You can't destroy it. You can't negotiate with fundamental physics. The only option would be evacuation, and evacuating Earth's population to somewhere safer runs into the obvious problem that there is nowhere safer within reach. Generation ships heading to other star systems would take thousands of years to reach destinations that might themselves be threatened by rogue black holes. Underground bunkers might preserve some fraction of humanity through orbital disruption, depending on severity, but only if Earth remains in a relatively stable orbit around the Sun. Ejection into interstellar space makes that impossible. The planet becomes uninhabitable too quickly for any bunker to matter. This is the situation we exist within. A galaxy filled with invisible threats following unpredictable paths at velocities that leave no time for meaningful response. The odds of a direct impact remain low over human timescales. Low enough that it doesn't make sense to lose sleep over it specifically. But the odds of an encounter somewhere in our cosmic neighborhood, close enough to affect our understanding of how stable planetary systems really are, sit much higher. The question becomes what kind of encounter would actually matter to us. Not just theoretically, but in ways we could measure or experience within human lifetimes. Start with gravitational influence at a distance. A stellar mass black hole passing within a few light years of the solar system wouldn't cause immediate catastrophe, but it would perturb the Oort cloud. That's the spherical shell of icy bodies extending roughly halfway to the nearest star, loosely bound to the Sun's gravity. Disturb that region, and you send comets falling inward toward the inner solar system. Not immediately. The journey takes thousands to millions of years depending on initial position and velocity. But once started, the process continues regardless of whether the black hole remains nearby. Historical impact records on Earth and the Moon show periodic increases in cratering rates. Some researchers have proposed these patterns correlate with the solar system's oscillation through the galactic plane, where stellar density runs higher. More stars means more gravitational perturbations. More perturbations means more comets get nudged loose. The mechanism makes sense even if the specific correlations remain debated. A rogue black hole passing through the Oort cloud would produce similar effects, just concentrated in time rather than spread across millions of years of gradual oscillation. The increased impact rate wouldn't sterilize Earth. Life has survived multiple impact events far worse than anything a perturbed Oort cloud could produce. But it would stress ecosystems, potentially triggering extinctions among larger organisms less able to shelter or adapt quickly. Human civilization, dependent on stable agriculture and infrastructure, would face serious challenges. Not extinction level, but enough to reshape societies and potentially set back technological development by centuries. That scenario assumes the black hole stays several light years away. Move it closer and effects intensify. At 1 light year out, roughly a quarter of the distance to Proxima Centauri, gravitational effects become more direct. The outer planets would experience measurable orbital perturbations. Nothing dramatic over human timescales, but enough to show up in precision tracking data. Jupiter's orbit might shift by fractions of a percent. Saturn's rings could develop new gaps or resonances as orbital periods change slightly. These aren't catastrophic alterations, but they'd be detectable, and they'd tell us something massive had passed nearby. The inner solar system would feel weaker effects at that distance. Earth's orbit wouldn't change noticeably within a single human lifetime. But over centuries, small perturbations accumulate. Climate patterns depend partly on Earth's orbital eccentricity and axial tilt. Alter those parameters even slightly and you change how solar energy distributes across the planet's surface. Ice ages have been triggered by orbital variations smaller than what a passing black hole at 1 light year might induce. Now bring it closer still. Half a light year. A tenth. At these ranges, we're talking about an object whose gravitational influence begins competing with the Sun's hold on the outer planets. Neptune and Uranus could experience significant orbital changes within decades. Their moons might be stripped away entirely, sent tumbling into new orbits around the Sun or ejected into interstellar space. The inner solar system would still remain relatively protected by distance and the sun's stronger local gravity, but relatively does heavy lifting in that sentence. At a tenth of a light year, maybe 3 months of travel time at typical stellar velocities, detection becomes theoretically possible through gravitational lensing. The black hole's gravity would bend light from background stars, creating a characteristic pattern of brightening and positional shifts as it moves across the sky. Dedicated surveys searching for such events could potentially spot it, given enough luck and the right observational geometry. But that requires the black hole to pass almost directly between us and cataloged background stars, and it requires astronomers to be looking at the right patch of sky at the right time with equipment sensitive enough to catch subtle lensing signatures. The odds aren't favorable. Even if detected, the warning time measured in months doesn't allow for much beyond observation and calculation. We'd watch it approach, model its trajectory, estimate its mass based on lensing strength, and project what effects it might have on planetary orbits. Then we'd wait to see if the models were right. If the black hole passes within the outer solar system itself, within Neptune's orbit, we've moved from theoretical concern to immediate crisis. At those ranges, orbital mechanics become chaotic in the technical sense. Small changes in initial conditions produce wildly different outcomes. Whether Earth remains in a stable orbit or gets perturbed into a more elliptical path, whether the perturbation is mild or severe, whether we end up closer to the Sun or farther away, all of this becomes sensitive to precise details of the black hole's mass, velocity, and trajectory. Run the simulation 1,000 times with slightly different starting parameters and you get 1,000 different results. Some show minimal impact. Others show Earth's orbit elongating enough to create extreme seasonal temperature swings. A few show ejection from the solar system entirely. The disturbing part isn't that ejection scenarios exist. It's that we couldn't predict which outcome would occur until the black hole was already here, moving through the system, its gravity actively reshaping orbital paths in real time. By then it's far too late for any response beyond documentation. Consider what ejection actually means. Earth doesn't crash into the black hole. It doesn't get torn apart by tidal forces unless the approach is extraordinarily close, within a few million kilometers. What happens instead is the planet gets gravitationally kicked, like a billiard ball struck at an angle. The velocity change might be only a few kilometers per second, but that's enough. Earth's orbital velocity around the Sun sits at about 30 kilometers per second. Add or subtract even a small fraction of that and you change whether the orbit remains bound to the Sun. Once unbound, Earth drifts into interstellar space. The Sun shrinks to just another bright star in the sky, eventually indistinguishable from the others except by position. Surface temperatures drop rapidly as solar heating cuts off. Oceans freeze within years. The atmosphere begins condensing as temperatures fall below the freezing points of various gases. Carbon dioxide snow falls first, then nitrogen, then oxygen. Eventually you're left with a ball of ice coated in frozen air, drifting through the void at several dozen kilometers per second relative to the galactic frame. Deep underground, residual heat from radioactive decay in Earth's core continues for billions of years. Hypothetically, life could persist in deep crustal environments or around hydrothermal vents on the ocean floor, sealed beneath kilometers of ice. These ecosystems already exist in darkness, independent of photosynthesis, powered by chemical energy from the planet's interior. They might not even notice the Sun's absence, at least not immediately. Surface life ends completely. Everything dependent on solar energy, which means everything humans need to survive, ceases functioning within months. No agriculture. No renewable energy. No ecosystem services. Survival would require moving underground with nuclear or geothermal power, growing food under artificial light, and maintaining sealed habitats indefinitely. The technical challenges are immense but theoretically solvable. What's not solvable is doing this for billions of people with no preparation time. Even if a fraction of humanity survived in deep bunkers or sealed cities, you've essentially ended human civilization as we understand it. The survivors would live in permanent artificial environments, cut off from any natural world, maintaining themselves through technology that must never fail because there's no outside to escape to. This is assuming the ejection is gentle enough to leave Earth intact as a physical body. A closer approach could generate tidal forces strong enough to cause massive earthquakes, trigger volcanic eruptions, or in extreme cases, literally crack the planet's crust. The threshold for tidal disruption depends on how close the black hole passes and how fast. A stellar mass black hole would need to come within a few 100,000 kilometers to tear Earth apart through tidal forces alone. That's close, closer than the Moon's orbit. It's unlikely but not impossible. What's more likely, if a rogue black hole passes through the inner solar system at all, is significant orbital disruption without physical destruction. Earth survives as a planet but ends up somewhere it wasn't before, in an orbit that no longer supports the climate patterns civilization developed around. Maybe the new orbit is more elliptical, creating extreme seasonal variations. Maybe it's slightly closer to the sun, triggering runaway greenhouse effects. Maybe it's farther out, pushing the planet toward permanent glaciation. Each scenario creates different challenges, some potentially manageable with advanced technology, others not. The fundamental problem remains unchanged. We can't predict these events with useful lead time. We can't prevent them. We can barely detect the objects responsible. And the consequences range from inconvenient to civilization ending depending on variables we can't control. So we exist in a galaxy where these objects drift through the dark, occasionally reshaping solar systems they pass near, and we have no systematic way of knowing where they are or where they're going. The best we can do is understand the physics, recognize the risk exists, and accept that some threats operate on scales beyond human ability to address. That acceptance doesn't mean ignoring the problem. It means acknowledging what we can and can't control, and focusing effort on the things that actually matter within our capability to influence. This brings us to something slightly more optimistic but equally strange. What happens if we reverse the scenario? Instead of losing the sun, what if Earth captured a second one? Binary star systems are common in the galaxy. Roughly half of all stellar systems contain two or more stars orbiting each other. If our solar system encountered a wandering star under precisely the right conditions, gravitational interactions could theoretically bind it into a stable configuration. The newcomer would need exactly the right mass, velocity, and trajectory. Too fast, and it simply passes through. Too slow or too close, and orbital chaos follows. Let's assume the best case. A star roughly half the Sun's mass approaches from a perpendicular angle to the solar system's plane, moving at just the right speed to be captured into a wide elliptical orbit. The two stars settle into a configuration where they orbit their common center of mass every few thousand years, staying far enough apart that planetary orbits remain mostly stable. Even in this ideal scenario, everything changes. First, there's no longer a single point in the sky that defines day and night, seasons, or climate stability. Depending on orbital positions, Earth might receive varying amounts of total radiation throughout the year. When both stars align on the same side, the planet gets hotter. When they oppose each other, one might be visible during what used to be night, eliminating true darkness for months at a time. Ecosystems evolved under predictable light cycles would face immediate stress. Plants time their growth, flowering, and dormancy to seasonal patterns that have remained consistent for millions of years. Disrupting that rhythm doesn't just inconvenience agriculture. It destabilizes the foundation of terrestrial food webs. Animals navigate, hunt, and reproduce based on day length and seasonal cues. Migratory birds use the sun's position for orientation. Nocturnal species depend on darkness. Coral reefs synchronize spawning to lunar cycles and water temperature patterns tied to solar radiation. All of these systems assume one sun following a predictable path. The climate effects cascade through every layer of atmosphere and ocean. Earth's climate system relies on differential heating between equator and poles to drive atmospheric circulation and ocean currents. Those patterns exist because solar radiation arrives at different angles across latitudes and varies predictably through the year. Adding a second star, even one much dimmer than the sun, introduces new heating patterns that don't align with the geography. Jet streams might shift latitude or weaken entirely. Ocean currents that distribute heat globally could alter course or speed. The intertropical convergence zone, which drives tropical weather patterns, might oscillate unpredictably or split into multiple bands. Then there's orbital mechanics. Even if Earth's orbit remains stable initially, long-term gravitational perturbations from the second star would accumulate. Over thousands of years, Earth's orbital eccentricity might increase, creating more extreme seasonal variations. The axial tilt that currently gives us moderate seasons could begin precessing faster or shifting to new angles. Other planets face worse outcomes. Mars, already in a precarious position with thin atmosphere and marginal temperatures, could be pushed into an orbit that makes it even less habitable. Jupiter and Saturn, the solar system's gravitational anchors, would experience altered orbits that ripple through the entire planetary arrangement. The asteroid belt, currently stable in gaps maintained by Jupiter's gravity, could destabilize. Resonances that previously kept asteroids in safe orbits might break down, sending debris inward toward the inner planets. Impact rates could increase significantly over geological timescales. None of this happens overnight. A captured star doesn't immediately scramble planetary orbits. The changes unfold over decades, centuries, millennia. But they're directional. The solar system wouldn't settle into a new stable state identical to the old one. It would transition toward a different equilibrium, one that might not include Earth in the habitable zone. From a human perspective, even the short-term effects present serious challenges. Agriculture depends on predictable growing seasons. Water resources rely on consistent precipitation patterns driven by stable atmospheric circulation. Infrastructure assumes certain temperature ranges and weather extremes. All of that gets recalibrated when the fundamental energy input to the climate system becomes variable. And we're still assuming the best case where the second star approaches gently and settles into a distant orbit. More likely scenarios involve closer approaches that don't result in capture but still perturb planetary orbit significantly during the encounter. A star passing through the outer solar system would gravitationally scatter comets from the Oort cloud, sending them falling inward. Some would miss Earth. Some wouldn't. The impact risk would spike for thousands of years after the encounter as these disturbed objects crossed the inner system. Planetary orbits themselves could shift. Not dramatically, not instantly, but enough to matter. Earth might end up in a slightly wider orbit, reducing solar radiation and triggering gradual cooling. Or a slightly tighter orbit, increasing temperatures and accelerating ice melt. Either direction creates a planet humans didn't evolve on and haven't built civilization around. The probability of capturing a second star remains extremely low. Space is vast, stellar encounters are rare, and the specific conditions needed for stable capture are narrow. But stellar flybys, close enough to disrupt things without capture, occur more frequently on geological timescales. The Sun will experience multiple close encounters with other stars over its remaining lifespan. Most will pass without incident. Some won't. And this assumes we're only dealing with normal stars. What if the intruder is a white dwarf, a stellar remnant much smaller but incredibly dense? Or a neutron star, packing more mass than the Sun into a sphere 20 kilometers across? The gravitational effects scale with mass, not volume. A neutron star passing through the outer solar system would wreak havoc despite being physically tiny. These objects are harder to detect at distance because they emit little light. A white dwarf shines dimly. A neutron star barely radiates in visible wavelengths. By the time we noticed one approaching, it might be too late to do anything beyond calculating the consequences. The galaxy contains billions of stellar remnants drifting through interstellar space. Most are isolated, moving on predictable paths that won't intersect our neighborhood. But on timescales of millions or billions of years, encounters become statistically inevitable. The solar system will interact with other massive objects. The question isn't if, but when and how severely. We can model these scenarios mathematically. We can run simulations showing what happens to planetary orbits under various perturbations. We can calculate impact probabilities and climate shifts. What we can't do is prevent them or predict them far enough in advance to matter. That leaves us in an odd position. We understand the risks. We know the mechanisms. We can describe in detail what would happen under different conditions. But we can't defend against threats operating at stellar scales with energies and masses that make human technology irrelevant. This isn't fatalism. It's recognition that some problems exist outside our ability to solve. You don't build contingency plans for events that would end technological civilization because there's no point. Either the event doesn't happen and the planning was unnecessary, or it does happen and the plans don't help. What matters instead is understanding our place in a dynamic galaxy where stability is temporary and change is guaranteed. The solar system occupies its current configuration because nothing has disturbed it recently. That's not a permanent state. It's a snapshot of one moment in an ongoing process that operates on timescales longer than human history but shorter than planetary lifespans. The Sun formed 4.6 billion years ago from a collapsing molecular cloud. It will continue fusing hydrogen for another 5 billion years before exhausting its core fuel and expanding into a red giant. Within that time span, the solar system will experience multiple gravitational encounters with passing stars, clouds of interstellar matter, and possibly rogue planets or stellar remnants. Most encounters will be minor. A slight tug on the Oort cloud. A tiny shift in planetary orbits too small to measure. Occasionally, something more significant occurs. A star passes within a light year, scattering comets inward. A molecular cloud drifts through the system, altering solar radiation through increased dust. A massive object transits nearby, pulling planets into new configurations. These are not hypothetical scenarios invented to frighten people. They're documented processes observed in other stellar systems and predicted by our understanding of galactic dynamics. We exist in a galaxy that doesn't care about preserving any particular arrangement of matter. Stars form, evolve, and die. Planets coalesce and get destroyed. Systems reorganize under gravitational influences that operate without regard for what lives on them. Acknowledging this doesn't mean giving up. It means recognizing which problems require solutions and which require acceptance. We can't prevent stellar encounters. We can understand them, model them, and perhaps detect them earlier with better observation networks. That knowledge serves a purpose even if it doesn't change outcomes. Human time operates on scales measured in decades or centuries. Stellar mechanics operate on scales measured in millions of years. That disconnect creates a perceptual problem. We evolved to recognize immediate threats. Predators, storms, drought. Our nervous systems weren't built to process dangers that unfold over timeframes longer than civilizations exist. A star passing within 2 light-years over the next million years doesn't trigger the same response as something happening next week. But the physics doesn't care about our perception. Gravity operates continuously. Orbits shift gradually. What seems stable on human timescales reveals itself as dynamic when viewed across proper intervals. Jupiter's orbit changes. Saturn's rings evolve. The Moon recedes from Earth at about 4 centimeters per year. These aren't static objects frozen in place. They're participants in an ongoing gravitational negotiation that never stops. Now scale that up to galactic levels. The Milky Way contains 200 billion stars, most with their own planetary systems. Add brown dwarfs, rogue planets, stellar remnants, molecular clouds, and regions of concentrated dark matter. Everything moves. Everything pulls on everything else within its gravitational influence. The result is a galaxy in constant motion, where encounters between systems happen regularly across cosmic timescales. Our Sun orbits the galactic center once every 230 million years. During each orbit, it passes through different regions of the galaxy. Spiral arms, interarm regions, areas of higher and lower stellar density. Each environment presents different risks. Spiral arms contain more massive stars, which means more supernovae, more stellar winds, more radiation. They also contain giant molecular clouds that can trigger ice ages by blocking sunlight. Interarm regions are quieter but not empty. Rogue objects drift through these spaces. Stellar remnants. Planets ejected from their original systems. Objects too dim to detect until they're relatively close. The galaxy doesn't maintain clear boundaries between safe and dangerous zones. It's all dangerous given enough time. What varies is the probability and severity of encounters. Right now, the solar system occupies a relatively calm neighborhood. The nearest star, Proxima Centauri, sits 4.2 light-years away. That's far enough that its gravitational influence on our planets is negligible. The next closest stars are also comfortably distant. This configuration is temporary. Stars move at different velocities relative to each other. In about 30,000 years, a red dwarf called Ross 248 will pass within 3.2 light-years of the Sun, becoming our closest neighbor for a time. Then it will continue on its path and something else will take its place. These close passes happen regularly on galactic timescales. Most are harmless. A star passing within 5 light-years exerts minimal gravitational influence on planets orbiting another star. The effects are measurable in simulations but negligible in practice. Closer encounters are rarer but more consequential. A star passing within 1 light-year would perturb the Oort cloud significantly, potentially sending comets into the inner solar system for millions of years afterward. A star passing within half a light-year could affect planetary orbits directly, though the changes would be subtle unless the encounter was extremely close. The problem is detection. We can track nearby stars with current technology, but only the relatively bright ones. Dim red dwarfs, brown dwarfs, and rogue planets are much harder to spot until they're already close. Infrared surveys have improved our ability to find these objects, but gaps remain. Something could be approaching that we won't notice until it's within a few light years. By then, we'd have thousands of years to study it but no ability to change its trajectory. Altering the path of a stellar mass object would require energy expenditures far beyond anything human technology can produce. You can't nudge a star the way you might deflect an asteroid. The mass difference is too large. The energies involved too extreme. Even if we had millions of years to prepare, the engineering challenges would be insurmountable. Which brings us back to the same conclusion. Observation and understanding, yes. Prevention, no. We can map nearby space. We can identify potential threats decades or centuries before they arrive. We can calculate exactly what will happen during an encounter. None of that changes the outcome. It just means we'll know what's coming. There's value in that knowledge even without the ability to act. Understanding allows for preparation of a different kind. Not physical defenses, but intellectual frameworks. If we know a stellar encounter will destabilize the Oort cloud in 50,000 years, that information becomes part of how future generations think about long-term survival. Maybe it influences where deep space probes are sent. Maybe it affects how astronomical databases are maintained. Maybe it does nothing practical but satisfies the human need to understand our environment. That need is real even when it doesn't lead to solutions. We study supernovae knowing we can't prevent them. We model black hole behavior knowing we'll never interact with one. We map the cosmic microwave background knowing it tells us about events we can't influence. Knowledge has value independent of utility. Stellar encounters fall into that category. They're important to understand because they're part of the environment we exist in. They shape planetary evolution. They influence the long-term habitability of solar systems. They determine which configurations of planets remain stable over billions of years. Earth exists in its current form partly because the solar system hasn't experienced a major gravitational disruption since planets finished forming. That stability allowed life to develop, evolve, and eventually produce technological civilization. It's not guaranteed to continue. At some point, something will pass close enough to change things. When that happens, the consequences depend entirely on what passes and how close it gets. A distant encounter might scatter some comets. A close encounter could reshape orbits. An extremely close encounter could eject planets from the solar system entirely. These aren't equally likely. The probability decreases dramatically as encounters get closer. But over billions of years, even low-probability events become near certainties. The Sun will experience multiple close encounters before it exhausts its hydrogen fuel. Some will be minor. At least one might be significant. The galaxy guarantees change over sufficient timescales. What it doesn't guarantee is survivability. Systems that get disrupted don't recover their original configurations. Planets that get ejected don't return. Once gravitational chaos reaches a certain threshold, the system reorganizes into a new stable state that might look nothing like the original. This has already happened to countless other systems. We observe planetary systems with highly eccentric orbits, planets too close to their stars, gas giants in locations where they couldn't have formed. These are signatures of past disruptions. Encounters with other stars. Planetary migrations triggered by gravitational interactions. Systems that reorganized after their original configurations became unstable. Our solar system shows signs of its own past reorganization. The NICE model suggests that Jupiter, Saturn, Uranus, and Neptune didn't form in their current positions. They migrated inward and outward after formation, possibly triggered by encounters with planetesimals or resonances between their orbits. This migration would have scattered smaller bodies throughout the solar system, explaining features like the late heavy bombardment 4 billion years ago. If that model is correct, the solar system has already experienced major gravitational reshuffling. What we see now is the result of that reorganization, not the original configuration. Which means change isn't hypothetical. It's already happened. The question is whether it will happen again during the remaining lifespan of the Sun. Probability suggests yes. Timing remains unknown. The galaxy contains too many variables to predict specific encounters far in advance. We can calculate general probabilities. We can identify nearby objects and track their movements. We can model what would happen under different scenarios. What we can't do is point to a specific date and say this is when the next major disruption occurs. That uncertainty is permanent. It's built into the nature of galactic dynamics. Too many objects moving in too many directions with too many possible interactions. Even perfect knowledge of current positions and velocities wouldn't allow precise predictions millions of years ahead because gravitational interactions are chaotic. Small changes in initial conditions produce large differences in outcomes over time. Free body problems are analytically unsolvable. Stellar neighborhoods involve millions of bodies. The math doesn't allow exact long-term predictions even in principle. We're left with statistical models and probability ranges. Useful for understanding general patterns but useless for predicting specific events. That's not a limitation of current technology. It's a fundamental feature of how gravity works in systems with multiple interacting masses. Chaos isn't something better computers can solve. It's an inherent property of the equations governing motion. Which means we'll never have certainty about future stellar encounters. We'll have better observations, more detailed models, improved probability estimates. We won't have schedules. The galaxy doesn't operate on schedules. It operates on physics, which produces patterns but not predictability. Stars move through space according to gravitational laws that allow probability calculations but resist precise forecasting over timescales measured in millions of years. The Sun's journey through the galaxy has already lasted 4.5 billion years. During that time, it's completed roughly 20 orbits around the galactic center. Each orbit takes between 200 and 250 million years, depending on the Sun's exact distance from the center and the distribution of mass in the galaxy. 20+ complete circuits means 20+ passages through the spiral arms, dozens or hundreds of close encounters with molecular clouds, and countless interactions with the changing gravitational landscape of the Milky Way. The solar system survived all of it. The planets remained in stable orbits. Earth maintained conditions suitable for life across geological timescales. Whatever encounters occurred during those billions of years, none were catastrophic enough to eject planets or sterilize Earth. That's not luck. It's statistics. Most stellar encounters are distant enough to cause minimal disruption. The dangerous ones are rare. Over billions of years, the rare events that do occur tend to fall within a range the system can absorb without complete destruction. But survival of past encounters doesn't guarantee immunity from future ones. Each passage through a spiral arm resets the probability. Each orbit through the galaxy exposes the Sun to new potential interactions. The gravitational environment changes constantly as stars move through their own orbits, clusters form and dissolve, and the galaxy's structure evolves. What protected the solar system during previous orbits might not be sufficient during future ones. The distribution of stars changes. Regions that were once relatively empty can become more crowded as stellar populations shift. The Sun's current path through the galaxy might take it through denser neighborhoods than it experienced in the past. Or it might lead it into quieter regions. There's no way to know without detailed mapping of stellar trajectories across millions of years, which remains beyond current observational capabilities. One factor that does influence encounter probability is the Sun's vertical oscillation through the galactic plane. The Sun doesn't orbit the galactic center in a flat circle. Its path carries it above and below the galactic plane in a wave-like motion, crossing through the plane approximately every 30 to 40 million years. When the Sun passes through the galactic plane, it encounters higher stellar densities than when it's above or below. The plane contains most of the galaxy's visible matter, including stars, gas, and dust. Crossing through it increases the probability of close encounters simply because there are more objects present. Some researchers have suggested this oscillation might correlate with mass extinction events on Earth, proposing that encounters with molecular clouds or increased comet impacts occur more frequently during plane crossings. The evidence remains debated. Extinction patterns don't show clear periodicity matching the oscillation cycle. Even if a correlation exists, it would demonstrate that galactic position influences Earth's history, not that future crossings will necessarily produce similar effects. Each crossing involves different molecular clouds, different stellar configurations, different gravitational contexts. Past patterns don't predict future outcomes with certainty. Beyond stellar encounters, the Sun faces long-term changes in the galaxy's overall structure. The Milky Way is currently on a collision course with the Andromeda Galaxy. The two galaxies will begin interacting in approximately 4 billion years, with a full merger occurring over the following few billion years. During galactic mergers, stellar orbits get disrupted on massive scales. Stars that once followed predictable paths around their galactic centers get scattered into new configurations as the two galaxies' gravitational fields interfere with each other. The Sun will likely survive the merger physically. Galactic mergers don't involve stars actually colliding because the distances between stars are enormous compared to their sizes. Even when two galaxies interpenetrate completely, the probability of any given star hitting another star remains vanishingly small. What changes is orbital structure. The Sun's current orbit around the Milky Way's center will become meaningless as that center merges with Andromeda's center. The combined galaxy, sometimes called Melkomena, will have a different shape, different rotation, different gravitational architecture. The Sun will end up in a new orbit around the merged galaxy's center, potentially far from its current position. That repositioning might place the Sun in denser regions with higher encounter probabilities, or in sparser regions with lower probabilities. The outcome depends on details of the merger that can't be predicted precisely. Simulations show general patterns but can't specify where individual stars end up. Too many variables. Too many gravitational interactions occurring simultaneously. The merger timeline presents an interesting coincidence. 4 billion years from now, the Sun will be nearing the end of its main sequence lifetime. It will have exhausted most of its hydrogen fuel and begun transitioning toward the red giant phase. The Andromeda merger will commence around the same time the Sun starts expanding. Earth's fate might be sealed by solar evolution before galactic dynamics become the dominant concern. As the Sun expands into a red giant, it will engulf Mercury and Venus. Whether it reaches Earth's orbit remains uncertain and depends on exact mass loss rates during the expansion. Even if Earth's orbit isn't physically consumed, the increased solar radiation will vaporize the oceans and strip away the atmosphere long before the Sun's surface reaches Earth's position. By the time the galactic merger creates new gravitational dynamics, Earth will likely already be uninhabitable. That doesn't mean stellar encounters before then are irrelevant. Between now and the Sun's red giant phase, roughly 5 billion years remain. During that time, the Sun will complete another 20 orbits around the galaxy. 20 more passages through spiral arms. Hundreds more opportunities for close encounters. The probability that at least one significant encounter occurs during those 5 billion years is not negligible. What constitutes a significant encounter? Definitions vary depending on what effects you're measuring. For disrupting the Oort cloud and potentially triggering comet showers, encounters within 1 or 2 light years matter. For perturbing planetary orbits directly, encounters need to be much closer, probably within a few thousand astronomical units. For ejecting planets entirely, encounters likely need to approach within hundreds of astronomical units. Each category has different probabilities and different consequences. Oort cloud disruptions are relatively common on million-year timescales. Direct planetary perturbations are rare but not impossible. Planetary ejections are extremely rare but have definitely occurred in other systems. The solar system probably won't experience a catastrophic close encounter during the next billion years. Probably. That's the strongest statement physics allows. The galaxy doesn't provide guarantees. Observation programs continue tracking nearby stars, measuring their positions, velocities, and trajectories. As data accumulates, predictions improve for specific stars over limited time periods. Gliese 710 will pass within 10,000 astronomical units in about 1.3 million years. HIP 85605 might come within 16,000 astronomical units in 240,000 years. These predictions carry uncertainty margins that increase with distance into the future. A star projected to pass at 10,000 astronomical units might actually pass at 8,000 or 12,000 depending on factors not fully constrained by current measurements. The difference matters when calculating gravitational effects on the Oort cloud. Small changes in closest approach distance produce large changes in the number of comets perturbed. Even with improving data, predictions beyond a few million years remain probabilistic rather than deterministic. The galaxy contains too many objects with too many possible interactions. The Sun's journey through the galaxy continues. Right now, it's moving toward the constellation Hercules at roughly 250 kilometers per second relative to the local standard of rest. That motion carries it through neighborhoods where stellar densities fluctuate, molecular clouds drift, and gravitational influences shift. Over the next 100 million years, the Sun will move several thousand light-years from its current position. New stars will become neighbors. Current neighbors will drift away. The gravitational landscape surrounding the solar system will transform completely multiple times before the Sun exhausts its hydrogen fuel. Each transformation brings new encounter possibilities. Each possibility carries a probability that can be calculated but not eliminated. The galaxy guarantees that change happens. It doesn't specify when or how severely. Our solar system exists in a dynamic environment where stability is temporary and disruption is eventual. Not immediate. Not predictable in detail. But inevitable given sufficient time. That's the nature of gravitational systems with many interacting bodies moving through space. Chaos emerges from deterministic laws. Probability replaces certainty. Patterns appear but predictions fail beyond certain timescales. The Sun will continue orbiting the galactic center, crossing through spiral arms, oscillating above and below the galactic plane, encountering molecular clouds and passing stars. Most encounters will be distant and inconsequential. Some will perturb the Oort cloud and send comets toward the inner solar system. A few might disturb planetary orbits enough to measure. One might eventually be close enough to fundamentally alter the solar system's architecture. We can't prevent it. We can't predict exactly when it will happen. We can only observe, calculate probabilities, and understand that the galaxy operates on timescales where rare events become commonplace. The question isn't whether the solar system will experience future disruption. The question is whether it will happen during a time frame that matters to us. For the next few million years, probably not. Beyond that, certainty dissolves into probability, and probability suggests that eventually, something significant will occur. The galaxy has 400 billion stars moving through space. The Sun is one of them, following its orbit through a constantly shifting gravitational landscape. Every orbit brings new encounters. Every encounter carries probabilities. Given enough orbits, those probabilities converge toward inevitability. That's not pessimism. That's mathematics applied to gravity operating across billions of years in a galaxy that never stops moving. The galaxy we inhabit operates without regard for our presence. Rogue black holes drift through the darkness between stars, following paths set by violent births millions or billions of years ago. Hundreds of millions of them, perhaps more, scattered across the Milky Way like invisible landmines in a cosmic ocean. We've detected a handful. The rest remain hidden, detectable only through rare gravitational lensing events that require perfect alignment and extraordinary luck. Detection methods improve. Surveys expand. Observation networks grow more sophisticated. None of it changes the fundamental problem. We're looking for objects that emit no light, produce no radiation, and reveal themselves only by bending the light of background stars during brief windows of alignment. Even when we catch these events, we're seeing something that happened years or centuries ago. The black hole itself has already moved on, continuing along a trajectory we can't predict with useful precision. The mathematics of galactic dynamics allows probability calculations but resists exact forecasting. Too many objects moving in too many directions with too many possible interactions. Free body problems are analytically unsolvable. Stellar neighborhoods involve millions of bodies. Chaos emerges from deterministic laws. Small changes in initial conditions produce wildly different outcomes over time. We can model general patterns but can't predict specific encounters millions of years ahead. That uncertainty is permanent. It's built into how gravity works in systems with multiple interacting masses. Better observations won't fix it. More powerful computers won't solve it. The galaxy doesn't operate on schedules we can map. It operates on physics that produces patterns but not predictability. What matters is understanding our position within this dynamic system. The solar system exists in its current configuration because nothing has disrupted it recently. That's not a permanent state. It's a temporary snapshot of one moment in an ongoing process that operates on timescales longer than human history but shorter than planetary lifespans. Change is guaranteed over sufficient time. What isn't guaranteed is survivability. Systems that get disrupted don't recover their original configurations. Planets that get ejected don't return. Once gravitational chaos reaches a certain threshold, everything reorganizes into a new stable state that might look nothing like what came before. This has happened to countless other systems. We observed the signatures in eccentric orbits, misplaced planets, and configurations that couldn't have formed naturally. Evidence of past encounters that reshaped entire solar systems. Our own system shows signs of reorganization in its past. the planets might not occupy their original positions. The late heavy bombardment 4 billion years ago suggests major gravitational reshuffling occurred. What we see now could be the result of that ancient chaos, not the initial arrangement. Which means change isn't hypothetical. It's already happened here. The question is whether it will happen again on timescales that matter to anything currently alive. Probability suggests yes, eventually. Timing remains unknown. The Sun will experience multiple close encounters with other stars, molecular clouds, and possibly rogue black holes before it exhausts its hydrogen fuel. Most will be minor. Some might be significant. One could potentially be catastrophic. The galaxy guarantees encounters over billions of years. It doesn't specify which ones will matter or when they'll occur. We can't defend against threats operating at stellar scales. We can't deflect a black hole or alter the trajectory of a passing star. The mass differences are too large. The energies involved too extreme. Even with millions of years to prepare, the engineering challenges would remain insurmountable. You can't nudge a stellar mass object the way you might deflect an asteroid. What we can do is observe, understand, and acknowledge which problems exist outside our ability to solve. Knowledge has value independent of utility. We study phenomena we can't influence because understanding our environment matters even when we can't control it. Rogue black holes are part of that environment. They shape galactic evolution. They influence which planetary configurations remain stable over billions of years. They determine, in ways we're only beginning to understand, which systems survive long enough for complex life to develop. Earth exists in its current form partly because the solar system hasn't experienced a major gravitational disruption since planets finished forming. That stability allowed life to develop, evolve, and eventually produce technological civilization. It's not guaranteed to continue. At some point, something will pass close enough to change things. When that happens, the consequences depend entirely on what passes and how close it gets. The galaxy contains 400 billion stars moving through space, countless stellar remnants, molecular clouds, rogue planets, and objects we haven't cataloged yet. Everything pulls on everything else within its gravitational influence. The result is a galaxy in constant motion where encounters between systems happen regularly across cosmic timescales. Most are harmless. Some aren't. The difference comes down to distance, mass, velocity, and timing. Variables we can measure in nearby objects but can't predict far in advance for the galaxy as a whole. So we exist in a dynamic galaxy where invisible predators drift through the darkness, occasionally reshaping solar systems they pass near. We have no systematic way of knowing where most of them are or where they're going. The best we can do is understand the physics, recognize the risk exists, and accept that some threats operate on scales beyond human ability to address. That acceptance isn't fatalism. It's recognition of what we can and can't control, and focusing effort on things that actually matter within our capability to influence. The galaxy operates according to physical laws that don't care about preserving any particular arrangement of matter. Stars form, evolve, and die. Planets coalesce and get destroyed. Systems reorganize under gravitational influences that operate without regard for what lives on them. We're participants in that process, not exempt from it. Understanding that doesn't change outcomes. It just means we'll know what we're looking at when the galaxy reminds us that stability is always temporary. Deep in the frozen vacuum of space, chunks of ancient ice and rock are hurtling toward Earth at speeds that would vaporize steel on contact. Inside them, locked within crystalline structures older than our sun, might be the answer to humanity's oldest question. Where did we come from? For decades, scientists dismissed comets as cosmic debris, dirty snowballs with no real significance beyond their spectacular light shows. Then something changed. When we finally caught up to these objects, when our spacecraft touched them and tasted their chemistry, we found something nobody expected. The building blocks of life itself, fully formed, perfectly preserved, waiting. This isn't speculation anymore. It's data. Hard, repeatable, undeniable data that's forcing us to rewrite the story of life on Earth. Before we had telescopes, before we understood what comets were, they terrified us. Ancient civilizations saw them as omens, disasters written in fire across the night sky. The Romans called them hairy stars because of their streaming tails. Chinese astronomers meticulously recorded their appearances, convinced they predicted the fall of dynasties. Nobody imagined these objects might be delivering something rather than threatening it. The modern scientific view wasn't much kinder. Through most of the 20th century, comets were considered interesting but irrelevant to the story of life. They were leftovers from the solar system's formation, frozen relics that occasionally swooped through the inner planets before vanishing back into the dark. Beautiful, yes. Important to biology, not a chance. That assumption held until we started catching them. In 2004, NASA's Stardust mission did something remarkable.
Guidance is internal. Roll program initiated.
It flew through the coma of Comet Wild 2, that glowing cloud of gas and dust surrounding the nucleus, and collected samples. Not much, just microscopic particles captured in a substance called aerogel, but enough. When those samples returned to Earth 2 years later, the results stopped people in their tracks. Glycine. A simple amino acid, one of the fundamental building blocks that cells use to construct proteins. It was sitting right there in the comet dust, formed in the freezing darkness of space long before Earth even existed. That discovery opened a door. If glycine could form in comets, what else might be hiding in them? The answer came from an unlikely source. In 2014, the European Space Agency's Rosetta mission arrived at Comet 67P, a rubber duck-shaped chunk of ice about 4 kilometers across. Instead of just flying past, Rosetta stayed. It orbited for 2 years, watching the comet wake up as it approached the sun, measuring everything it could. What Rosetta found wasn't just interesting, it was revolutionary. The comet was outgassing 16 different organic compounds, not simple molecules, but complex carbon-based structures. Formaldehyde, methanol, ethanol, amino acids, and something else. Something that made biologists sit up and pay attention. Phosphorus. An element absolutely essential for life as we know it. It forms the backbone of DNA. It's in every cell membrane. Without phosphorus, Earth-style biology simply cannot function. And here it was, streaming off a comet billions of miles from the nearest living thing. The implications were staggering. These weren't random chemicals. They were the exact ingredients you'd need to start building the machinery of life. But finding ingredients isn't the same as proving they created something. You can have flour, eggs, and sugar sitting on a counter, and they won't spontaneously become a cake. Something has to bring them together under the right conditions. Something has to do the mixing. That's where Earth's early history becomes critical. 4.5 billion years ago, our planet was a molten nightmare. Volcanic hellscape, no stable crust, certainly no oceans. Not exactly a promising environment for delicate organic chemistry. Yet somehow, Within a few 100 million years, life appeared. Not gradually, not tentatively, but explosively. By 3.8 billion years ago, we have clear evidence of cellular life already thriving. That timeline has always bothered scientists. It's too fast. Earth barely had time to cool down before biology showed up. Where did all the necessary building blocks come from? How did they organize themselves so quickly? The traditional answer was that Earth made them itself. Lightning strikes in a primordial atmosphere, volcanic vents pumping out chemicals, ultraviolet radiation breaking apart simple molecules and recombining them into complex ones. The famous Miller-Urey experiment in 1953 seemed to prove this was possible. Put some basic gases in a flask, add electricity to simulate lightning, and amino acids appear. Except there's a problem. We got the atmosphere wrong. The Miller-Urey experiment used methane, ammonia, and hydrogen, a strongly reducing mixture that favors organic chemistry. But geological evidence now suggests early Earth's atmosphere was mostly carbon dioxide and nitrogen. Run the experiment with those gases and you get almost nothing. The chemistry doesn't work. So if Earth wasn't making its own organic molecules efficiently, where were they coming from? Look up. Every year, Earth sweeps through debris left behind by comets. We see it as meteor showers, beautiful streaks of light as tiny particles burn up in the atmosphere. But not everything burns. Some material makes it through, settling gently onto the surface. Modern estimates suggest Earth gains about 40,000 tons of cosmic dust annually. That's now, in a relatively clean solar system. 4 billion years ago, during the period we call the Late Heavy Bombardment, the rate was millions of times higher. Picture it. Young Earth, still cooling, oceans just beginning to condense from steam. And it's being absolutely pelted by comets and asteroids, hundreds of impacts every year, each one delivering its cargo of organic molecules. Not just simple stuff, but complex, ready-made building blocks for biochemistry. The entire planet becomes a chemistry lab being constantly restocked with new ingredients. This is where the math gets interesting. Calculate the total mass of cometary material that hit Earth during the first billion years. Factor in the concentration of organic compounds we've measured on real comets. Run the numbers and you get something shocking. Comets could have delivered more organic carbon to early Earth than the planet could possibly have made on its own. By a lot. Maybe by factors of thousands or millions. But quantity isn't everything. You also need the right delivery mechanism. Drop complex organic molecules onto a planet from space and they face a problem. They're moving at cosmic speeds, tens of kilometers per second. That kind of impact generates heat. Lots of heat. Enough to break apart most chemical bonds and destroy exactly the compounds you're trying to deliver. Except comets have a trick. They're not solid rock. They're mostly ice, mixed with dust and organics. When a comet hits an atmosphere, or even a primordial ocean, that ice acts like a cushion. It absorbs energy, vaporizes, creates a shock buffer. Calculations show that organic molecules buried inside cometary ice can survive impacts that would obliterate anything else. The ice protects its cargo all the way down. Even better, that ice itself is valuable. Early Earth needed water. Lots of water. Our planet formed close to the sun, in a region too hot for ice to condense. The water in our oceans had to come from somewhere colder. Comets fit perfectly. They're essentially giant ice cubes that formed in the outer solar system and then migrated inward. Each impact was a water delivery, bringing not just H2O but also everything dissolved in it. We can test this idea chemically. Water molecules come in different isotopes, variations with extra neutrons. The ratio of regular hydrogen to deuterium, heavy hydrogen, works like a fingerprint. Measure it in Earth's oceans and compare it to measurements from comets. If the ratios match, you found your source. The results are messy. Some comets match Earth's ratio almost perfectly. Others are way off. What this tells us is that Earth's water probably came from multiple sources. Some comets, yes, but also asteroids, and possibly some water that was trapped in the rocks that originally formed our planet. It's a mixture, which actually makes sense. 4 billion years of bombardment meant Earth was sampling everything the solar system had to offer. But we're getting ahead of ourselves. Delivering organic molecules is one thing. Getting them to organize into something alive is something else entirely. The molecules are here. They're scattered across the early Earth's surface, dissolved in the oceans, maybe concentrated in tidal pools or around hydrothermal vents. But molecules don't spontaneously decide to become alive. They need to do something first. They need to replicate. This is the central mystery. Life, at its core, is information that copies itself. DNA holds instructions. Those instructions get read, executed, and then copied to make more DNA. But DNA can't copy itself alone. It needs proteins. Enzymes that unzip the double helix, read the code, assemble new strands. Proteins are molecular machines, and they're incredibly good at their jobs. Except proteins can't make themselves either. They need DNA to encode their blueprints. You see the problem. DNA needs proteins. Proteins need DNA. It's a chicken and egg paradox, except both the chicken and the egg are microscopically small and made of carbon chains. For decades, this looked unsolvable. Then, in the 1980s, scientists discovered something that changed everything. RNA, ribonucleic acid, DNA's simpler cousin, and RNA could do something nobody expected. It could act as both information storage and enzyme. Some RNA molecules, called ribozymes, could catalyze chemical reactions, including, critically, making copies of other RNA molecules. Suddenly there's a way out of the paradox. Forget DNA and proteins for now. Start with RNA. One molecule playing both roles. An RNA world, where these versatile chains are doing all the heavy lifting. Storing information, copying themselves, maybe even catalyzing the reactions needed to build their own components. It's elegant. Almost too elegant. But does it actually work? Test it. Take RNA molecules and put them under conditions that might have existed on early Earth. See if they can evolve, adapt, replicate without any help from modern biology. Researchers have done exactly this. They've created RNA molecules that can copy other RNA strands with reasonable accuracy. They've shown that random RNA sequences, given the right environment, can develop catalytic activity through pure trial and error. The chemistry works. RNA can bootstrap itself. But there's still a massive gap between one self-replicating RNA molecule and anything we'd recognize as alive. That molecule needs protection. It needs to separate itself from the environment, create an inside and an outside. Otherwise, every molecule it makes just diffuses away into the ocean. No concentration, no organization, no evolution. This is where membranes come in. Lipids, fatty molecules with one end that loves water and another that hates it, can spontaneously form bubbles. Vesicles. Little spheres with a double-layered skin that keeps the inside separate from the outside. We see this in test tubes. Mix lipids and water and they self-assemble into something that looks startlingly like a cell membrane. No instructions needed. Just physics and chemistry doing their thing. Now imagine an RNA molecule that happens to be inside one of these lipid bubbles. It's replicating, making copies of itself. Those copies are trapped inside with it. The concentration builds. Maybe some of those RNA molecules catalyze reactions that help make more lipids, growing the membrane. The bubble gets bigger. Eventually it might split, dividing into two bubbles, each carrying RNA. You've just invented cellular division without involving a single protein or DNA molecule. This isn't life yet. Not quite, but it's something that can evolve. Bubbles with better RNA that replicates faster or makes useful products, will outcompete bubbles with worse RNA. Selection pressure exists even at this primitive level. And once you have selection, evolution is inevitable. The timeline here is staggering. We're talking about processes that might have taken tens of millions of years. Maybe 100 million. The early Earth had time, lots of it, and it had variety, thousands of different environments, each running its own chemical experiments. Shallow pools heated by the sun, deep ocean vents with their chemical gradients, underground water systems percolating through mineral-rich rock, ice formations with liquid pockets. Every one of these is a potential laboratory. What's fascinating is that you don't need everything to happen in one place. Maybe RNA replication gets figured out in one environment, membrane formation in another. Then geological processes, volcanic eruptions, tidal movements, mix everything together. Combine the solutions. Evolution doesn't follow a neat, linear path. It's messy, parallel, full of dead ends and lucky accidents. But here's what really matters. Once you have something that can replicate and evolve, even if it's incredibly primitive, you've crossed a threshold. Because evolution is brutally good at solving problems. Give it enough time and enough variation, and it will find solutions to challenges that seem impossible. Like replacing fragile RNA with more stable DNA, or developing protein synthesis to build better enzymes than ribozymes could ever be. The transition from an RNA world to the DNA protein world we have now probably happened gradually. Maybe DNA started as just a more stable way to store backup copies of important RNA sequences. Then it got better at the job. Eventually it took over information storage completely, while proteins specialized in doing the actual work. RNA got relegated to the role it plays today, messenger, translator between DNA and proteins. We can see echoes of this ancient RNA world in modern cells. Ribosomes, the molecular machines that build proteins, are made mostly of RNA. The energy currency of the cell, ATP, is basically an RNA building block with some extra phosphate groups attached. Even DNA synthesis requires RNA primers to get started. These are fossils, chemical fossils, remnants of a time when RNA did everything. But proving this all happened is hard. RNA doesn't fossilize. It's too fragile. The oldest actual fossils we have are from about 3.5 billion years ago. Stromatolites, layered rock structures built by bacterial mats. By that point, life was already sophisticated. DNA, proteins, cell walls, photosynthesis. The really interesting stuff, the origin itself, happened earlier. Maybe 4 billion years ago, maybe even older, and it left almost no direct evidence. So we're forced to reconstruct it from clues, chemical signatures in ancient rocks, isotope ratios that suggest biological activity, computer simulations of prebiotic chemistry, lab experiments trying to recreate the conditions. Every piece of evidence is indirect, circumstantial. But they all point in the same direction. Life emerged from chemistry, not through some mysterious vital force, but through processes we can understand, replicate, and test. There's one more piece to this puzzle. One that makes the whole thing even stranger. The genetic code. The way DNA sequences get translated into amino acids, which then fold into proteins. This code is nearly universal. Bacteria use it. Plants use it. Animals use it. With tiny variations, every living thing on Earth reads DNA the same way. Which means the code was established early, probably before the last common ancestor of all life. And once it was set, it was locked in. Changing your genetic code would be like rewriting the operating system on a computer while it's running. Possible in theory, but catastrophically difficult in practice. Why this particular code? Is it optimal? Or just a frozen accident, the first solution that worked well enough? Some researchers argue it's actually pretty good at minimizing the damage from mutations. Similar codons often code for chemically similar amino acids. So if a mutation changes one letter in a codon, there's a decent chance the resulting protein still works. That's not random. That's error correction built into the system, but it's also consistent with evolution. An early, slightly error-prone genetic code that worked well enough to get life started. Then, over time, selection pressure refined it. Lineages with codes that handled errors better survived. Those with worse codes died out. What we're left with is the optimized version. Not perfect, but good enough to support the incredible diversity of life we see today. Step back and look at the full picture. 4 billion years ago, maybe earlier, Earth was a planet covered in organic chemistry experiments. Molecules delivered by comets and asteroids, synthesized in the atmosphere, cooked up around volcanic vents. RNA figuring out how to replicate. Lipids forming membranes. Everything mixing, reacting, competing. And somewhere in that chaos, a combination of molecules found a way to persist, to improve, to evolve. That combination was the first life. Not a single moment of creation, but a gradual transition from complex chemistry to simple biology. The boundary between non-living and living wasn't a line. It was a gradient. And we're still not entirely sure where exactly to draw it. Once life existed, even in its most primitive form, the rules changed. Natural selection kicked in. Not as a guiding force, but as an automatic filter. Anything that replicated more efficiently than its competitors spread. Anything less efficient vanished. No intention required. Just math playing out over deep time. The first cells were probably nothing like modern bacteria. Simpler, messier. Their membranes leaked. Their metabolism was inefficient. But they worked well enough to persist. And that's all evolution needs. A starting point. Once you have replication, variation, and selection, improvement becomes inevitable. Not planned, just statistically certain. Early Earth was divided into two broad domains: bacteria and archaea. They look superficially similar under a microscope. Single cells, no nucleus, circular DNA. But genetically, they're as different from each other as either is from us. Different membrane chemistry, different metabolic pathways, different cellular machinery. This split happened early, probably before 3.5 billion years ago. Why it happened is still debated. Maybe different environments selected for different solutions. Maybe it was just chance, two lineages drifting apart. Either way, both domains survived. Both thrived. Both are still here today. For the next 2 billion years, life stayed small. Microbial. Single cells doing their thing in the oceans, in sediments, around vents. It doesn't sound exciting, but this period was crucial. Because microbes invented almost everything: photosynthesis, respiration, nitrogen fixation, fermentation. Every major metabolic pathway we see in complex life today was pioneered by bacteria or archaea. They figured out how to extract energy from sunlight, from minerals, from organic molecules. They built the biochemical toolkit that all later life would inherit. Then, around 2.5 billion years ago, something dramatic happened. Cyanobacteria, a group of photosynthetic bacteria, started producing oxygen as a waste product. Not a little oxygen, industrial quantities, enough to fundamentally alter the planet's chemistry. This wasn't planned. Oxygen was toxic to most organisms at the time. But cyanobacteria had evolved a way to deal with it, and they thrived. Everyone else had to adapt or die. The buildup was slow at first. Oxygen reacted with dissolved iron in the oceans, forming rust that settled to the seafloor. Those deposits, called banded iron formations, are some of the richest iron ore reserves we have today. For hundreds of millions of years, the oceans soaked up the oxygen. But eventually, the iron ran out. Oxygen started accumulating in the atmosphere. This is called the Great Oxidation Event. It fundamentally restructured the biosphere. Most anaerobic organisms retreated to oxygen-free environments. Deep sediments, guts of animals, anywhere they could avoid the toxic gas. But other lineages adapted. They evolved ways to use oxygen for respiration, extracting far more energy from the same nutrients. Aerobic respiration is about 15 times more efficient than anaerobic metabolism. That's a game changer. It opened the door to larger, more complex organisms. But complexity didn't arrive immediately. For another billion years, life stayed stubbornly simple. Bacteria and archaea dominated. No multicellular organisms. No complex cells. Just microbes. Why the delay? We're not entirely sure. Maybe oxygen levels weren't high enough yet. Maybe nutrients were limiting. Maybe it just took that long for the right innovations to evolve. Evolution doesn't optimize for speed. It optimizes for survival. And single-celled life was surviving just fine. Then, around 1.5 to 2 billion years ago, something unprecedented happened. A bacterial cell got engulfed by an archaeal cell. Normally, that's dinner. But this time, the bacterial cell survived inside. It kept its own genome, its own membrane, and it started providing a service. It processed oxygen, generating energy for the host. In return, it got protection and nutrients. This wasn't cooperation. Not at first. More like a hostage situation that gradually became mutually beneficial. Over time, the bacterial cell lost most of its independence. Its genome shrank. Many of its genes migrated to the host's nucleus. But it kept its essential function: energy production. Today, we call these structures mitochondria. Every complex cell on Earth, every plant, every animal, every fungus, has them. They're the descendants of that ancient symbiotic event. Without mitochondria, complex life as we know it wouldn't exist. This wasn't a one-time fluke. It happened again with photosynthesis. An archaeal cell engulfed a cyanobacterium. Same deal. The cyanobacterium survived inside, kept photosynthesizing, became a permanent resident. Today, we call these chloroplasts. Every plant and algae has them. Two separate endosymbiotic events. Two different bacterial lineages incorporated into archaeal hosts. Both absolutely critical for the evolution of complex life. These hybrid cells are called eukaryotes. They're fundamentally different from bacteria and archaea. They have a nucleus, complex internal structures, linear chromosomes, sexual reproduction, the ability to grow large and differentiate into specialized cell types. Every organism you can see without a microscope is a eukaryote. Every tree, every insect, every fish, every human. We're all descendants of those ancient mergers. But even with eukaryotic cells, life stayed mostly single-celled for a long time. Maybe another billion years. Single eukaryotes floating around, eating bacteria, photosynthesizing. Then, gradually, some lineages started sticking together. Colonies formed. Simple at first. Just clusters of identical cells. But over time, cells within colonies began specializing. Some handled reproduction. Others handled feeding. Others provided structure. This is the origin of multicellularity. Not a sudden leap, but a gradual transition from independent cells to cooperative groups. Multicellularity evolved multiple times independently. Plants did it. Animals did it. Fungi did it. Even some bacteria and algae pulled it off. Each time, the pattern was similar. Cells stuck together, started dividing labor, became interdependent. Why? Because in certain environments, being big has advantages. You're harder to eat. You can capture more resources. You can differentiate into specialized structures: roots, leaves, muscles, nerves. Suddenly, evolution had a whole new playground. By about 600 million years ago, the first complex multicellular organisms appeared in the fossil record. Weird, soft-bodied creatures called the Ediacaran biota. Some looked like quilted fronds, others like segmented discs. They don't resemble anything alive today. Most of them went extinct without leaving descendants. But they proved that large, complex life was possible. They set the stage for what came next. Then, around 540 million years ago, the Cambrian explosion happened. Not an explosion in the literal sense. More like a sudden diversification. Within about 20 million years, most major animal body plans appeared. Arthropods, mollusks, chordates, echinoderms. Animals with hard shells, jointed legs, segmented bodies, eyes. The fossil record goes from sparse and strange to abundant and recognizable. What triggered the Cambrian explosion? Probably multiple factors. Oxygen levels rising to a critical threshold. Predator-prey dynamics creating evolutionary arms races. The evolution of developmental genes that allowed for complex body plans. Ecological feedback loops where one innovation triggered others. It wasn't a single cause. It was a cascade. Once it started, it accelerated. One of the most important innovations was eyes. The ability to see opened up entirely new survival strategies. Predators could hunt more effectively. Prey could escape more efficiently. Vision created selection pressure for faster movement, better armor, more sophisticated nervous systems. Suddenly, being smart mattered. Brains got bigger. Behavior got more complex. Another key innovation was hard body parts. Shells, exoskeletons, bones. Before the Cambrian, almost everything was soft-bodied. Hard structures provided protection, but also structural support. They allowed animals to grow larger, move faster, dig deeper. And crucially, they fossilized. Which is why the Cambrian fossil record is so much richer than anything before it. Not necessarily because life suddenly became more diverse, but because it became more preservable. From the Cambrian onward, evolution proceeded in recognizable patterns. Animals colonized the oceans, then the land. Plants followed, turning barren continents into forests. Insects evolved, then amphibians, then reptiles, then mammals and birds. Each group building on the innovations of the ones before. Each adapting to new environments, filling new niches. But here's the thing. Every step in this story, from the first self-replicating molecules to the Cambrian explosion, was contingent. Not inevitable. If any number of things had gone differently, life might not exist. Or it might exist in forms completely unrecognizable. The fact that we're here, examining our own origins, is the result of billions of years of accidents, near misses, and unlikely events. Earth could have stayed frozen during snowball Earth periods. Life might never have survived. The Great Oxidation event could have poisoned everything without any lineages adapting. Endosymbiosis might never have happened. Multicellularity might never have evolved. Any of these failures would have left Earth as a microbial planet indefinitely. Interesting, sure, but not capable of producing anything like us. Yet it didn't fail. Every bottleneck, every crisis, every random event lined up just right. Not because of destiny, just because of probability playing out over unimaginable timescales. Given enough planets, enough time, improbable things become statistically likely. We're the outcome of one very long, very unlikely chain of events. And that chain is still unfolding. The story of life on Earth isn't just about what survived. It's about what almost didn't. About 5 times in the past 540 million years, mass extinction events wiped out most species on the planet. Not small die-offs. Catastrophic collapses where 70 to 95% of all species disappeared. These weren't gradual declines. They were biological apocalypses that reset evolution and forced life to rebuild from whatever happened to make it through. The first major extinction happened at the end of the Ordovician period, about 445 million years ago. At the time, most life still lived in the oceans. Trilobites, brachiopods, early fish. The continents were barren rock. Then the climate destabilized. A rapid ice age locked up vast amounts of water as glaciers. Sea levels dropped dramatically. Shallow marine habitats, where most life existed, simply disappeared. Organisms adapted to warm, stable conditions suddenly faced freezing temperatures and habitat loss. About 85% of marine species went extinct. But here's what's interesting. The extinction happened in 2 pulses. First when the Ice Age began. Second when it ended and oceans warmed rapidly again. Life couldn't adapt to the cold. Then it couldn't adapt when things warmed back up. Whichever way the climate swung, something died. The survivors were generalists. Species that could tolerate wider ranges of temperature, salinity, oxygen levels. Specialists, finely tuned to specific conditions, were wiped out. This pattern repeats in every mass extinction. Adaptability beats optimization when the environment becomes unpredictable. The second major extinction came at the end of the Devonian period, around 375 million years ago. This one unfolded over several million years. Not a single catastrophic event, but a prolonged crisis. The leading hypothesis involves ocean anoxia. Large areas of the ocean losing oxygen. Fish, invertebrates, coral reefs, all suffocating. What caused the anoxia? Possibly massive algae blooms triggered by nutrient runoff from the newly forested continents. Plants had just colonized land. Their roots broke down rock, releasing nutrients into rivers that flowed into the ocean. too many nutrients caused explosive algae growth. When the algae died and decomposed, they consumed oxygen. The oceans became dead zones. About 75% of species disappeared. Reef ecosystems collapsed. Armored fish, which had dominated for millions of years, were devastated. Sharks, more adaptable, survived. This extinction reshaped marine life. It cleared space for new groups to evolve. But it took millions of years for biodiversity to recover. The third extinction is the big one. The Permian-Triassic event, 252 million years ago. The worst mass extinction in Earth's history. About 96% of marine species and 70% of terrestrial vertebrate species went extinct. Life came closer to complete annihilation than at any other time. The cause? Massive volcanic eruptions in what's now Siberia. Not a single volcano. An entire region erupting for hundreds of thousands of years. Lava flows covering an area larger than Europe. The eruptions released enormous amounts of carbon dioxide, sulfur dioxide, and other gases. Global temperatures spiked. Oceans acidified. Oxygen levels plummeted. On land, acid rain and greenhouse heating devastated ecosystems. In the oceans, warming and acidification killed off calcifying organisms. Coral reefs vanished. Food chains collapsed from the bottom up. Some researchers think the warming triggered the release of methane from ocean floor deposits. Methane is a far more potent greenhouse gas than CO2. If enough was released, it would have created a runaway warming effect. Temperatures potentially rose 10 degrees Celsius or more. The planet became a hothouse. Only the most resilient organisms survived. Small body size helped. Lower metabolic demands. Ability to hide underground or underwater. Generalist diets. Life that could eat almost anything had an advantage over specialists. The recovery took 10 million years. Longer than any other extinction. For millions of years after the Permian extinction, ecosystems remained impoverished. Low diversity. Simplified food webs. But eventually, life rebounded. And the groups that survived went on to dominate the Mesozoic. Including the archosaurs, the lineage that would produce dinosaurs. The fourth major extinction happened at the end of the Triassic period, about 201 million years ago. Another round of massive volcanism. This time in the central Atlantic, as the supercontinent Pangaea began to break apart. Rifting continents triggered volcanic eruptions that lasted for hundreds of thousands of years. Again, CO2 levels spiked. Oceans acidified. Temperatures soared. About 80% of species went extinct. But this extinction had an unusual outcome. It cleared the way for dinosaurs. Before the Triassic extinction, dinosaurs were relatively minor players. They existed, but so did many other reptile groups. Crocodile relatives, large amphibians, early mammal ancestors. All competing for the same resources. The extinction removed most of those competitors. Dinosaurs, for whatever reason, were better at surviving the crisis. Maybe their upright stance. Maybe their respiratory systems. Maybe just luck. But in the aftermath, they diversified rapidly and became the dominant land animals for the next 135 million years. Which brings us to the fifth extinction. The one everyone knows. The End Cretaceous event, 66 million years ago. The asteroid impact that killed the dinosaurs. This one was different. Not a slow burn like the others. Not volcanism or climate shifts playing out over millennia. This was sudden. Catastrophic. A 10-kilometer-wide asteroid slammed into what's now the Yucatan Peninsula at 20 kilometers per second. The impact released energy equivalent to billions of nuclear bombs. It vaporized rock. Triggered earthquakes. Generated tsunamis. Ignited global wildfires. But the real killer was the aftermath. The impact threw trillions of tons of dust and aerosols into the atmosphere. Sunlight was blocked. Photosynthesis stopped. Temperatures plummeted. Plants died. Herbivores starved. Carnivores followed. Within months, ecosystems collapsed. About 75% of all species went extinct, including all non-avian dinosaurs. Not because they were weak. Not because they were poorly adapted. But because the rules changed instantly and completely. No amount of evolutionary success mattered when the sun disappeared. The survivors were small, burrowing animals, scavengers, anything that could hide underground or underwater, anything with low energy requirements. Birds made it through, though most species didn't. Mammals survived, but only the small ones. Crocodiles and turtles, with slow metabolisms, endured. In the aftermath, the planet was dark, cold, and nearly lifeless for years. Then, slowly, life returned. Plants regrow from seeds and roots. Survivors emerged and began to spread. Ecological niches, empty for the first time in millions of years, were filled by whatever happened to be around. Mammals, previously limited to small nocturnal roles, suddenly had opportunities. No more dinosaurs to compete with. No more giant predators. Within 10 million years, mammals had diversified into dozens of new forms. Browsers, grazers, predators, climbers, swimmers. The age of mammals had begun. Not because mammals were superior, but because dinosaurs were gone. Each of these 5 mass extinctions reset the clock. They didn't erase life, but they reorganized it. Groups that had dominated for millions of years vanished. New groups, previously marginal, took over. Evolution doesn't have a direction. It doesn't move toward complexity or intelligence. It just responds to whatever pressures exist at the time. And when those pressures are catastrophic, the response is equally extreme. Survival in a mass extinction isn't about being the best. It's about being lucky enough to have the right traits at the right moment. Small size when food is scarce. Generalist diet when ecosystems collapse. Burrowing behavior when the surface becomes uninhabitable. These aren't strengths in normal times. They're insurance policies for disasters. And here's the uncomfortable part. We're living in the 6th mass extinction right now. Species are disappearing at rates comparable to the Big Five. Not from asteroid impacts or volcanic eruptions. From us. Habitat destruction. Climate change. Overhunting. Pollution. We're not just witnesses to extinction. We're the cause. And unlike previous extinctions, this one is happening in real time. Fast enough to observe. Fast enough to measure. But possibly too fast to stop. The difference is, we know it's happening. We can see the patterns. We understand the mechanisms. Previous mass extinctions were blind cosmic accidents. This one is optional. Which makes it either more tragic or more hopeful, depending on what we do next. The question isn't whether Earth will survive. It will. Life has endured worse. The question is what form that life will take. Whether we'll be part of it. And what we're willing to do to change the trajectory. Earth's history isn't just a record of extinctions. It's a record of recoveries. And those recoveries follow patterns. Predictable, repeatable patterns that play out over millions of years. Understanding them reveals something crucial about how life actually works when everything falls apart. After each mass extinction, the planet enters what scientists call a dead zone. Not literally dead, but functionally empty. Food webs are shattered. Ecosystems lack structure. Energy flows are disrupted. The survivors exist, but they're not thriving. They're just hanging on in a world that doesn't work properly yet. This phase lasts anywhere from hundreds of thousands to millions of years. During this time, diversity remains low. A few generalist species spread widely, filling multiple roles because specialists haven't evolved yet. Think of it as ecological simplicity. Not because life can't be complex, but because complexity requires time to build. Then something shifts. Resources accumulate. Populations grow. Competition increases. And suddenly, evolution accelerates. New species branch off. Specialists emerge. Food webs gain layers. This is the recovery phase, where diversity explodes and ecosystems regain their structure. But here's what matters. The new ecosystems don't look like the old ones. They're built from different parts. Organized around different principles. dominated by different groups. Recovery doesn't mean restoration. It means reinvention. After the end Permian extinction, the worst in Earth's history, recovery took roughly 10 million years. Longer than any other mass extinction. Why? Because the damage was deeper. Ocean chemistry was disrupted. Carbon cycles were broken. Climate remained unstable for millions of years. Life had to wait for the planet itself to stabilize before it could rebuild. The Triassic period that followed looked nothing like the Permian. Synapsids, which had dominated before, were reduced to minor roles. Reptiles, particularly archosaurs, took over. These were the ancestors of dinosaurs and crocodiles. They succeeded not because they were superior, but because they happened to have traits that worked in new conditions. After the end Cretaceous extinction that killed the dinosaurs, recovery was faster. About 2 to 3 million years before ecosystems regained complexity. Why quicker this time? The planet wasn't as severely damaged. Ocean chemistry recovered faster. Climate stabilized sooner. And crucially, more lineages survived, providing more raw material for evolution to work with. Mammals filled the empty niches left by dinosaurs. But they didn't just become small versions of what came before. They evolved entirely new body plans. New feeding strategies. New ways of moving and reproducing and interacting. Within 10 million years, mammals had diversified into forms ranging from tiny shrews to early whales. This reveals a fundamental truth about evolution. It's not progressive. It doesn't aim toward improvement. It's opportunistic. Whatever works in the current environment spreads. Whatever doesn't, disappears. The best organism is simply the one that survives long enough to reproduce. And survival depends heavily on luck. Being in the right place when disaster strikes. Having the right traits when conditions change. Being part of a lineage that happens to persist. Intelligence doesn't guarantee survival. Size doesn't. Strength doesn't. Adaptation to current conditions definitely doesn't, because those conditions can change overnight. This is why predicting recovery is so difficult. We can identify general patterns, but the specifics depend on which groups survive and what opportunities they find. After the dinosaurs, it could have been something other than mammals. If a few key lineages had gone extinct, Earth's history would look completely different. Now consider our current situation. We're in the early stages of a mass extinction. Species are vanishing rapidly. Ecosystems are degrading. But we're not yet in the dead zone. That comes later, if current trends continue. Which means we're at a decision point. We can still influence the outcome. What would recovery look like after a human-caused mass extinction? Hard to say. It depends on what survives. If large mammals disappear, something else will eventually fill those roles. Maybe birds. Maybe reptiles. Maybe something unexpected. Evolution doesn't care about our preferences. If humans disappeared tomorrow, Earth would recover. It might take millions of years, but diversity would return. New species would evolve. Ecosystems would rebuild. The planet has done this before, multiple times. It's resilient in ways that individual species aren't. But that's not a comforting thought. Because from our perspective, recovery after our extinction wouldn't include us. We'd be a thin layer in the fossil record. Evidence of a species that emerged, dominated briefly, then vanished. Just like the dinosaurs. Just like the trilobites. Just like thousands of other lineages that once seemed permanent. The real question isn't whether Earth will recover. It's whether we want to be part of that recovery. Whether we're willing to change our behavior to remain part of the story. Because unlike previous mass extinctions, this one comes with awareness. We understand what's happening. We can measure it. We can model future scenarios. We have knowledge that no species has ever possessed before. That knowledge creates responsibility. Not moral responsibility in some abstract sense, but practical responsibility. We're causing changes that will determine which species persist and which don't. Including possibly our own. And unlike an asteroid impact, these changes are gradual enough that we can respond. If we choose to. But here's the hard part. Responding effectively requires acting against immediate self-interest. Preserving habitat means not developing land. Reducing emissions means changing energy systems. Limiting consumption means accepting less material wealth. These aren't easy choices. They're not even obviously rational from an individual perspective. Yet they're necessary from a species perspective. From an ecosystem perspective. From a long-term survival perspective. The same perspective that matters when you're looking at geological timescales and extinction patterns. Because on those timescales, short-term gains vanish. Only persistence matters. Only what survives long enough to leave descendants. This is where human intelligence becomes either our greatest asset or our fatal flaw. We can understand long-term consequences in ways other species can't. We can plan beyond our own lifetimes. We can coordinate globally. But we can also rationalize inaction. Prioritize immediate comfort. Assume someone else will solve the problem. Other species don't face this dilemma. They can't choose to prevent extinction. They simply respond to immediate pressures, and either their traits work or they don't. Humans are the first species capable of consciously deciding whether to alter our trajectory. Whether to use our intelligence to ensure our persistence. The fossil record shows that dominance is temporary. Every group that once ruled eventually declined. Trilobites dominated for 270 million years, then vanished. Dinosaurs lasted 165 million years, then disappeared. Humans have existed for maybe 300,000 years. We've been technologically advanced for less than 10,000. We're newcomers. And newcomers don't have track records of stability. What we do have is unprecedented power. Power to reshape ecosystems. Power to drive climate change. Power to cause extinctions at rates comparable to asteroid impacts. That power doesn't make us immune to extinction. It makes us capable of causing our own. The patterns from previous mass extinctions suggest what might happen next. If we continue current trends, diversity will decline. Ecosystems will simplify. Specialist species will disappear first. Then larger species. Then anything requiring stable conditions. Eventually, we reach a threshold where ecosystems can't provide the services we depend on. Clean water. Stable climate. Pollination. Soil formation. Food production. At that point, human civilization becomes unsustainable. Not because we lack technology, but because the biological foundation collapses. We can't engineer our way out of ecosystem failure. We depend on functional ecosystems the same way every other species does. Remove enough pieces, and the whole structure falls apart. This isn't speculation. It's pattern recognition. Every mass extinction followed similar trajectories. Stress accumulates. Systems become fragile. A final trigger causes collapse. The only difference now is we can see it coming. We have data. Models. Projections. We know which actions accelerate the problem and which might slow it. Whether we act on that knowledge determines what the next few million years look like. Whether the Anthropocene becomes a brief anomaly or a major extinction event. Whether humans persist or become another fossil layer. Whether intelligence, our defining trait, proves adaptive or maladaptive on evolutionary timescales. The answer isn't predetermined. Evolution doesn't script outcomes. It responds to conditions. And conditions, for the first time in Earth's history, are partially under the control of one species. That's never happened before. We don't have precedent for a species consciously shaping its own evolutionary future. Which makes this moment unique. Not just in human history, but in planetary history. We're the first species capable of understanding mass extinctions while potentially causing one. The first that can choose whether to continue down that path. The first with enough knowledge to know better and enough power to do something about it. What we do next matters. Not because the universe cares. Not because Earth cares. But because we care. Because we're capable of caring about things beyond our immediate survival. About other species. About future generations. About whether the story continues or ends with us. That capacity for long-term thinking is either our salvation or our epitaph. And we're in the process of finding out which. Looking back at the fossil record reveals something unsettling. Intelligence rarely appears as a survival trait. Most successful lineages, the ones lasting tens or hundreds of millions of years, rely on simplicity. Bacteria, jellyfish, crocodiles. They don't solve problems. They persist through durability. Intelligence is expensive. It requires large brains, extended development periods, high energy intake. For most of Earth's history, those costs outweighed the benefits. Only in specific circumstances, environments demanding flexibility and learning, did intelligence become advantageous. And even then, it remained rare. Out of billions of species across 4 billion years, only one developed technology. That's not a sign of inevitability. It's statistical noise. Which raises a question. If intelligence is so rare and so costly, what happens when it creates problems faster than it solves them? When the very trait that enabled survival becomes the mechanism of decline? We're testing that now. Human intelligence produced agriculture, medicine, technology. It extended lifespans, reduced infant mortality, enabled population growth beyond any precedent. But it also produced weapons capable of ending civilization in hours. Pollution that persists for millennia. Climate disruption that compounds across decades. We're intelligent enough to create these problems. Whether we're intelligent enough to solve them remains unproven. And the clock is running. Not in human time, where decades feel long. In geological time, where our entire civilization is a blink. If we disappeared tomorrow, future geologists would find a thin layer marking our existence. Plastics. Concrete. Radioisotopes. A brief spike in carbon isotopes. Then silence. The planet would continue. Life would recover. It always does. Not the same life, not the same ecosystems, but something. Earth doesn't need humans. We need Earth. That asymmetry matters. We talk about saving the planet, but that's backwards. The planet will be fine. It survived 5 mass extinctions, supervolcano eruptions, asteroid impacts, ice ages, hothouse climates. It'll survive us. What we're actually trying to save is ourselves. Our way of life. The stable conditions we evolved to exploit. Those conditions aren't guaranteed. They're contingent on systems we're actively destabilizing. And once those systems cross certain thresholds, they don't snap back. They reorganize around new equilibria. Equilibria that might not include industrial civilization, or large human populations, or humans at all. That possibility should focus attention. Because unlike previous species facing extinction, we can see it coming. We have data showing ocean acidification rates, temperature projections, biodiversity decline curves, ecosystem collapse timelines. We know where current trajectories lead. And yet, knowing doesn't guarantee action. Information alone never changes behavior. If it did, everyone would exercise, save money, avoid processed food. But knowing what's good for us and doing it are different things. The gap between knowledge and action defines the human condition. And right now, that gap is widening. We know fossil fuels drive climate change. We keep burning them. We know industrial agriculture depletes soil. We keep expanding it. We know overfishing collapses stocks. We keep fishing. Not because we're stupid. Because short-term incentives override long-term consequences. Because individual rationality produces collective irrationality. Because the benefits of harmful actions accrue to individuals while the costs distribute across everyone. That's not a moral failing. It's a structural problem. And structural problems require structural solutions. Individual action matters, but it's insufficient. Recycling, reducing consumption, changing diet, all positive steps. But they don't address the underlying systems driving ecosystem collapse. Those systems, energy infrastructure, agricultural practices, economic incentives, require coordinated policy changes. Which requires political will. Which requires public pressure. Which requires enough people caring enough to demand change. And that's where we are. In a narrow window where the trajectory is set but not locked. Where the momentum is strong but not irreversible. Where outcomes remain uncertain because they depend on choices not yet made. This moment won't last. Windows close. Systems reach tipping points. Momentum becomes irreversible. The question is whether we recognize the moment while we're in it. Whether we understand that what feels like normal is actually unprecedented. That the stability we take for granted is historically anomalous. That the future isn't guaranteed to resemble the past. Because it won't. The planet we're creating will be fundamentally different from the one we inherited. Hotter. Less biodiverse. Less stable. Whether it remains habitable for billions of humans depends entirely on how much hotter, how much less diverse, how much less stable. Those aren't abstract variables. They're outcomes of specific decisions. Energy policy. Land use. Consumption patterns. Trade agreements. Infrastructure investments. Decisions being made now, today, by governments, corporations, individuals. Each decision moves the needle. Slightly. Incrementally. But cumulatively, they determine trajectory. And trajectory determines destination. We like to think we're separate from nature. That technology insulates us from ecological limits. That intelligence exempts us from evolutionary pressures. But we're not separate. We're embedded. We breathe the same air. Drink the same water. Depend on the same ecosystem services as every other organism. Our cities, our technology, our entire civilization rests on a foundation of functional ecosystems. Remove that foundation and everything collapses. Not might collapse. Will collapse. It's physics. You can't support a structure after removing its base. And we're systematically removing the base. Deforestation. Ocean acidification. Soil depletion. Aquifer exhaustion. Pollinator decline. Each one weakens the foundation. Each one moves us closer to structural failure. We're not facing one problem. We're facing interconnected system failures happening simultaneously. Climate change amplifies species extinction. Species extinction reduces ecosystem resilience. Reduced resilience accelerates climate impacts. Feedback loops compound. Tipping points cascade. And suddenly, gradual change becomes rapid collapse. That's how complex systems fail. Slowly, then all at once. The challenge is acting during the slow phase. When problems seem manageable. When denial remains plausible. When short-term costs feel more real than long-term consequences. Acting requires overriding our evolutionary programming. We evolved for immediate threats. Predators. Starvation. Injury. Our brains are wired for rapid response to visible danger. But climate change isn't a predator. It's a statistical shift. A gradual accumulation. A probability distribution changing shape. Our brains aren't built to process that. We don't feel threatened by parts per million. By decimal point temperature increases. By percentage changes in biodiversity. We feel threatened by things with teeth. By things that can hurt us now. Which is why this is hard. Why knowing isn't enough. Why information doesn't automatically translate to action. We're asking people to respond emotionally to spreadsheets. To feel urgency about graphs. To sacrifice immediate comfort for abstract future benefits. That's not how humans work. But it's what the situation requires. Which means we need to change how we work. Not our biology, that's too slow. But our systems. Our institutions. Our decision-making frameworks. We need structures that account for long-term consequences. That price in externalities. That prioritize sustainability over quarterly profits. That value ecosystem health over GDP growth. Those structures don't exist by default. They require intentional design. Political will. Social pressure. Cultural shifts. They require enough people demanding something different. Enough people recognizing that current systems are driving us toward collapse. Enough people willing to support changes that might be personally inconvenient but collectively necessary. And that's the real test. Not whether we can develop solutions. We have solutions. Renewable energy. regenerative agriculture, circular economies, ecosystem restoration. The technology exists. The knowledge exists. What's missing is implementation at scale. What's missing is political and economic systems that prioritize long-term survival over short-term extraction. What's missing is collective willingness to accept that infinite growth on a finite planet is mathematically impossible. That's the hard part. Not the science. Not the engineering. The acceptance that our current trajectory is unsustainable. That something has to change. That we can't keep doing what we're doing and expect different results. And we're running out of time to figure this out. Not in a dramatic, countdown clock way, but in the sense that every year of delay makes the problem harder. Every ton of carbon emitted stays in the atmosphere for decades. Every species lost is gone permanently. Every ecosystem threshold crossed is effectively irreversible on human timescales. We're making decisions now that will echo for thousands of years. Decisions about what kind of planet we leave behind. What kind of future we're creating. Whether intelligence, our defining characteristic, proves adaptive or catastrophic. The answer isn't written yet. We're writing it. Right now. Through choices large and small. Through policies and purchases. Through what we demand and what we accept. Through whether we treat this as an emergency or a distant concern. Evolution doesn't care which we choose. It'll respond to whatever conditions we create. It'll favor whatever traits prove adaptive in the world we're building. Maybe that world includes humans. Maybe it doesn't. Maybe intelligence remains advantageous. Maybe it becomes a liability. Maybe we're the ancestors of something extraordinary. Maybe we're just another failed experiment. Another branch that couldn't adapt fast enough. Another fossil layer marking a brief moment when one species thought it could outsmart 4 billion years of planetary processes. We won't know the answer for millions of years. But we're determining it now. Part 6 of 6. The story we've been told about comets, the one where they're just icy debris wandering through space, needs updating. Because the data keeps pointing in one direction. These objects aren't random. They're delivery systems. Packages sent from the outer solar system carrying exactly what early Earth needed but couldn't make efficiently on its own. Think about the timing. Earth forms hot. Too hot for organic chemistry. It needs to cool, needs water, needs the building blocks for biochemistry. And right on schedule, here come the comets. Billions of them during the late heavy bombardment. Each one carrying ice, organics, amino acids, phosphorus. Each impact a delivery. Not violent destruction, but violent creation. We've spent decades assuming life started here through local chemistry. Lightning strikes. Volcanic vents. Tidal pools. And maybe some of it did. But the numbers don't work. Early Earth's atmosphere wasn't right for making complex organics in quantity. The Miller-Urey experiment, elegant as it was, used the wrong gases. When you correct for that, the yield drops dramatically. Local production wasn't enough. But comets? They're making organics constantly. In the cold dark between stars. No atmosphere to worry about. No oxygen to interfere. Just carbon, hydrogen, nitrogen, oxygen, and time. Lots of time. These molecules form, accumulate, get locked into ice matrices that protect them. Then they wait. Sometimes for billions of years. Until gravity pulls them inward. Until they slam into young planets. Until they deliver their cargo. What we found on Wild 2 and 67P isn't an accident. It's a pattern. Comets everywhere are doing this. Making the same molecules. Carrying the same building blocks. It's chemistry operating at solar system scale. And Earth was in the path of that delivery route for hundreds of millions of years. The ice itself mattered just as much as what was in it. Early Earth needed water. Vast amounts. Our oceans didn't condense from the primordial atmosphere. They came from outside. From objects that formed in colder regions and then migrated inward. Some from asteroids, yes. But comets contributed. Isotope ratios prove it. Not all our water is cometary, but some is. Enough to matter. So now picture the actual scenario. 4 billion years ago. Earth with thin oceans, no continents yet, active volcanism everywhere. And it's being bombarded constantly. Not planet-killing impacts, but steady, relentless delivery. Each comet brings water, organics, minerals. The ice cushions the impact, protects the cargo. The organics survive, dissolve into the ocean, accumulate. The minerals settle. The carbon compounds concentrate in tidal zones, around vents, in shallow pools. You're not starting with nothing. You're starting with a planet being continuously restocked with prebiotic chemistry. With molecules that already have some complexity. With building blocks ready to assemble into something more sophisticated. The local chemistry, the lightning and vents and UV radiation, they're still happening. But now they're working with better raw materials. They're not creating from scratch. They're refining what's already there. And here's what makes this profound. It means life's origin isn't purely local. It's not Earth solving the problem alone. It's Earth benefiting from processes that happened across the entire solar system. From chemistry in molecular clouds. From reactions in the outer solar system. From delivery mechanisms that operated for hundreds of millions of years. Life's origin is a collaboration between a planet and its cosmic environment. Which raises an obvious question. If this happened here, did it happen elsewhere? Are there other planets, right now, being seeded by comets? Other oceans accumulating organic molecules. Other worlds where chemistry is transitioning toward biology. We don't know. But the statistics suggest yes. Our solar system isn't unique. Comets form around other stars. Planets get bombarded everywhere. The same physical processes, the same chemistry, the same delivery mechanisms. If it worked once, it can work again. Maybe it's working right now on planets we haven't discovered yet. Maybe it's worked countless times on worlds that existed billions of years ago. Maybe we're not the first. Maybe we won't be the last. That doesn't make life inevitable. Chemistry alone doesn't guarantee biology. You need the right conditions, the right timing, the right sequence of events. But it makes life less miraculous, less impossibly unlikely. It shifts the question from, how did life beat astronomical odds? To, given favorable conditions and enough time, how often does chemistry become biology? And that's a different question. One with potentially different answers. Because chemistry is patient. It doesn't care about timescales. It just keeps trying combinations. Keep mixing molecules for 1 billion years and eventually something interesting happens. Not guaranteed, but probable. And probability, given enough opportunities, approaches certainty. We're still missing pieces. We don't know exactly how RNA formed, how membranes and replication combined, how the genetic code got established. Those are hard problems, but they're becoming tractable. Every year, lab experiments get closer to recreating conditions that produce self-replicating systems. Every year, we understand more about what early Earth was actually like. Every year, the gap between non-life and life gets smaller. Comets didn't solve the origin of life. They solved the supply problem. They provided raw materials that early Earth couldn't efficiently produce. They turned an improbable event into something merely unlikely. And on planetary timescales, unlikely events happen constantly. You just need to wait. The evidence keeps accumulating. Not just from comets we've visited, but from meteorites, from interstellar chemistry, from laboratory experiments. All of it pointing toward the same conclusion. The building blocks of life aren't rare. They're common. They form naturally in cold environments. They survive delivery to planetary surfaces. They accumulate. They react. They experiment. What's rare isn't the chemistry. It's the conditions that let chemistry become biology. Stable liquid water. Energy sources. Mineral surfaces for catalysis. Protection from radiation. Enough time without catastrophic disruption. Those conditions are specific. Not impossible, but requiring a particular combination of planetary characteristics. Earth had those characteristics. Maybe other planets do too. Maybe they're common. Maybe they're rare. We're only beginning to survey the possibilities. Only beginning to understand how many Earth-like worlds exist. Only beginning to look for biosignatures, chemical signs that biology is happening somewhere else. The search is underway. Telescopes scanning exoplanet atmospheres for oxygen, methane, combinations that suggest life. Probes examining Europa and Enceladus, moons with subsurface oceans that might harbor biology. Future missions to Venus, Mars, Titan, looking for current life or fossil evidence of past life. Each mission refines our understanding. Each discovery adjusts the probabilities. And those probabilities matter, because they determine whether we're alone or part of something larger. Whether life's origin was a singular miracle or a common occurrence. Whether intelligence is unique to Earth or inevitable given enough time. Whether we're the only species capable of asking these questions or one of many scattered across the galaxy. We don't have those answers yet. But we're closer than we've ever been. Closer to understanding our origins. Closer to knowing whether life elsewhere exists. Closer to determining our place in the universe. Not through philosophy or speculation, but through data. Through chemistry. Through missions that touch these ancient objects and read their composition. Comets are messengers. Not from gods or fate, but from the early solar system. They carry information about conditions 4.5 billion years ago. About chemistry in the outer regions. About what was available when Earth formed. That information is still readable, still preserved in ice that hasn't melted since the solar system's beginning. Every comet we study refines the picture. Every measurement adds detail. Every discovery adjusts our understanding. We're not guessing anymore about what these objects contain. We're measuring it directly. And what we're measuring consistently shows organic complexity. Amino acids. Nucleobases. Phosphorus. Water. Everything life needs. That doesn't prove comets created life. Proof would require showing the mechanism, demonstrating that delivered organics actually assembled into something living. We can't do that. We weren't there. We don't have recordings. We have only evidence, circumstantial but compelling, pointing toward cometary delivery as a crucial part of life's origin. The alternative is that all of this is coincidence. That comets happen to carry exactly the molecules life uses, but contributed nothing. That early Earth independently synthesized everything despite having the wrong atmospheric chemistry. That the timing of heavy bombardment and life's appearance is unrelated. Possible, but increasingly implausible. Science works by eliminating alternatives until only one explanation fits the data. We're not there yet. But we're moving in that direction. Each study, each mission, each experiment narrows the possibilities. And what's emerging is a story where life's origin wasn't purely terrestrial. Where Earth's chemistry was supplemented by cosmic delivery. Where our existence depended on objects formed in a cold dark carrying cargo across billions of kilometers. It's a strange story. not the one we expected. But data doesn't care about expectations. It cares about what actually happened. And what appears to have happened is that life's ingredients came from space. Not all of them, but enough to matter. Enough to tip the balance from impossible to merely improbable. Enough to give chemistry the raw materials it needed to begin experimenting with biology. We're the result of that experiment. Not the only possible result, but one that worked. One that survived. One that eventually became capable of looking back and asking where it came from. And now we have an answer, partial but growing more complete. We came from Earth, yes. But Earth came from the solar system. And the solar system provided, through comets, the chemical foundation that made us possible. That foundation is still out there. Still orbiting. Still carrying the same molecules. Still waiting to be studied. Each comet is a time capsule from the solar system's formation. Each one holds clues about conditions back then. About chemistry. About the processes that led to us. We've only examined a handful. Thousands more are accessible. Each one potentially holding new information, new insights, new pieces of the puzzle. The work continues. Missions are being planned to return samples from comets. To land on their surfaces. To drill into their cores and retrieve pristine material that's been frozen since the beginning. Each sample will be analyzed in laboratories with instruments far more sensitive than what existed even a decade ago. Each analysis will reveal more about what comets contain and how those contents relate to biology. We're at the beginning of understanding this connection, not the end. The evidence so far is suggestive, compelling, but incomplete. We need more data, more samples, more experiments, more missions. The story of how comets contributed to life's origin is still being written. But the outline is visible. The general shape is clear. And it's changing how we think about our place in the universe. Because if comets seeded Earth, they're seeding other planets too. If organic delivery is common, then the building blocks of life are widespread. If chemistry can transition to biology given the right conditions, then those conditions might exist elsewhere. The universe might be full of experiments similar to the one that produced us. Some failing, some succeeding, some just beginning, some already billions of years old. We don't know yet, but we're looking. And every year, our tools get better. Our understanding deepens. Our search expands. The question of whether we're alone is becoming answerable. Not through speculation, but through observation. Through detecting biosignatures on distant worlds. Through finding life in our own solar system beyond Earth. Through understanding how common the processes that created us actually are. That understanding starts with comets. With these frozen archives carrying evidence from our beginning. With missions that brave enough to catch up to them, touch them, taste their chemistry. With scientists patient enough to analyze the data, piece together the story, follow wherever the evidence leads. And where it's leading is toward a cosmos more interconnected than we imagined. Where life's origin isn't isolated to individual planets, but involves solar system-wide processes. where chemistry in one region affects biology in another, where what happens in the cold outer darkness eventually influences what emerges in the warm inner light. We're part of that story. Products of processes that began before Earth existed. Beneficiaries of delivery systems that operated for hundreds of millions of years. Descendants of chemistry that started in molecular clouds and ended in living cells. The path from there to here was long, improbable, contingent on countless specific events. But it happened. And understanding how it happened changes everything about how we see ourselves and our origins. A telescope floating 1 million miles from Earth just detected something that shouldn't exist. 2 chemicals in the atmosphere of a distant planet, chemicals that on Earth are produced exclusively by living organisms. This isn't speculation or wishful thinking. It's data from the most powerful observatory humanity has ever built, pointing at a world 124 light-years away where something might be alive right now. The planet is called K2-18b. You've never heard of it, but scientists have been watching it obsessively since the James Webb Space Telescope turned its instruments toward this particular corner of the constellation Leo. What they found there has divided the scientific community into camps of cautious optimism and aggressive skepticism, because the implications are staggering. We might be looking at the first real evidence of life beyond Earth. Here's what makes this so compelling. The chemicals detected, dimethyl sulfide and dimethyl disulfide, don't just sometimes get produced by life on Earth. They're made almost exclusively by microscopic marine organisms like phytoplankton and algae. These aren't gases that form easily through random chemistry. They require specific biological processes, the kind that happen when living cells metabolize sulfur compounds in ocean water. Finding them in another planet's atmosphere is like walking into an empty house and smelling fresh coffee. Something made that. But let's pump the brakes for a second, because this story is way more complicated than the headlines suggest. K2-18b sits in what astronomers call the habitable zone of its star, a red dwarf much smaller and cooler than our Sun. The planet orbits this star every 33 days, receiving roughly the same amount of light Earth gets from the Sun. It's massive compared to our world, about 8.6 times Earth's mass and 2.6 times larger in diameter. That makes it what scientists call a sub-Neptune, somewhere between Earth and the ice giants in our own solar system. The distance? 124 light-years. That means the light the Webb telescope is analyzing left that planet during the late 1800s on Earth. We're looking at old light, ancient photons that traveled through space for more than a century before hitting Webb's mirrors and revealing their secrets. What makes K2-18b particularly interesting is that it might be what's called a Hycean world. The term was coined in 2021, a mashup of hydrogen and ocean, describing planets that weren't supposed to be habitable but might actually be perfect for life. These are worlds covered in deep oceans, potentially hundreds or even 1,000 kilometers deep in some places, with thick hydrogen-rich atmospheres above them. Before the concept of Hycean planets, scientists assumed hydrogen atmospheres would make worlds too hot for life. K2-18b is forcing a rethink of that assumption. The detection itself happened through a method called transit spectroscopy. When K2-18b passes in front of its star from our perspective, starlight filters through the planet's atmosphere before reaching us. Different molecules absorb specific wavelengths of light, creating a kind of chemical fingerprint. Webb's instruments are so sensitive they can detect these tiny variations in brightness and identify what gases are present millions of miles away. In 2023, the telescope detected methane and carbon dioxide in K2-18b's atmosphere. That was already significant, the first time such carbon-based molecules were spotted on an exoplanet in a habitable zone. But there was something else in the data, a weak signal that looked like it might be dimethyl sulfide. So the research team, led by scientists from the University of Cambridge, pointed Webb back at the planet using a different instrument, the mid-infrared instrument, designed to detect different wavelengths of light. What they found was stronger evidence for both dimethyl sulfide and dimethyl disulfide. The concentrations are wild compared to Earth. On our planet, these chemicals exist at levels below 1 part per billion in the atmosphere. On K2-18b, the estimated concentrations are over 10 parts per million. That's thousands of times stronger. If these readings are accurate, something is pumping these gases into that atmosphere at an extraordinary rate. On Earth, the process works like this. Marine phytoplankton, particularly dinoflagellates and coccolithophores, produce a compound called DMSP as part of their cellular processes. When these organisms die or get eaten, or when viruses attack them, DMSP breaks down into dimethyl sulfide. It's a complex chain involving bacteria, enzymes, and photochemical reactions. The DMS then escapes into the atmosphere where it plays a role in cloud formation and the planet's sulfur cycle. It's a signature of biological activity in ocean ecosystems. Finding it on another world should mean something similar is happening there. Should. That's where the controversy explodes. The statistical confidence level of this detection sits at 3 sigma. In scientific terms, that means there's a 0.3% chance the signal is just random noise, a fluke in the data. Sounds pretty good, right? Except the gold standard for scientific discovery is 5 sigma, which represents a probability of less than 0.00006% that the result is random. The difference between 3 sigma and 5 sigma is the difference between interesting and definitive. The research team knows this. They've been careful not to claim they've discovered life. What they're saying is that the data they have is consistent with the presence of these biosignature molecules, and that more observations are needed. They estimate another 16 to 24 hours of observation time with Webb could push them to that 5 sigma threshold. But here's where it gets messy. Other scientists have analyzed the same data and reached different conclusions. Some argue that the DMS signal isn't actually there at all, that it overlaps too much with methane signals and the analysis methods aren't robust enough to separate them. The data, they say, is consistent with a flat line, no bump or wiggle indicating a real detection. It's a classic case of seeing what you want to see in noisy data. Then there's the magma planet hypothesis. Some researchers think K2-18b isn't a water world at all, but a hellscape with oceans of molten rock instead of liquid water. Raymond Peary-Humbert, a planetary physicist at Oxford, has run models suggesting the planet is too hot for life, that any water present would be superheated and the surface would be volcanic. If that's true, the entire Hycean world concept for K2-18b collapses. There's also the non-biological production problem. DMS has been detected on comets and in interstellar space, proving it can form without life through purely chemical processes we don't fully understand. Just because we only know biological sources on Earth doesn't mean that's the only way it forms in the universe. The cosmos is creative with chemistry in ways we're still discovering. The debate reveals something fundamental about where we are in the search for extraterrestrial life. The James Webb Space Telescope has given us capabilities we've never had before. In just a few years of operation, we've learned more about exoplanet atmospheres than in the previous 3 decades combined. But we're operating at the absolute edge of what's possible with current technology. We're trying to detect faint signals from small planets incredibly far away, and interpretation of that data requires making assumptions about alien environments we can't directly observe. This is the paradox. We finally have tools powerful enough to potentially detect life on other worlds, but we might not have tools precise enough to prove it definitively. Webb might identify the most promising candidates, the worlds worth watching more closely, but confirming life could require the next generation of telescopes that haven't been built yet. What we do know is this: K2-18b is real. It's sitting in its star's habitable zone. It has an atmosphere with carbon-based molecules. The chemistry is complex and active. Whether that chemistry includes life remains an open question, one that's driving some of the most heated scientific debates happening right now. The lead researcher, Niku Midhusudhan from Cambridge, has said that the only scenario currently explaining all the Webb data, past and present, is one where K2-18b is a Hycean world teeming with life. But he's also emphasized the need for deep skepticism, for testing and retesting, because that's how science works. No one wants to claim prematurely that we found alien life. What kind of life are we talking about if it exists? Not little green men or intelligent civilizations. The conditions on K2-18b, assuming it's habitable at all, would support microbial life at best. Think of Earth's oceans billions of years ago, filled with single-celled organisms producing gases as metabolic waste. That's the kind of biology we might be detecting, primitive but profound. The hydrogen-rich atmosphere adds another layer of complexity. Laboratory experiments show that Earth microorganisms can survive in hydrogen atmospheres, so hydrogen itself isn't a deal-breaker for life. But it changes which biosignature gases are reliable indicators. Some gases that scream life on Earth might form through non-biological processes in hydrogen-rich environments, making interpretation even trickier. The temperature is estimated between 250 and 300 Kelvin in the absence of greenhouse effects. That's cold, but not impossibly so. With the right atmospheric composition and pressure, liquid water could exist. The deeper layers of the atmosphere might be too hot, crushing, but there could be a zone, a sweet spot where conditions align. Ocean depths on Hycean worlds are staggering to contemplate. Depending on surface gravity and temperature, these oceans could extend tens to hundreds of kilometers deep, reaching pressures of 60,000 bar before the water transitions to high-pressure ice. That's an alien environment by any measure, but Earth's deep oceans host life in equally extreme conditions. Hydrothermal vents, crushing pressure, total darkness, yet life thrives. If K2-18b is producing dimethyl sulfide biologically, the implications extend far beyond one planet. Hycean worlds are thought to be common around red dwarf stars, the most numerous stars in the galaxy. Their larger sizes compared to rocky planets make them easier to observe and analyze. If these worlds can host life, the number of potentially habitable planets in the universe explodes. But we're getting ahead of ourselves. The data is preliminary, contested, requiring confirmation. The scientific process is working exactly as it should, with competing teams analyzing the same information and reaching different conclusions. That tension, that back and forth, is how we eventually arrive at truth. What happens next matters enormously. The full dataset became publicly available in late April, meaning more astronomers can now scrutinize every detail. Additional observation time with Webb has been requested. Other instruments on other telescopes might be able to contribute complementary data. The investigation is just beginning. Standing at this moment in history feels significant regardless of what we ultimately discover about K2-18b. We're asking questions about alien life not through speculation but through direct observation of another world's chemistry. We're analyzing gases in an atmosphere 124 light-years away and debating whether they come from living organisms. That alone represents a milestone. The search for life beyond Earth has entered a fundamentally new phase, one where we're no longer limited to searching for radio signals or planning distant missions to Mars. We're using infrared telescopes to sniff the air of alien worlds, looking for the chemical exhaust of biology. What we're learning is that the universe is far more complex than our models predicted, that every new observation raises new questions, and that the answer to whether we're alone might be closer than we ever imagined. But first, we need to understand what we're actually looking at. The challenge lies in how we actually detect these molecules from such an enormous distance. Light becomes the messenger. When K2-18b passes between its star and Webb's instruments, starlight filters through the planet's atmosphere. Different molecules absorb specific wavelengths, creating a unique spectral fingerprint. Each molecule has its own signature pattern, a barcode written in missing wavelengths. Webb's mid-infrared instrument was specifically designed to read these barcodes. The telescope doesn't see K2-18b directly. What it captures is the star's light after it's been altered by passing through alien air. The brightness drops slightly during transit, and that drop varies by wavelength depending on what's in the atmosphere. Methane absorbs certain infrared wavelengths. Carbon dioxide takes others. And dimethyl sulfide, if it's there, should create its own distinctive absorption pattern. The problem is that these signals are incredibly faint. We're talking about detecting changes in brightness of less than 1%, and then within that tiny signal, finding even smaller variations that indicate specific molecules. It's like trying to identify a single instrument in an orchestra from a mile away while standing next to a jet engine. The initial detection of dimethyl sulfide came from analyzing how starlight was absorbed at specific infrared wavelengths between about 3 and 5 microns. The researchers saw what they interpreted as the spectral signature of DMS, a pattern that shouldn't be there unless something is producing this molecule. But here's where it gets complicated. Dimethyl disulfide has overlapping spectral features in the same wavelength range. Both molecules belong to the same chemical family. Both are predicted biosignatures. The current data can't definitively distinguish between them. Think of it like hearing a muffled voice through a wall. You know someone's speaking, but you can't quite make out whether they said yes or yeah. Both fit what you're hearing. Additional observations might sharpen the signal enough to tell them apart, but right now, we're stuck with one or the other, possibly both. The concentrations detected make the biological interpretation even more intriguing. On Earth, dimethyl sulfide exists in the atmosphere at concentrations below 1 part per billion by volume. It's produced by marine phytoplankton, released into the air, and quickly broken down by chemical reactions. The levels are low because production is balanced by destruction. On K2-18b, the estimated concentration is over 10 parts per million, thousands of times higher than Earth's levels. That's a massive difference requiring explanation. If biology is producing DMS on K2-18b, it must be doing so at extraordinary rates, or the molecule must be more stable in that environment, or both. A hydrogen-rich atmosphere might slow down the chemical reactions that normally destroy DMS on Earth. Alternatively, if there's a vast ocean teeming with DMS-producing organisms and the atmospheric chemistry is different, concentrations could build up to levels we never see in our own atmosphere. But the skeptics have compelling counterarguments. The DMS signal isn't strong. It appears in some data analysis methods but not others. When you're working at the absolute limits of instrumental sensitivity, noise becomes a serious concern. Random fluctuations can create patterns that look like signals. Statistical tools help separate real detections from false positives, but they're not perfect, especially when the signal is weak. The 3 sigma confidence level means there's a 0.3% chance the signal is just noise, a random fluctuation that happens to look like dimethyl sulfide. That might sound pretty good, but science has a higher bar. 5 sigma confidence, the gold standard for claiming a discovery, means less than a 0.00006% chance of being wrong. We're not there yet. Not even close. Then there's the methane problem. Computer models accounting for the physics and chemistry of both DMS and methane in a hydrogen-based atmosphere suggest the signal might actually be methane, not dimethyl sulfide at all. Methane was already detected on K2-18b in previous observations. If methane absorption overlaps with where we expect to see DMS, we might be mistaking one for the other. It's like trying to hear a whisper next to someone shouting. The loud signal can mask or mimic the quiet one. Raymond Peary-Humbert from Oxford University published research suggesting K2-18b might not be a water world at all. His models indicate the planet could be too hot for liquid water oceans, that what we're seeing might be better explained by a magma planet with oceans of molten rock instead of water. If that's true, the entire Hiccean interpretation collapses. No water ocean means no marine phytoplankton-like organisms producing DMS. The whole biological hypothesis falls apart. A magma planet sounds outlandish, but it's not impossible. The temperature estimates for K2-18b range from about 250 to 300 Kelvin without greenhouse effects, but greenhouse warming from a thick hydrogen atmosphere could push surface temperatures much higher. If the deeper atmosphere is hot enough to melt rock, we're not looking at a potentially habitable world but a hellscape wrapped in hydrogen. The recent reanalysis added more fuel to the skeptical fire. Independent researchers examined the same Webb data and found that instead of a clear signal, a bump or wiggle in the spectrum, the data looks consistent with a flat line. No dimethyl sulfide. No dimethyl disulfide. Just noise and uncertainty. They argue that more observations are absolutely necessary before making any claims about biosignature gases. This is where science gets messy and beautiful at the same time. Multiple teams analyzing identical data reach different conclusions. It's not that anyone's being dishonest or incompetent. It's that interpretation at the edge of detectability involves judgment calls about data processing, statistical methods, and modeling assumptions. Different choices lead to different results. Some researchers emphasize the signal they see and argue it's worth taking seriously even if it needs confirmation. Others emphasize the uncertainty and argue the evidence doesn't meet the threshold for a credible detection. Both perspectives are valuable. The optimists push the field forward by exploring possibilities. The skeptics keep everyone honest by demanding rigorous proof. The Discovery team, led by researchers including Mikku Madhusudhan, maintains that the only scenario currently explaining all the Webb data, including past and present observations, is a Hiccean world potentially hosting life. They're not claiming definitive proof. They're saying this interpretation fits the evidence better than alternatives. But they also emphasize the need for deep skepticism of their own results. Science advances through testing and retesting, not through accepting the first interesting result that comes along. What's undeniable is that we're operating at the absolute limit of current technology. Webb was designed to do exactly this kind of observation, but even Webb has constraints. The signals from small planet atmospheres are weak. The number of suitable targets is limited. The inference methods, the mathematical tools we use to extract meaning from noisy data, have inherent limitations. We're pushing against fundamental barriers of what's possible with this generation of instruments. So what comes next determines everything. The full dataset became publicly available in late April, opening the door for more astronomers to scrutinize every detail. Fresh eyes might spot something previous analyses missed. Alternative interpretations will be proposed and tested. The scientific community will collectively work through the data, and consensus will eventually emerge, though it might take months or years. Additional observation time with Webb is crucial. The team estimates that 16 to 24 hours of follow-up observations could push the statistical significance from 3 sigma to 5 sigma, crossing the threshold from intriguing possibility to credible detection. That's not a guarantee, though. More data might strengthen the signal, or it might make the whole thing disappear, revealing it was noise all along. Other instruments might contribute complementary information. Ground-based telescopes, future space missions, different observational techniques could all add pieces to the puzzle. The detection of biosignature gases isn't a one-shot deal. It's a gradual accumulation of evidence from multiple independent sources until the weight of data becomes overwhelming. But there's a deeper question lurking beneath all the technical debate. Even if we confirm dimethyl sulfide is present, even if we reach 5 sigma confidence, even if alternative explanations are ruled out, we still face the interpretation problem. Does the presence of DMS necessarily mean life? On Earth, yes. Dimethyl sulfide is produced by biological processes, mainly marine phytoplankton breaking down a precursor molecule called dimethylsulfoniopropienate. The biochemical pathways are complex, involving enzymes, bacteria, viruses, and photochemical reactions. It's deeply integrated into Earth's sulfur cycle and plays a role in cloud formation by contributing to sulfate aerosol production. The connection to life is ironclad here. But K2-18b isn't Earth. It's a world with a hydrogen atmosphere, potentially crushing pressures, temperatures, and chemistry completely unlike anything in our experience. Could there be non-biological pathways producing DMS under those exotic conditions? We genuinely don't know. DMS has been detected on comets and in the interstellar medium, proving it can form without biology in certain environments. Those detections don't involve planetary atmospheres or the concentrations we're discussing, but they demonstrate that the molecule itself isn't exclusively biological. Unknown chemistry in unknown conditions could potentially generate biosignature gases through non-living processes. This is the challenge facing astrobiology. There's no silver bullet, no single molecule that unambiguously screams life regardless of context. Everything depends on context. The molecule matters less than the environment producing it. What we need is a comprehensive understanding of what K2-18b actually is, and right now, we're operating with incomplete information. Let's step back and examine what we actually know about this world. K2-18b orbits an M-dwarf star, a red dwarf, about 124 light-years away in the constellation Leo. The star itself is smaller and cooler than our Sun, with a surface temperature around 3,457 Kelvin compared to the Sun's 5,778 Kelvin. Its radius is only 45% of the Sun's. These details matter because they shape the radiation environment, the energy budget, and the habitability prospects of any planet in the system. K2-18b completes one orbit every 33 days, placing it squarely within what astronomers call the habitable zone, the region where temperatures theoretically allow liquid water to exist on a planet's surface. It receives roughly the same amount of stellar radiation that Earth receives from the Sun. That sounds promising until you remember that habitable zone is a crude first-order approximation. It doesn't account for atmospheric composition, greenhouse effects, albedo, or a dozen other factors that determine whether a planet is genuinely habitable or a hellscape dressed in optimistic terminology. The planet is massive. 8.6 times Earth's mass. 2.6 times Earth's radius. Those numbers push it into the category of subneptunes, worlds larger than Earth but smaller than Neptune. In our solar system, there's nothing quite like it. We have rocky terrestrial planets and gas giants, but nothing in between. Subneptunes are common throughout the galaxy, yet we have no local example to study. That's a problem because it means we're working from theory and distant observations rather than direct knowledge. Here's where things get interesting. K2-18b's size and mass suggest it shouldn't be a rocky planet like Earth. It's too big. Traditional models predicted that planets of this size would have thick hydrogen atmospheres, crushing pressures, and no solid surface to speak of. Mini Neptunes, basically. Not places where life as we understand it could take hold. But the data from Webb complicated that picture considerably. The detection of methane and carbon dioxide in 2023 was the first hint that K2-18b might be something different. These carbon-based molecules in a habitable zone planet suggested chemistry compatible with life. Then came the potential DMS detection, and suddenly we're looking at a planet that doesn't fit neatly into existing categories. This led researchers to propose that K2-18b might be a Hycean world. The term Hycean was coined in 2021 by Niku Madhusudhan and his team at Cambridge. It's a portmanteau of hydrogen and ocean. The concept describes planets with vast liquid water oceans beneath thick hydrogen-rich atmospheres. Before this idea emerged, astronomers assumed such planets would be too hot to harbor life. The hydrogen atmosphere would trap heat through a runaway greenhouse effect, turning any water into superheated steam. But detailed modeling suggested otherwise. Under certain conditions, a hydrogen atmosphere could actually be cool enough to allow liquid water oceans at the surface. Think about what that means. A planet with an ocean covering its entire surface, potentially hundreds or even thousands of kilometers deep depending on temperature and gravity. Pressures at the ocean floor could reach 60,000 bar before transitioning to high-pressure ice phases. Above this ocean, a thick blanket of hydrogen gas, completely unlike Earth's nitrogen-oxygen atmosphere. Temperatures at the surface might reach 200 degrees Celsius or higher, yet the ocean persists because the pressure is so immense. This is not an environment remotely similar to Earth. If life exists there, it's operating under physical and chemical rules we can barely imagine. The hydrogen atmosphere alone changes everything. On Earth, certain biosignature gases are considered reliable indicators of life because they react quickly and shouldn't persist without biological replenishment. But in a hydrogen-rich atmosphere, those same gases might be produced through non-biological chemistry or might be stable enough to accumulate without life. The rulebook we've been using doesn't apply. Laboratory experiments have shown that Earth microorganisms can survive in hydrogen-rich atmospheres. Hydrogen itself isn't toxic to life. But that's different from saying life could originate and thrive in such conditions. We're extrapolating from our limited understanding of terrestrial biochemistry into a regime where we have no data. The ocean depths on a Hycean world depend critically on surface temperature and gravity. Models suggest they could span anywhere from tens of kilometers to potentially 1,000 kilometers before the pressure becomes so extreme that water transitions into exotic ice phases that exist only under crushing force. These ice layers would be hot, not cold, because temperature increases with depth. The conventional image of ice doesn't apply here. Within such an ocean, where would life exist? Near the surface, where temperatures might be survivable but radiation from the star could be intense. Deeper down, where pressure is enormous but conditions might be more stable. Around hydrothermal vents on the ocean floor, if such things exist. We genuinely don't know. The possibilities are wide open, constrained only by physics and chemistry, not by any examples we can point to. But there's a competing interpretation that throws all of this into question. Some researchers, including Raymond Peary-Humbert at Oxford, argue that K2-18b isn't a water world at all. Their models suggest it's too hot for liquid water to exist at the surface. Instead, they propose it might be a magma planet, a world where the surface is molten rock, not ocean. If that's correct, the entire Hycean hypothesis collapses, and K2-18b becomes a completely different kind of object, one with no habitability potential whatsoever. The debate hinges on details. Atmospheric composition, cloud properties, albedo, internal heat flow. Small differences in these parameters lead to radically different conclusions. One model produces a temperate water world. Another produces an inferno. Both are consistent with the limited data we have, which tells you how uncertain the situation really is. What about the concentration of DMS itself? On Earth, dimethyl sulfide exists in the atmosphere at levels below 1 part per billion by volume. Trace amounts. On K2-18b, the estimated concentration is over 10 parts per million. Thousands of times stronger. That's a massive difference. If the detection is real, it demands an explanation. Biological processes on Earth don't produce DMS at those concentrations in the atmosphere. So either K2-18b has vastly more biological activity than Earth, or the chemistry producing DMS there operates through entirely different mechanisms. Perhaps life on a Hycean world, if it exists, is incredibly productive. An ocean teeming with microorganisms, all releasing DMS as a metabolic byproduct, could potentially generate those high concentrations. Or maybe the atmospheric dynamics are different. On Earth, DMS gets oxidized quickly. On K2-18b, maybe it persists longer, accumulating to higher levels. We're speculating now, stacking assumptions on top of incomplete data. The alternative is that we're misinterpreting the signal entirely. Recent reanalyses of the web data suggest the DMS feature might not be there at all. Instead of a clear spectral bump indicating the molecule's presence, the data might be consistent with a flat line, just noise. The strength of the claimed detection depends entirely on how you process and interpret the raw data. Different analysis techniques produce different results. That's not ideal when you're trying to make the most important discovery in human history. Both DMS and DMDS are from the same chemical family, and their spectral features overlap in the wavelength range Webb observed. The current data can't definitively tell them apart. Future observations might resolve that ambiguity, or they might reveal that neither molecule is actually present. We're waiting on more data to settle questions that can't be answered with what we have now. The scientific process is working exactly as it should. Initial detection, public announcement, independent verification attempts, debate, more observations, gradual convergence toward truth. It's messy. It's slow. It involves false starts and dead ends. But it's the only method we have for reliably understanding reality. The alternative is wishful thinking dressed up as certainty. What happens if follow-up observations confirm DMS is really there? We're still left with the interpretation problem. Does its presence mean life, or does it mean we discovered an exotic chemical pathway that operates under conditions we've never studied? The problem runs deeper than just identifying molecules. It's about understanding what they mean in an environment nothing like Earth. When we detect DMS in our atmosphere, we know where it comes from because we've studied the organisms that produce it. We've mapped the pathways, measured the rates, understood the seasonal variations. we have context. On K2-18b, we have none of that. We're looking at a hydrogen-rich atmosphere wrapped around a planet that might be ocean, might be magma, circling a star completely different from our sun. Every assumption we make is built on Earth-based chemistry, and there's no guarantee those rules apply. Consider how DMS behaves here. Marine phytoplankton, specifically dinoflagellates and coccolithophores, synthesize it through complex biochemical pathways involving enzymes, viral interactions, and photochemical processes. Once released into the atmosphere, it oxidizes quickly, gets broken down, contributes to cloud formation. The whole cycle is tightly regulated by temperature, light availability, nutrient concentration. Change any of those parameters, and the entire system responds differently. Now imagine trying to predict what happens on a world where the atmospheric pressure is different, the radiation environment is different, the ocean chemistry is different. You can't just transplant Earth biology there and expect it to work the same way. That's why the concentration issue is so puzzling. Over 10 parts per million compared to less than 1 part per billion on Earth. If biology is producing it, the ecosystem would need to be extraordinarily productive, generating DMS at rates we've never observed. Or the atmospheric chemistry could be preventing its breakdown, allowing it to accumulate. Both scenarios require mechanisms we don't fully understand. You're trying to reverse engineer an alien biosphere from a single data point. It's like finding a footprint and trying to reconstruct the entire animal. Then there's the non-biological possibility. DMS has been detected on comets and in interstellar space, proving it can form without life. The processes aren't well understood, but they exist. Maybe K2-18b has some exotic chemistry driven by radiation, temperature gradients, or mineral interactions that produces DMS abiotically. We can't rule that out. The challenge is that we don't know all the ways molecules can form under extreme conditions. Chemistry textbooks are written based on laboratory experiments and Earth observations. We're constantly discovering that nature is more creative than our models predict. Statistical significance matters here more than in most fields. The current detection sits at 3 sigma. In particle physics, you need 5 sigma before claiming a discovery. That's because the stakes are enormous and the risk of false positives is real. 3 sigma means there's a 0.3% chance the signal is just noise, random fluctuations masquerading as a real feature. Sounds pretty good until you consider how many observations astronomers make, how many wavelengths they examine, how many molecules they search for. With enough attempts, even unlikely coincidences become probable. The researchers know this. They're calling for more observation time, specifically 16 to 24 hours with Webb, to push the detection past 5 sigma. That would reduce the false positive probability to essentially 0. But getting that telescope time isn't trivial. Webb is the most in-demand observatory in history. Every astronomer wants a piece of it. Time is allocated through competitive proposals, peer review, priority ranking. K2-18b is important, but so are hundreds of other targets. Distant galaxies, forming stars, other exoplanets. The telescope can only point in one direction at a time. Patience is required, which is frustrating when you're sitting on potentially the biggest discovery ever made. While we wait, other teams are analyzing the same data independently. That's how science progresses. Multiple groups, different analysis techniques, various assumptions. If everyone reaches the same conclusion, confidence grows. If results diverge, that tells you the signal is ambiguous and more data is essential. Recent reanalyses have been less optimistic than the original announcement. Some researchers see a flat line where others see a spectral feature. The difference comes down to data processing choices. How you remove noise, how you model the baseline, which wavelength ranges you emphasize. None of these choices are obviously right or wrong. They're judgment calls, and different judgments lead to different conclusions. This is normal in cutting-edge science, especially when working at the limits of instrumental capability. Webb is astonishingly sensitive, but it's not magic. Detecting molecules in the atmosphere of a planet 124 light-years away requires extracting incredibly faint signals from noisy data. Think about what's actually happening. Light from a distant star passes through a thin layer of gas surrounding a planet. That gas absorbs specific wavelengths corresponding to molecular vibrations. Webb measures the spectrum, looking for those absorption features. But the planet's atmosphere is tiny compared to the star. The signal you're trying to detect is a fractional change in brightness at specific wavelengths. Any instrumental artifact, any calibration error, any unaccounted variable can produce false features. The overlap between DMS and DMDS complicates things further. Both molecules are sulfur-containing organics with similar structures. Their spectral signatures overlap in the wavelength range Webb observed. You can't definitively say which one you're seeing, or if it's a combination, or if it's something else entirely producing a similar-looking feature. Future observations at different wavelengths might resolve the ambiguity, but right now, the data is consistent with multiple interpretations. What about the hydrogen-rich atmosphere itself? On Earth, biosignature gases are identified based on their behavior in our nitrogen-oxygen atmosphere. Certain molecules, like oxygen or methane in large quantities, are considered strong biosignatures because they shouldn't coexist without biology constantly replenishing them. But in a hydrogen-dominated atmosphere, those rules change. Some gases that would be biosignatures on Earth become unreliable indicators elsewhere. The chemistry is just different. Hydrogen reacts with things nitrogen doesn't. It changes oxidation states, reaction rates, equilibrium concentrations. You need entirely new models to predict what a biosignature would even look like in that environment. Microorganisms from Earth can survive in hydrogen-rich conditions. Lab experiments have demonstrated that. So hydrogen itself isn't toxic to life. But would life that evolved in a hydrogen atmosphere produce the same waste gases as Earth life? Maybe. Maybe not. Evolution is contingent. Life adapts to its environment using whatever chemistry is available. On Earth, photosynthesis uses water and produces oxygen. On a Hycean world, maybe life uses different molecules, produces different byproducts. We're looking for Earth-like biosignatures because those are the ones we know how to recognize. That doesn't mean they're the only ones that exist. The bigger question is whether we're even asking the right questions. For nearly a century, astronomers have focused on atmospheric disequilibrium as a sign of life. The idea is that certain gas mixtures shouldn't exist together unless something is actively maintaining them. Oxygen and methane, for example. They react with each other, so if you detect both in significant quantities, something must be replenishing them faster than they can react away. Life is one explanation. But it's not the only one. Geological processes, photochemistry, exotic atmospheric dynamics could also create disequilibrium. The challenge is distinguishing between biological and non-biological sources from light years away. K2-18b represents a test case for this entire approach. If the DMS detection holds up, if follow-up observations confirm it, we're forced to interpret what it means. Is it life? Is it chemistry we don't understand? Is it an instrumental artifact we haven't identified? Each answer has profound implications. If it's life, everything changes. If it's not, we've learned something important about planetary atmospheres and the limits of remote sensing. Either way, the process of figuring it out advances our understanding. The lead researchers have been careful with their language. They're not claiming definitive proof of life. They're presenting data, proposing interpretations, calling for verification. That's exactly how it should work. The temptation to overhype is enormous. This is the kind of discovery that makes careers, wins awards, gets remembered in textbooks. But claiming life prematurely, only to be proven wrong later, damages credibility and sets the field back. Better to be cautious, methodical, rigorous. Let the data accumulate. Let the debate unfold. Let the truth emerge through the messy, slow process of scientific consensus building. What happens if Phi Sigma is reached and DMS is confirmed beyond doubt? We're still left with interpretation. The molecule is there, but what's producing it? That question can't be answered with spectroscopy alone. You'd need detailed atmospheric models, laboratory experiments simulating Hisian conditions, maybe even direct detection of other biosignatures to build a coherent case. One molecule isn't enough. You need a pattern, a suite of indicators that together point toward biology as the most likely explanation. That's the standard. Anything less leaves too much room for doubt. And that's where the timeline becomes critical. The researchers estimate they need between 16 and 24 additional hours of observation time with Webb. That might not sound like much, but telescope time is precious. Webb isn't dedicated to a single target. Hundreds of research teams compete for every available hour. Scheduling those observations, collecting the data, processing it, that takes months. Maybe longer. During that waiting period, the scientific community doesn't sit idle. The original dataset became publicly available in April, which means independent researchers can now access the same raw data. They'll run their own analyses, apply different statistical methods, test alternative interpretations. Some will support the findings. Others will challenge them. That's the messy reality of frontier science. Consensus doesn't emerge from a single paper but from a community-wide process of scrutiny and verification. Here's what makes this particularly complicated. The signal isn't clean. It's buried in noise, overlapping with methane spectral features, sitting right at the edge of what current instruments can reliably detect. Different teams using different data reduction techniques might reach different conclusions about whether the bump in the spectrum is real or an artifact. That's already happening. Recent reanalyses of the same data suggest the signal might be consistent with a flat line, no feature at all. The original team stands by their results, pointing to specific wavelengths and modeling approaches that support the detection. Who's right? More data will tell. But even if the 5 sigma threshold is eventually reached, even if DMS is confirmed with statistical certainty, we're not done. Confirmation means the molecule is there. It doesn't automatically mean life put it there. You'd still need to rule out non-biological explanations. And here's where it gets tricky. DMS has been detected in comets. It's been found in the interstellar medium, the diffuse gas and dust between stars. That proves it can form through purely chemical processes, no biology required. So how do you distinguish between biological and non-biological sources from 124 light-years away? Context matters. On Earth, DMS concentrations in the atmosphere are typically below 1 part per billion. On K2-18b, the estimated concentration is over 10 parts per million, thousands of times higher. That difference is significant. Non-biological processes tend to produce trace amounts, not massive concentrations. But that's an assumption based on Earth chemistry. Maybe Hycean world chemistry operates differently. Maybe there's some exotic photochemical pathway we haven't considered that churns out DMS at high concentrations without biology. You can't rule it out just because we haven't thought of it yet. This is why the search for biosignatures requires multiple lines of evidence. One molecule, however compelling, isn't enough. You need a pattern. A suite of gases that together make biological production the most parsimonious explanation. The researchers detected methane and carbon dioxide in earlier observations. Those are consistent with biological activity, but they're also produced by geological processes. Add DMS to the mix and the biological hypothesis becomes stronger. But it's still not definitive. You'd want to see other sulfur compounds, maybe organic molecules, signatures of metabolic waste products that don't have obvious non-biological sources. The challenge is that we're working with incredibly limited information. Transmission spectroscopy gives you atmospheric composition, nothing more. You can't see the surface. You can't measure ocean salinity or pH. You can't detect cellular structures or DNA. All you have is the chemical fingerprint of gases backlit by starlight. From that, you're trying to infer the presence of life. It's like trying to diagnose a patient's illness by analyzing their breath, except the patient is 124 light-years away and you only get to sample their breath once every few years. What would make the case stronger? Detection of gases that have no known non-biological source. On Earth, certain compounds are produced exclusively by life. Methyl chloride, for example, is made by marine algae and has no significant geological source. If you detected that on K2-18b, alongside DMS and other biosignatures, the biological hypothesis would become much harder to dismiss. But even then, you'd need to demonstrate that no unknown chemistry could produce those gases. That's a high bar. Some researchers argue we're approaching this wrong. Instead of looking for individual molecules, we should be looking for chemical disequilibrium patterns that only life can sustain. The idea is that life constantly pushes chemistry away from equilibrium, maintaining gas mixtures that would otherwise react away. On Earth, oxygen and methane coexist because life produces both faster than they can react with each other. Without life, that disequilibrium would collapse within a few million years. If you can demonstrate that K2-18b's atmosphere is in persistent disequilibrium, and that no geological or photochemical process can maintain it, that's stronger evidence than any single molecule. The problem is proving the negative. How do you demonstrate that no unknown process exists? You can't. You can only show that all known processes fail to explain the data. That's weaker than it sounds because planetary science is full of surprises. Venus has phosphine in its atmosphere, and nobody's entirely sure why. It could be life, or it could be some weird atmospheric chemistry we don't understand yet. The same uncertainty applies here. There's also the question of what kind of life we're talking about. If K2-18b hosts biology, it's almost certainly microbial. Single-celled organisms living in the ocean, metabolizing whatever chemistry is available. Not fish, not plants, nothing complex. The conditions wouldn't support it. High atmospheric pressure, crushing ocean depths, temperatures that might reach 200 degrees Celsius in deeper layers. Surface waters might be cooler, more temperate, but you're still looking at an alien environment fundamentally different from Earth. Life adapted to that environment wouldn't look like Earth life. It would be something else entirely. Which raises an interesting philosophical point. When we search for biosignatures, we're inherently biased toward Earth-like life because that's the only reference we have. We know what Earth life produces, what gases it releases, what chemical disequilibria it creates. But life elsewhere might operate on completely different principles. Silicon-based instead of carbon-based. Using ammonia instead of water. Metabolizing in ways we haven't imagined. If that's the case, we might be looking right at biosignatures without recognizing them because they don't match our preconceptions. This is the central tension in astrobiology. You want to cast a wide net, consider all possibilities, but you also need specific, testable predictions. You can't search for everything simultaneously. You have to prioritize, make educated guesses about what's most likely. That inevitably introduces bias. The challenge is being aware of that bias and not letting it blind you to unexpected findings. K2-18b might not be the planet where we finally confirm extraterrestrial life. The signal might not hold up. The interpretation might shift as more data comes in. But it's pushing the field forward regardless. It's forcing researchers to refine their models, develop better detection methods, think harder about what constitutes convincing evidence. Each attempt, whether successful or not, teaches us something about planetary atmospheres, about the limits of our instruments, about the complexity of distinguishing biology from chemistry. The next generation of telescopes will help. Instruments currently being designed will have higher sensitivity, better spectral resolution, the ability to study smaller, rockier planets. They'll be able to detect fainter signals, resolve overlapping spectral features, measure atmospheric composition with greater precision. That will narrow the uncertainty, make the interpretations less ambiguous. But it won't eliminate the fundamental challenge. We're still doing remote sensing across vast distances, inferring complex phenomena from limited data. What happens if we do eventually confirm life on K2-18b or another exoplanet? The implications extend far beyond astronomy. It would reshape our understanding of biology, showing that life isn't unique to Earth but emerges wherever conditions allow. It would raise questions about how common life is, whether intelligence is inevitable, what our place is in a universe teeming with biology. Those aren't just scientific questions. They're philosophical, even existential. But we're not there yet. Right now, we're in the uncertain middle ground between detection and confirmation. The data is suggestive but not conclusive. The interpretations are plausible but not proven. The path forward requires patience, rigor, and a willingness to accept that we might not get definitive answers as quickly as we'd like. The scientific process doesn't move in straight lines. It advances through incremental steps, occasional breakthroughs, and frequent setbacks. Each observation adds a data point, constrains the possibilities, eliminates hypotheses that don't fit. That's how knowledge builds. Not through sudden revelations, but through accumulated evidence slowly shifting the balance of probability. K2-18b represents one data point in that larger process. A significant one, certainly. The detection of potential biosignature gases on a habitable zone planet using our most advanced telescope is noteworthy regardless of how the interpretation ultimately resolves. But it's still just one planet among thousands we've discovered, millions that likely exist in our galaxy alone. Consider the broader landscape. Webb has only been operational since 2022. In that short time, it's already transformed exoplanet science, providing atmospheric data that was impossible to obtain before. WASP 39b, a hot Jupiter, revealed a complete chemical inventory including water vapor, carbon dioxide, carbon monoxide, sodium, potassium, and sulfur dioxide. That last one was particularly interesting because it requires photochemistry, chemical reactions driven by starlight in the upper atmosphere. It showed that planets far different from Earth still have complex atmospheric processes. TOI 561b, an ultra-hot super-Earth, challenged assumptions about small planets close to their stars. Conventional wisdom said they shouldn't retain atmospheres. The stellar radiation should strip away any gases. Yet Webb detected what appears to be a thick atmosphere, possibly above a global magma ocean. The planet's unusually low density suddenly made sense. It's not just rock. It has a substantial gaseous envelope despite the harsh environment. These discoveries matter because they expand our understanding of what's possible. Each unexpected finding forces researchers to reconsider their models, question their assumptions, think more creatively about planetary formation and evolution. That's the value of exploration. Not just confirming what you already believe, but discovering what you didn't anticipate. Which brings us back to the central question. How do we know when we've actually found life? The answer isn't simple because life itself isn't simple. On Earth, biology produces countless chemical signatures. Oxygen, methane, phosphine, nitrous oxide, dimethyl sulfide, hundreds of volatile organic compounds. But almost all of these can also be produced through non-biological processes under the right conditions. Oxygen comes from photosynthesis, but also from water vapor breaking apart in the upper atmosphere. Methane comes from microbes, but also from volcanic activity and geochemical reactions. Phosphine might come from life, but it's also produced in gas giants through atmospheric chemistry. The challenge is distinguishing biological production from geological or atmospheric production when you can't visit the planet to investigate directly. You're limited to remote observations, spectral analysis, statistical inference. That means looking for combinations of gases that are unlikely to coexist without biology. On Earth, oxygen and methane together create a disequilibrium signature. They react with each other chemically, so their simultaneous presence suggests continuous replenishment from different sources. Biology maintains that disequilibrium. Remove life, and the gases would equilibrate, disappearing over geological timescales. But what if alien biochemistry operates differently? What if life elsewhere uses different metabolic pathways, produces different waste products, creates different atmospheric signatures? We wouldn't necessarily recognize it because we're calibrated to Earth's patterns. This is the biosignature detection paradox. You need specific predictions to guide your search, but those predictions inevitably narrow your perspective. You might miss what you're not looking for. Some researchers argue for a more agnostic approach. Instead of searching for specific molecules, look for any chemical disequilibrium that can't be explained by known planetary processes. If you detect an atmosphere that's thermodynamically unstable, something must be maintaining it. That something could be biology. The problem with this approach is that planetary processes are complex and not fully understood. What looks like unexplained disequilibrium might just be physics we haven't modeled correctly. You risk false positives if you're not careful. The flip side is false negatives. If you're too conservative, demanding ironclad proof before accepting a biosignature, you might dismiss genuine detections because they don't fit your preconceptions. Science requires balancing these risks. Being open to unexpected findings while maintaining rigorous standards of evidence. It's not easy. The history of science is littered with premature announcements, overinterpreted data, claims that didn't hold up to scrutiny. That's why the K2-18b team is proceeding cautiously despite the suggestive signals. They've reached 3 sigma statistical significance, meaning there's a 0.3% chance the signal is random noise. That sounds compelling, but in scientific terms, it's not enough for confirmation. The standard for discovery claims is 5 sigma, which corresponds to a probability of less than 0.00006% that the signal is coincidental. Getting from 3 sigma to 5 sigma requires more observation time, better data, additional wavelength coverage. The team estimates they need 16 to 24 more hours of telescope time to reach that threshold. Whether they'll get it is uncertain. Telescope time is precious. Webb is oversubscribed by a factor of 10, meaning far more proposals than available observation slots. Every hour spent on K2-18b is an hour not spent on other targets. Committees evaluate proposals, prioritize based on scientific merit, feasibility, likely impact. K2-18b is compelling, but so are dozens of other candidates. The allocation process is competitive. Assuming they do get the time and the signal strengthens to 5 sigma, then what? Even definitive detection of dimethyl sulfide doesn't automatically mean life. It just means biology becomes the most likely explanation. You'd still need to rule out alternative scenarios. Could photochemistry in a hydrogen-rich atmosphere produce DMS through pathways we haven't considered? Could geological processes release sulfur compounds that combine in the atmosphere to form DMS? Are there reactions involving minerals, water, and atmospheric gases that might generate these molecules without biology? These questions need answers before claiming discovery. The scientific community would scrutinize every aspect. The data reduction methods, the spectral analysis techniques, the atmospheric models, the statistical treatments. Other teams would attempt independent analyses using the same data. They'd look for errors, biases, alternative interpretations. This process is essential. Extraordinary claims require extraordinary evidence, and the claim of extraterrestrial life is about as extraordinary as it gets. The evidence needs to withstand intense scrutiny from multiple independent groups before acceptance. Even if the biosignature interpretation holds up, you're still left with profound uncertainties. You know life probably exists on that planet, but you don't know what kind. You don't know how it originated, how it evolved, whether it's widespread or rare. You don't know if it's simple or complex, ancient or recent, thriving or barely surviving. All you have is a chemical signature in an atmosphere 124 light-years away. The rest is inference and speculation. That might seem frustrating, but it's actually remarkable. A century ago, we didn't know if other planets existed beyond our solar system. 50 years ago, we had no way to study their atmospheres. 20 years ago, we couldn't detect biosignature gases even if they were present. Now we're at the threshold of potentially confirming life elsewhere. The pace of progress has been extraordinary. The capabilities we've developed in just a few decades would have seemed like science fiction to earlier generations. Future telescopes will push further. The Habitable Worlds Observatory, currently in early planning stages, is designed specifically to characterize Earth-like planets around Sun-like stars. It will have a coronagraph to block starlight, allowing direct imaging of planets in reflected light rather than relying on transit spectroscopy. That opens up new possibilities. You could study planets that don't happen to pass in front of their stars from our perspective. You could analyze surface features, detect seasonal variations, maybe even observe geological activity. Ground-based extremely large telescopes coming online in the next decade will complement space-based observations. The 30-meter telescope, the Giant Magellan Telescope, and the Extremely Large Telescope will have collecting areas far larger than Webb, allowing them to gather more photons and achieve higher spectral resolution. They'll be limited by Earth's atmosphere, but adaptive optic systems are becoming sophisticated enough to compensate. Combined with space telescopes, they'll provide multiple independent measurements of planetary atmospheres, reducing uncertainties and strengthening conclusions. The technology is advancing rapidly. So is our theoretical understanding. Researchers are developing more sophisticated atmospheric models, accounting for complex chemistry, cloud formation, atmospheric circulation patterns. They're studying extreme environments on Earth, places where life persists under conditions previously thought uninhabitable. Deep ocean vents, acidic hot springs, Antarctic ice, high-altitude deserts. Each discovery of terrestrial extremophiles expands the envelope of possibility for where life might exist elsewhere. This is the context in which K2-18b should be understood. Not as a definitive answer, but as a milestone in an ongoing journey. We're learning how to ask the right questions, developing the tools to answer them, building the knowledge base to interpret what we find. Each planet we study teaches us something new about atmospheric processes, planetary formation, the conditions necessary for habitability. That knowledge accumulates, refining our search strategies and improving our detection capabilities. The question of whether we're alone in the universe won't be answered by a single observation. It will be answered through accumulated evidence from multiple planets, multiple biosignatures, multiple independent confirmation. K2-18b might be part of that answer. Or it might turn out to be a false alarm, teaching us about atmospheric chemistry instead of biology. Either way, it's moving the field forward. That's what matters. Not whether this particular planet hosts life, but whether we're getting better at finding out. And we are. The tools exist now. The methods are proven. The candidates are identified. What happens next depends on how we use them. The timeline stretches ahead with uncomfortable uncertainty. Those additional observation hours with Webb might happen next year. Or the year after. Scheduling depends on committee decisions, competing priorities, telescope availability. Meanwhile, K2-18b keeps orbiting its red dwarf star, oblivious to our scrutiny, its atmosphere continuing whatever processes are producing those spectral features we're arguing about. What's clear is that we've crossed a threshold. Not necessarily the threshold of discovering life, but the threshold of being able to look. Webb represents a capability that didn't exist 5 years ago. We can now analyze the atmospheric composition of planets in habitable zones around other stars. That's not incremental progress. That's a fundamental shift in what's possible. Think about where we were just a generation ago. The first exoplanet around a Sun-like star was confirmed in 1995. Before that, we literally didn't know if planets existed beyond our solar system. We suspected they did, but suspicion isn't knowledge. Now we've cataloged thousands. We know that planets are common, that rocky worlds exist throughout the galaxy, that many orbit within their stars' habitable zones. The question has shifted from, are there other worlds? To, what are those worlds like? K2-18b forces us to confront how we answer that second question. The data is ambiguous. The interpretations diverge. But the fact that we're having this debate at all, arguing over spectral features in the atmosphere of a planet 124 light-years away, that's the real story. We're not just theorizing anymore. We're measuring, analyzing, testing hypotheses against actual observations. Whether dimethyl sulfide is really there, whether it's produced by life or exotic chemistry, those questions will get resolved through the normal scientific process. More data will arrive. Better models will be developed. Consensus will eventually form, though it might take years. That's fine. Science doesn't run on news cycle timelines. It runs on evidence accumulation, and evidence takes time. The broader trajectory is what matters. Each planet studied adds to our understanding of atmospheric processes, of what's normal and what's anomalous, of how to distinguish biology from geology from instrumental artifacts. We're building a reference library of planetary atmospheres, learning to read chemical signatures across an enormous range of conditions. That knowledge base will prove invaluable when the next candidate emerges, and the one after that. Because K2-18b won't be the last world where we detect potential biosignatures. Webb is just getting started. There are thousands of exoplanets within its observational range. Some will be too hot, too cold, too massive, too small. But some will sit in that narrow band of conditions where life as we understand it might exist. Those are the targets. Those are where humanity's attention will focus over the coming decades. The search for life beyond Earth isn't a single moment of discovery. It's a process of gradually narrowing uncertainty, eliminating alternatives, building confidence through accumulated evidence. Maybe K2-18b is the first confirmed detection. Maybe it's a stepping stone toward understanding Hycean worlds that don't actually host life. Maybe it's teaching us that our biosignature detection methods need refinement before we can trust them. All of those outcomes advance the field. What we're witnessing is the maturation of a scientific discipline. Astrobiology is transitioning from speculation to observation, from hypothetical arguments to data-driven conclusions. The tools exist now to test ideas that were purely theoretical a decade ago. That's transformative. It changes the conversation from, could there be life? To, here's what we measured, here's what it might mean, here's how we find out for sure. The philosophical implications lurk beneath the technical debates. If life exists on K2-18b, even simple microbial life, it would demonstrate that biology isn't unique to Earth. It would show that the chemical and physical conditions necessary for life arise naturally when planets form in habitable zones. That has profound consequences for how common life might be throughout the galaxy, throughout the universe. If it happened twice in one small corner of space, it's probably happened billions of times elsewhere. But those implications only matter if the detection is real. And that's still uncertain. The data is suggestive. The interpretation is plausible. The statistical confidence is approaching significance. But we're not there yet. The gap between intriguing possibility and confirmed discovery remains, and crossing that gap requires rigor that can't be rushed. So we wait. For more telescope time. For additional observations. For independent verification. For the slow grinding process of science to either confirm or refute what the initial data suggested. That waiting is hard, especially when you're potentially sitting on the biggest discovery in human history. But it's necessary. Getting it right matters more than getting it first. Meanwhile, the search continues. Other planets. Other biosignatures. Other research teams developing new detection methods, new analytical techniques, new ways of interpreting atmospheric chemistry. The field is advancing on multiple fronts simultaneously. K2-18b is one thread in a much larger tapestry. Whether this particular thread leads to confirmation of life or not, the tapestry keeps growing, the picture keeps coming into focus. What happens over the next few years will determine whether K2-18b enters the history books as the first world where we found evidence of extraterrestrial life, or as a cautionary tale about the challenges of biosignature detection. Either way, it's already changed how we think about the search. It's demonstrated that we have the capability to detect potential biosignatures. It's revealed the complexity of interpretation. It's shown us both the promise and the pitfalls of this endeavor. The universe doesn't care about our timelines or our eagerness for answers. It will reveal its secrets at its own pace, through careful observation and rigorous analysis. Our job is to keep looking, keep measuring, keep questioning our interpretations until the weight of evidence becomes overwhelming. That's how we'll eventually answer the question of whether we're alone. Not through a single dramatic discovery, but through accumulated knowledge that makes the answer undeniable. K2-18b might be that answer. Or it might be a false start. The only way to know is to keep looking at the data, keep refining the models, keep pushing the instruments to their limits. Because somewhere out there, on some planet around some distant star, life probably exists. Finding it, proving it, understanding it, that's the challenge defining this era of astronomy. And we're closer now than we've ever been. 7 planets orbit a star 40 light-years away. Not scattered randomly like our solar system, but compressed into a space smaller than Mercury's orbit around our sun. If you stood on one of these worlds and looked up, neighboring planets would appear larger in the sky than our moon. This isn't science fiction. This is TRAPPIST-1. In 2017, NASA announced the discovery of 7 Earth-sized planets around a single star. 3 of them sit in the habitable zone where liquid water could exist. Within weeks, TRAPPIST-1 became the most studied planetary system beyond our own. Scientists redirected telescopes, reprioritized missions, and rewrote research proposals. Because this system isn't just interesting, it's a laboratory for understanding whether life exists elsewhere in the universe. The star itself defies everything we assume about solar systems. TRAPPIST-1 is an ultra-cool dwarf star, barely larger than Jupiter, burning at temperatures that make it glow deep red rather than yellow like our sun. It produces less energy in a year than our sun emits in a day. Yet around this dim ember orbit 7 rocky worlds, each locked in gravitational resonance, their orbits synchronized like a cosmic clockwork mechanism that's been running for billions of years. Distance creates problems. 40 light-years means the light we see from TRAPPIST-1 today left that star before the internet existed. Any signal we send would take 40 years to arrive, and we'd wait another 40 for a response. Even our fastest spacecraft would need hundreds of thousands of years to reach it. This isn't a place we'll visit anytime soon. But distance doesn't mean irrelevance. The James Webb Space Telescope changed everything. For the first time in human history, we can analyze the atmospheres of planets orbiting other stars. We're not guessing anymore about what exists on distant worlds. We're measuring it directly. And TRAPPIST-1, with its compact system and frequent planetary transits, offers the best opportunity we have to detect signs of life beyond Earth. Here's what makes this system extraordinary. The planets don't just orbit randomly. They're locked in what astronomers call orbital resonance. For every 8 orbits TRAPPIST-1b completes, planets C, D, E, F, G, and H complete 5, 3, 2, 1, and 1 orbits respectively. This mathematical precision isn't coincidence. It's the signature of a system that has stabilized over billions of years, where gravitational interactions have pulled planets into synchronized motion. Think of it like pushing someone on a swing. Push at random times and nothing happens. Push at exactly the right moment in each cycle and the swing goes higher. The TRAPPIST-1 planets push and pull on each other at precisely the right times, stabilizing their orbits and potentially creating conditions that could support life. The innermost planet, TRAPPIST-1b, completes an orbit in just 1.5 Earth days. It's too close to the star, receiving 4 times more radiation than Earth gets from the Sun. Surface temperatures likely exceed 400 degrees Fahrenheit. Any water that once existed has long since evaporated. But move outward and conditions change rapidly. TRAPPIST-1e sits in the middle of the habitable zone. It's almost exactly Earth's size, slightly more massive, with a density suggesting a rocky composition similar to our own planet. If water exists anywhere in this system, this is where we'd expect to find it. Scientists have focused enormous attention on this single world because it represents our best chance of finding life around an ultra-cool dwarf star. But there's a problem nobody expected. The first atmospheric measurements came back essentially blank. The James Webb Space Telescope detected no significant atmosphere on TRAPPIST-1b or c. For planets that should theoretically hold on to their atmospheres, this absence is troubling. It suggests something is stripping away these gaseous envelopes faster than planets can retain them. The star itself might be the culprit. Ultra-cool dwarf stars like TRAPPIST-1 are violent in ways our Sun isn't. They produce intense stellar flares, bursts of radiation and charged particles that slam into nearby planets. These flares can be thousands of times more powerful than solar flares. When they strike a planet, they don't just heat the surface. They strip away atmospheric particles, molecule by molecule, potentially rendering worlds uninhabitable despite being in the so-called habitable zone. This creates a paradox. Ultra-cool dwarf stars are the most common type of star in the galaxy. They make up roughly 75% of all stars. They also live for trillions of years, far longer than our Sun's projected 10 billion-year lifespan. If life needs time to develop, these stars offer more of it than any other stellar type. But if their flares destroy atmospheres, then the most common stars in the galaxy might also be the least likely to host life. Yet dismissing TRAPPIST-1 would be premature. Planets might protect themselves in ways we haven't considered. Strong magnetic fields could deflect stellar wind. Thick atmospheres could regenerate faster than flares strip them away. Oceans could provide a reservoir of gases that replenish atmospheric losses. And some planets in the system, particularly those farther from the star, might avoid the worst of the stellar violence while still receiving enough energy for liquid water. TRAPPIST-1f and g occupy positions at the outer edge of the habitable zone. They receive less radiation than Earth, but not so little that water must freeze. These worlds might be covered in ice with liquid oceans beneath frozen crusts, similar to Jupiter's moon Europa or Saturn's moon Enceladus. Such environments could be remarkably stable, shielded from stellar flares by kilometers of ice while maintaining liquid water in contact with rocky cores where chemical reactions could support life. The density measurements tell us something unexpected. These planets aren't identical copies of Earth. Their densities vary significantly, suggesting different compositions. Some might be water worlds with deep global oceans. Others could be desiccated rocks stripped bare by stellar radiation. A few might have retained thick atmospheres of hydrogen and helium. The system isn't uniform. It's diverse, offering multiple pathways for habitability or multiple ways for planets to fail at supporting life. Tidal forces add another layer of complexity. Because the planets orbit so close to their star and are likely tidally locked, one side permanently faces the star while the other side remains in eternal darkness. This creates extreme temperature gradients. The day side might be scorching hot while the night side freezes. Any atmosphere would constantly circulate, trying to redistribute heat from day to night. This circulation could create permanent storms, winds that never stop, weather patterns unlike anything Earth experiences. But tidal locking isn't necessarily bad for life. The twilight zones, the regions between permanent day and permanent night, could be remarkably stable. Temperatures there might remain moderate, avoiding the extremes of either hemisphere. If liquid water exists, it would likely pool in these twilight regions, creating narrow bands where conditions stay relatively constant. Life, if it exists, might be confined to these transitional zones, thriving in the permanent sunset of a tidally locked world. Scientists debate whether we could ever know for certain if these planets host life. Detecting an atmosphere is one thing. Proving that atmosphere contains biosignatures, gases produced by living organisms, is far more challenging. Oxygen is the classic example. On Earth, oxygen exists in our atmosphere because photosynthetic organisms constantly produce it. Without life, oxygen would quickly react with surface rocks and disappear. Finding oxygen in TRAPPIST-1E's atmosphere would be compelling evidence for life. But oxygen alone isn't enough. Geological processes can produce oxygen without life. We need combinations of gases, chemical signatures that only make sense if biology is present. Oxygen combined with methane, for instance, would be powerful evidence because these gases react with each other and shouldn't coexist unless something continuously produces them. Life produces both. Geology typically doesn't. The James Webb Space Telescope will spend years studying TRAPPIST-1. Each time a planet passes in front of the star, starlight filters through its atmosphere and reaches us carrying information about what gases exist there. By analyzing this light, scientists can identify atmospheric components. But the signals are faint. Detecting them requires hundreds of observations, patient accumulation of data, building up evidence piece by piece until a picture emerges. Recent observations of TRAPPIST-1b have been discouraging. The planet appears to have no substantial atmosphere. This doesn't doom the entire system, but it raises questions about how well any of these planets have retained their atmospheres. If the innermost planet lost its gases, what about the others? Are we searching for life in a system where stellar activity has already stripped away the very atmospheres we need to study? TRAPPIST-1c faces similar scrutiny. Early measurements suggested the possibility of a thick carbon dioxide atmosphere. Subsequent observations found no evidence for it. Either the atmosphere is incredibly thin or composed of gases we haven't detected yet. Or perhaps it simply doesn't exist. Each negative result narrows the possibilities but doesn't eliminate hope. We're still learning how to interpret these observations, still understanding the limitations of our instruments. The system's age compounds these uncertainties. TRAPPIST-1 is roughly 7.6 billion years old, significantly older than our solar system. That's billions of additional years for stellar flares to pummel planets, for atmospheres to erode, for conditions to change. But it's also billions more years for life to emerge, evolve, and potentially leave detectable traces. Age cuts both ways. What happens next depends on what we find. If TRAPPIST-1e has an atmosphere, the focus shifts to characterizing it completely. Scientists will search for water vapor, carbon dioxide, methane, oxygen, and dozens of other compounds. Each detection or non-detection refines our understanding of what kind of world exists there. If we find nothing, attention might shift to the outer planets where conditions could be less hostile despite receiving less stellar energy. Human nature drives us to find patterns, to imagine what these worlds look like, to picture oceans and mountains and alien skies. But we need to resist premature conclusions. TRAPPIST-1 might host life. It might be completely dead. It might fall somewhere in between, with environments capable of supporting life but currently empty through cosmic accident. The only way to know is through methodical observation, collecting evidence without rushing to judgment. The implications extend beyond 7 planets around a dim star. TRAPPIST-1 is common in the galaxy. Not this exact system, but ultra-cool dwarf stars with compact planetary systems. If we determine that TRAPPIST-1 planets can't support life, we're effectively ruling out billions of similar systems. If we find that life can exist there despite the challenges, we're opening up vast regions of the galaxy as potential habitats. Either answer reshapes our understanding of life's prevalence in the universe. Human outlined these possible outcomes. What actually exists at TRAPPIST-1 remains unknown. But each observation brings clarity, each measurement constrains possibilities. We're moving from speculation to data, from wondering to knowing. And the journey has barely started. The challenge isn't just detecting atmospheres. It's understanding what those atmospheres tell us about the planets beneath them. An atmosphere doesn't exist in isolation. It's shaped by volcanic activity, weathering of rocks, biological processes, and the relentless bombardment of stellar radiation. Consider what happens when starlight passes through a planetary atmosphere. Different molecules absorb specific wavelengths of light. Oxygen absorbs certain frequencies. Water vapor absorbs others. Methane has its own signature. By measuring which wavelengths are missing from the light that reaches us, scientists can deduce what gases are present. But this requires the planet to pass directly between us and its star, creating a transit. During those few hours when the geometry aligns, telescopes collect as much data as possible. Then the planet moves on, and we wait weeks or months for the next opportunity. The signal we're measuring is incredibly weak. Imagine trying to detect a single grain of sand added to a beach by measuring the beach's total weight. That's the scale we're working with. The atmosphere of an Earth-sized planet adds roughly 1 part in 10,000 to the total light blocked during a transit. Within that tiny signal, we're searching for even tinier variations caused by specific molecules. It's technically possible, but it requires perfect conditions, flawless calibration, and patience. TRAPPIST-1 doesn't make this easy. The star itself is variable, with surface features that change over time. Star spots, the cooler regions on a star's surface, can mimic or obscure atmospheric signals. When a planet transits across a star spot, the light curve changes in ways that have nothing to do with the planet's atmosphere. Separating these effects requires multiple observations and sophisticated modeling. We're essentially trying to subtract the star's natural variations to isolate the planet's contribution. The James Webb Space Telescope was designed for exactly this kind of work. Its infrared capabilities allow it to detect molecules that are invisible to optical telescopes. Carbon dioxide, for instance, has strong absorption features in the infrared. Water vapor shows up clearly. Methane becomes detectable. But even Webb has limitations. Observing a single planet requires multiple transits. Building up enough signal to confidently detect an atmosphere can take dozens of hours of telescope time. With 7 planets to study and limited observing windows, the process stretches across years. Early results from Webb have been humbling. The instrument works brilliantly, but the planets aren't cooperating. TRAPPIST-1b shows no sign of a thick atmosphere. TRAPPIST-1c remains ambiguous. These aren't instrument failures. They're real results telling us something important about how planets survive around red dwarf stars. Maybe atmospheres around these stars are rare. Maybe they exist but are composed of gases we haven't thought to look for. Or maybe we need more data before drawing conclusions. The habitable zone planets present a different puzzle. TRAPPIST-1e receives roughly the same amount of energy from its star as Earth receives from the Sun. If it has an atmosphere, that atmosphere could support liquid water on the surface. But the planet is tidally locked, with one side permanently facing the star and the other side in eternal darkness. This creates extreme temperature gradients. The day side could be scorching, the night side frozen. Only in the narrow band between them, the terminator region, might temperatures allow liquid water. Unless the atmosphere redistributes heat. A thick atmosphere with strong winds could transport warmth from the day side to the night side, moderating temperatures across the entire planet. Earth's atmosphere does this to some extent. Venus does it far more effectively, with winds so powerful they circle the planet in just 4 days despite the planet's slow rotation. If TRAPPIST-1e has similar atmospheric circulation, the entire surface could be habitable. But if the atmosphere is thin or non-existent, the terminator might be the only refuge. This matters for more than just temperature. Atmospheric circulation affects where water accumulates. On a tidally locked planet with poor heat transport, all the water could freeze on the night side, leaving the day side as a scorched desert. With good circulation, water could remain liquid across much of the surface. The difference between these scenarios determines whether the planet could support life, and whether that life might be detectable from Earth. Detecting life itself requires finding biosignatures, gases that are produced by living organisms and wouldn't persist in the atmosphere without continuous replenishment. Oxygen is the classic example. On Earth, photosynthetic organisms produce vast amounts of oxygen. Without them, oxygen would rapidly combine with rocks and disappear from the atmosphere. Finding oxygen around another planet doesn't guarantee life, but it strongly suggests biological activity. Methane is another candidate. On Earth, methane comes from both biological and geological sources. Bacteria in swamps produce methane. Volcanic activity releases it. Finding methane alone doesn't prove life exists. But finding methane and oxygen together creates a stronger case. These gases react with each other, so their simultaneous presence suggests something is actively producing them. Life is the most obvious explanation. The problem is false positives. Geological processes can produce oxygen under certain conditions. Photochemistry in the upper atmosphere can generate small amounts. Methane can accumulate if volcanic activity is high and chemical reactions are slow. We need multiple lines of evidence, combinations of gases that can't be easily explained by non-biological processes. And we need to understand the planet's geology, its star's activity, and its atmospheric chemistry well enough to rule out alternative explanations. TRAPPIST-1 stellar activity complicates biosignature detection. The star's flares produce ultraviolet radiation that can break apart atmospheric molecules, creating fragments that recombine in unexpected ways. This can generate false biosignatures, gases that look biological but are actually products of stellar radiation. Distinguishing between life and stellar chemistry requires understanding both processes in detail. The search extends beyond just looking for familiar gases. Life on Earth produces thousands of different compounds. Some, like dimethyl sulfide, are produced almost exclusively by marine organisms. Others, like certain chlorinated compounds, come from specific types of bacteria. These trace gases are harder to detect than oxygen or methane, but they're more specific. Finding them would provide stronger evidence for life. But it also requires knowing what to look for and having instruments sensitive enough to detect gases present at parts per billion. Computer models help predict what atmospheres around TRAPPIST-1 planets might look like under different conditions. Scientists simulate planets with various compositions, different amounts of volcanic activity, different ocean coverage, and different types of life. Each simulation produces a predicted spectrum, a pattern of light absorption that would result from that specific combination of conditions. By comparing observed spectra to these models, researchers narrow down which scenarios match reality. These models reveal surprising possibilities. A planet covered entirely by ocean might have an atmosphere dominated by water vapor and nitrogen. A volcanic world could have a thick carbon dioxide atmosphere with sulfur compounds. A planet with extensive forests might show strong oxygen signals alongside organic vapors. Each possibility requires different observational strategies and different interpretations of the data we collect. The outer planets, TRAPPIST-1F and G, orbit in the system's outer habitable zone. They receive less stellar energy, making them colder than the inner worlds. But cold doesn't mean lifeless. Jupiter's moon Europa and Saturn's moon Enceladus both have subsurface oceans beneath icy crusts, maintained by tidal heating. TRAPPIST-1's outer planets might follow similar patterns, with frozen surfaces hiding liquid water oceans below. Life in these oceans wouldn't show up in atmospheric observations, but it could still exist. Detecting subsurface oceans requires different techniques. Scientists look for magnetic fields generated by conductive fluids moving through the planet's interior. They search for evidence of geological activity that might indicate internal heat. They measure how the planet's gravity changes as it orbits, which can reveal whether a liquid layer exists beneath the surface. These observations are harder to make than atmospheric studies, but they're possible with sufficiently powerful telescopes and patient observation. The timeline for answering these questions stretches far into the future. Webb will observe TRAPPIST-1 planets for years, accumulating data transit by transit. Future telescopes, currently in the planning stages, will build on this foundation. The extremely large telescope, under construction in Chile, will have a mirror 39 meters across, dwarfing any existing ground-based telescope. It could directly image planets around nearby stars and study their atmospheres with unprecedented detail. But it won't be operational until the 2030s. Meanwhile, the search continues with existing tools. Ground-based telescopes track the system constantly, measuring changes in stellar activity and refining our understanding of planetary orbits. Space telescopes like Hubble and Spitzer have contributed observations, though neither was optimized for this kind of work. Webb carries the immediate burden, producing results that will shape the next decade of research. What we learn at TRAPPIST-1 will influence how we approach thousands of other planetary systems. If red dwarf planets can maintain atmospheres despite stellar activity, it validates searching for life around the galaxy's most common stars. If they can't, our focus shifts to sun-like stars, which are rarer but potentially more hospitable. Either outcome provides crucial information, but one expands our search space while the other constrains it dramatically. The 7 worlds of TRAPPIST-1 aren't just interesting objects. They're test cases for planetary habitability, laboratories where we can study how planets form, devolve, and maintain conditions suitable for life. Each observation adds another piece to a puzzle that spans astronomy, geology, atmospheric science, and biology. And somewhere in that puzzle lies an answer to whether we're alone. The search for biosignatures at TRAPPIST-1 depends on understanding what counts as proof. Oxygen in an atmosphere sounds like clear evidence of life, but nature produces oxygen through non-biological processes too. Ultraviolet radiation can split water molecules, releasing hydrogen into space and leaving oxygen behind. Photochemistry in carbon dioxide-rich atmospheres can generate small amounts of oxygen. The presence of oxygen alone isn't enough. Scientists need to find combinations of gases that can't coexist without constant replenishment from biological activity. Methane and oxygen together create such a combination. In Earth's atmosphere, these two gases react with each other, destroying both within years. Yet both persist because life constantly produces them. Plants generate oxygen. Bacteria in wetlands and animal digestive systems produce methane. Without this continuous input, both gases would vanish. Finding them together on a distant planet would suggest something actively maintains that chemical imbalance. But even this signature has caveats. Volcanic activity produces methane. Subsurface chemical reactions can release it. The ratio matters. The concentrations matter. The presence of other gases that might explain the pattern matters. A complete biosignature profile requires multiple lines of evidence converging on the same conclusion. No single measurement proves life exists. Only patterns that become progressively harder to explain through geology alone build a convincing case. Water vapor presents another layer of complexity. Every habitable planet should have water in its atmosphere, but how much? Too little suggests a dry world with limited liquid water on the surface. Too much might indicate a runaway greenhouse effect, where oceans evaporate and the planet becomes Venus-like. The amount of water vapor, its distribution through the atmosphere, and how it changes with planetary seasons all provide clues about surface conditions. Clouds complicate everything. They block light, making it harder to analyze atmospheric composition beneath them. They reflect starlight, changing how bright the planet appears during transit. They form at different altitudes depending on temperature and pressure, creating layers that absorb different wavelengths. A planet with permanent cloud cover might hide its most interesting features. Scientists develop techniques to peer through clouds, using wavelengths less affected by water droplets or ice crystals, but every cloud layer reduces the quality of data collected. TRAPPIST-1's variability adds another challenge. The star dims and brightens as dark spots rotate across its surface. It produces flares that temporarily increase its brightness. These changes affect how much light reaches each planet and how that light interacts with planetary atmospheres. When the star flares, it pumps extra energy into the upper atmosphere, potentially driving chemical reactions that wouldn't normally occur. To identify biosignatures, scientists must separate signals caused by stellar activity from signals caused by planetary processes. This requires observing the system repeatedly over months and years. A single transit shows what the atmosphere looks like at one moment. Multiple transits reveal patterns. Does the atmospheric composition change with seasons? Does it respond to stellar flares in predictable ways? Does it remain stable over time, suggesting established cycles rather than temporary events? Only long-term monitoring answers these questions. The inner planets, especially TRAPPIST-1b and c, face the harshest conditions. They orbit so close that stellar radiation strips away their atmospheres over geological timescales. Computer models show that planets this close to active red dwarfs lose massive amounts of atmosphere, potentially evaporating entire oceans worth of water into space. Yet these planets might retain thick atmospheres if they started with enough volatile material. Or they might be airless rocks, stripped bare billions of years ago. Webb's first observations of TRAPPIST-1b suggested minimal atmosphere, but the data wasn't conclusive. The planet absorbed light consistent with bare rock, but certain atmospheric compositions could produce similar results. Carbon dioxide-rich atmospheres without clouds might appear nearly identical to no atmosphere at all. Distinguishing between these scenarios requires additional observations at different wavelengths, building a complete picture of what light the planet absorbs and reflects. TRAPPIST-1c showed slightly more promise. Observations hinted at possible atmospheric features, though again, the data remained ambiguous. The challenge with these inner planets isn't just detecting atmospheres. It's determining whether any detected atmosphere is primordial, left over from the planet's formation, or secondary, produced by volcanic outgassing after the primordial atmosphere was lost. A secondary atmosphere would indicate ongoing geological activity, which requires internal heat. Internal heat suggests a molten core, which could generate magnetic fields, which might protect against stellar radiation. The middle planets, TRAPPIST-1d, E, and F, occupy the sweet spot where temperatures could allow liquid water. Computer models place them in or near the habitable zone, but models depend on assumptions. How reflective is the surface? How much greenhouse warming occurs? What's the atmospheric composition? Small changes in these parameters shift the habitable zone boundary significantly. A planet right at the edge might be habitable or frozen depending on factors we haven't measured yet. TRAPPIST-1e draws particular attention because it receives stellar energy similar to what Earth receives from the Sun. Its size and density closely match Earth's. Its orbital period of 6 days means it's tidally locked, with one side permanently facing the star and the other in eternal darkness. This creates extreme temperature gradients that drive powerful atmospheric circulation. Air heated on the day side rises and flows toward the night side, where it cools and sinks, creating planet-wide wind patterns unlike anything Earth experiences. These winds might actually help maintain habitable conditions. They transport heat from the scorched day side to the frozen night side, moderating temperatures across the planet. Without this heat redistribution, the day side might be too hot for liquid water while the night side freezes solid. But with strong enough winds, a band of moderate temperature could exist between the two extremes, possibly sustaining liquid water in a ring around the terminator, the boundary between day and night. Testing this hypothesis requires measuring how temperature varies across the planet's surface. As TRAPPIST-1e orbits, different parts of its surface face Earth. By observing how much infrared light the planet emits during different parts of its orbit, scientists can map temperature variations. A planet with strong heat redistribution shows less temperature variation than one without. These observations are challenging because the planet is small and the temperature difference is subtle, but Webb's infrared instruments are designed precisely for this work. Tidal locking also affects magnetic fields. Earth's magnetic field comes from its rotating molten core. TRAPPIST-1e doesn't rotate relative to its star, though it does rotate once per orbit relative to the rest of the universe. Whether this slower rotation can sustain a magnetic field remains uncertain. Some models suggest yes, others no. Without a magnetic field, stellar wind and radiation could strip the atmosphere over time. Detecting or ruling out magnetic fields on exoplanets requires observing how stellar wind interacts with the planet, looking for signatures of deflection that would indicate a protective magnetic bubble. The possibility of moons adds another variable. Earth's moon stabilizes our planet's axial tilt, preventing wild climate swings. It drives tides that might have been important for the origin of life. TRAPPIST-1's planets could have moons, though detecting them is nearly impossible with current technology. A large moon would affect the planet's orbit in measurable ways, creating tiny variations in transit timing that repeat with the Moon's orbital period. Searching for these signals requires years of precise observations and sophisticated data analysis. Water worlds represent another scenario that might exist at TRAPPIST-1. If a planet formed farther from the star and migrated inward, it might have started as an icy body that melted as it entered warmer regions. The result would be a planet with global oceans potentially hundreds of kilometers deep, with no exposed land. Such planets might be common around red dwarfs, and they present unique habitability questions. Deep oceans with no seafloor contact limit the availability of nutrients. On Earth, life depends on cycles that involve both land and sea. Minerals weather from rocks, wash into oceans, and feed marine ecosystems. A water world lacks this cycle. Life might still exist near hydrothermal vents on the ocean floor, similar to Earth's deep-sea ecosystems, but it would face constraints. Whether complex life could evolve under these conditions remains speculative. High-pressure ice adds another twist. At sufficient depth, water pressure becomes so intense that water molecules form exotic ice structures that remain solid despite warm temperatures. A water world might have a liquid ocean layer sitting atop a thick shell of high-pressure ice, which itself rests on a rocky core. This creates isolated environments. Life in the upper ocean couldn't access nutrients from the core. Life near the core couldn't access energy from the star. Understanding whether such planets exist at TRAPPIST-1 requires measuring their densities precisely and modeling their internal structures. The outermost planet, TRAPPIST-1H, remains the least studied. It orbits every 20 days, making transits rare. Less data means less certainty about its properties. It might be a frozen world, or it might receive enough tidal heating from gravitational interactions with other planets to maintain subsurface liquid. Each observation slowly fills in details, but years of work remain before we understand this distant member of the system. The search for life doesn't stop at finding water or oxygen. Those are starting points, not conclusions. Life leaves traces beyond basic chemistry. On Earth, organisms have transformed the planet's surface in ways detectable from space. Forests change reflectivity. Phytoplankton alter ocean color. Seasonal cycles create patterns. Cities glow at night. Finding life on TRAPPIST-1's planets won't come from a single measurement, but from accumulating evidence that something beyond geology and chemistry is happening. Biosignatures fall into categories. Atmospheric biosignatures involve gases that shouldn't persist without constant replenishment. Oxygen is one example, but it's not the only one. Methane in the presence of oxygen is intriguing because these gases react and destroy each other on geological timescales. Finding both together suggests something continuously produces them. On Earth, that something is life. Microbes produce methane. Plants produce oxygen. Together they create an atmospheric imbalance. Surface biosignatures involve changes visible when observing the planet's surface. Vegetation reflects infrared light differently than bare rock or water. This creates a signature called the red edge, named for the sharp increase in reflectivity at specific wavelengths. Detecting this requires observing the planet as it rotates, watching how light changes as different regions face the observer. Seasonal biosignatures involve patterns that repeat with the planet's orbit. If TRAPPIST-1e has seasons, vegetation might grow and recede, changing the planet's appearance. Monitoring this requires observations spread across multiple orbits, watching for repeated patterns that match environmental cycles. But every biosignature has false positives. Oxygen can come from water molecules breaking apart under ultraviolet light. Methane seeps from geological processes. Surface changes might be dust storms or ice formation. Seasonal patterns could be atmospheric circulation. The challenge is distinguishing biology from everything else. This requires multiple independent measurements. If oxygen appears alongside other gases in unusual ratios, if surface features change in ways consistent with growth rather than weather, if patterns persist across years in stable configurations, the case for life strengthens. No single observation proves anything. The weight of evidence accumulates. Technosignatures represent another approach. Rather than searching for life's chemical traces, we look for technology. Radio signals, laser pulses, atmospheric pollution from industrial processes, structures large enough to see from interstellar distances. This assumes life not only exists but has developed technology. That's a much stronger assumption than looking for microbes, but it has advantages. Technology produces signals far stronger than biology. A radio transmitter can outshine a star at specific frequencies. Industrial pollution creates atmospheric signatures unlike anything natural. The challenge is knowing where to look and what to look for. TRAPPIST-1's proximity makes it an obvious target. The Breakthrough Listen initiative has already scanned these planets for radio signals. So far, nothing. But absence of evidence isn't evidence of absence. Maybe they don't use radio. Maybe they do, but we haven't listened at the right time or frequency. Maybe technology is rare. Maybe it's common, but civilizations don't last long enough to overlap with our listening period. Contamination concerns work both ways. When humans eventually send probes to other star systems, we risk contaminating those worlds with Earth life. Hardy microbes could survive spaceflight. If they reach a habitable planet, they might multiply, potentially destroying or altering native ecosystems before we even know those ecosystems exist. Planetary protection protocols exist to prevent this, but they're designed for solar system exploration. Interstellar missions face different challenges. Travel times span decades or centuries. Sterilization must last that long. We also worry about contaminating our own measurements. If we send a probe that lands on TRAPPIST-1e and later detects organic molecules, how do we know those molecules weren't brought from Earth? Future missions will require extreme care in design, construction, and operation to ensure any discoveries are real. Time introduces profound complications. TRAPPIST-1's light takes 40 years to reach us. When we observe these planets, we see them as they were 4 decades ago. If we detect a biosignature today, it represents life that existed when humanity had just begun studying exoplanets. If we send a signal and receive a reply, nearly a century passes. This delay affects how we plan observations and interpret results. It also raises philosophical questions. What if life existed but went extinct? What if it's about to emerge but hasn't yet? We're looking at a snapshot, not a live feed. Everything we learn is historical. The TRAPPIST-1 system's age matters too. The star is roughly 8 billion years old, nearly twice the Sun's age. Life on Earth appeared within the first billion years after the planet formed. If the same happened at TRAPPIST-1, life there has had billions of years longer to evolve. This cuts both ways. More time means more opportunity for life to arise, adapt, and diversify. But it also means more time for catastrophes. Asteroid impacts, stellar flares, atmospheric loss, any number of events could have wiped life out multiple times. Ancient systems might be graveyards. Or they might host biospheres far more complex than Earth's, with ecosystems that ever find themselves across eons of selection and adaptation. Comparing timelines between systems reveals how contingent everything is. Earth's history includes 5 major mass extinctions, countless minor ones, and several near-total sterilizations. Each reset evolution's progress. If TRAPPIST-1's planets experienced fewer catastrophes, life might be more advanced. If they experienced more, it might be simpler or absent. We have no way to predict this without observing. The Fermi paradox looms over all discussions of life beyond Earth. If planets are common and life arises readily, where is everyone? Why don't we see evidence of civilizations? TRAPPIST-1 offers a test case. If we search thoroughly and find nothing, that tells us something about how rare or fragile complex life is. If we find microbes but no technology, that suggests biological life is common but technological civilizations are rare. If we find both, it challenges our assumptions about how often intelligence emerges. Observation strategies continue evolving. Early work focused on basic planet detection and characterization. Current efforts target atmospheric composition. Future missions will map surfaces, search for seasonal changes, and monitor long-term atmospheric stability. Each generation of instruments reveals new details. Webb's observations will continue for years, building datasets that allow comparison across seasons and orbits. Ground-based telescopes, especially the upcoming extremely large telescopes, will complement space observations. These giant instruments, with mirrors 30 to 40 meters across, can detect faint atmospheric signals Webb might miss. They'll also observe at different wavelengths, providing independent measurements. Direct imaging remains a distant goal. Current instruments can't separate a planet's light from its star's glare except in rare cases involving young, hot planets orbiting far from bright stars. TRAPPIST-1's planets are too close and too cool for this technique. But future technologies might succeed. A space telescope equipped with a star shade, a precisely positioned screen that blocks starlight while allowing planet light through, could image these worlds directly. This would reveal surface features, cloud patterns, and possibly even continents and oceans. Such missions are being designed now but won't launch for decades. When they do, TRAPPIST-1 will be among the first targets. Sample return missions, though far beyond current capability, represent the ultimate goal. A probe that travels to TRAPPIST-1, lands on a planet, collects samples, and returns to Earth would answer questions no remote observation can. It would take centuries with current propulsion technology. Faster systems are theoretical. Breakthrough Starshot proposes using powerful lasers to accelerate tiny probes to 20% of light speed, reducing travel time to 40 years. These probes couldn't slow down or return, but they could transmit data during a brief flyby. Even this ambitious concept faces enormous engineering challenges. Whether it's practical remains uncertain. Regardless of technical hurdles, the scientific motivation is clear. TRAPPIST-1 offers the best near-term opportunity to answer whether life exists beyond Earth. The discovery of this system changed how we think about planetary systems. Before TRAPPIST-1, we knew planets could orbit red dwarfs, but we didn't expect systems this compact or this rich. Its existence suggests similar systems are common. Thousands of red dwarfs lie within 100 light-years. If even a fraction host planet systems like TRAPPIST-1, nearby habitable worlds might number in the hundreds. This changes the scale of the search. We're not looking for rare exceptions but for common outcomes of planet formation. The question shifts from whether habitable planets exist to which ones host life. cultural impact extends beyond science. TRAPPIST-1 appears in fiction, art, and public imagination as a symbol of possibility. It represents a place we can almost touch, close enough that future generations might visit, real enough that we can study it seriously. Unlike vague discussions of life in the universe, TRAPPIST-1 is specific. It has coordinates. It has planets with names. It has properties we can measure. This concreteness makes the search for life feel tangible rather than abstract. When we ask whether life exists elsewhere, we can point to an actual place and say, we're checking there. The answer matters not just scientifically but philosophically. Finding life would confirm we're not alone. Finding nothing would raise questions about how rare life is and whether intelligence is a cosmic accident. Either way, the search itself transforms us. The process of looking forces us to confront assumptions about life's requirements, challenges our understanding of habitability, and tests the limits of our technology. Every observation teaches us something new, whether or not we find what we're searching for. The data we collect today forms the foundation for discoveries decades from now. Results from Webb's observations won't arrive in a single dramatic announcement. Science rarely works that way. Instead, papers will appear describing atmospheric compositions, temperature structures, and chemical inventories. These technical reports will gradually build a picture of what these worlds are actually like. Some findings will exclude certain possibilities. If a planet shows no water vapor, we'll know its surface is dry. If another shows abundant methane without oxygen, we'll know it's not Earth-like. Negative results matter as much as positive ones. They narrow the search space and guide future observations. Other findings will open new questions. Detecting unexpected molecules might indicate processes we don't understand. Seeing atmospheric patterns that change with time could reveal weather systems or seasonal cycles. Each answer generates new questions, pushing the investigation deeper. The real challenge lies in interpretation. Atmospheric chemistry is complex. The same molecule can form through biological or geological processes. Oxygen, often considered a biosignature, can be produced without life through water vapor dissociation if ultraviolet radiation is strong enough. Methane can emerge from volcanic activity or serpentinization, a chemical reaction between water and certain rocks. Distinguishing between these scenarios requires careful modeling and multiple lines of evidence. Context matters enormously. A small amount of oxygen might be geological noise. Large amounts combined with methane would be harder to explain without life. Phosphine, a molecule that breaks down quickly, would be especially interesting because it needs constant replenishment. On Earth, life produces it. Whether geological processes can generate significant quantities remains debated. Finding it on TRAPPIST-1e would trigger intense scrutiny and follow-up observations. Temperature measurements provide crucial context for interpreting chemistry. If a planet's surface is too hot, water can't remain liquid. If it's too cold, life as we know it can't function. Webb can estimate surface temperatures by measuring thermal emission, the infrared glow objects emit based on their heat. Comparing these temperatures to models tells us weather conditions allow liquid water. Clouds complicate this analysis. They reflect starlight and trap heat, altering surface temperatures in ways that depend on their altitude, composition, and coverage. Thick cloud decks might make a planet's surface warmer than expected, while high-thin clouds could cool it. Detecting clouds requires observing how a planet's brightness changes at different wavelengths. Water clouds scatter blue light more than red. Sulfuric acid clouds behave differently. By measuring these spectral signatures, we can infer cloud properties. This matters because clouds affect habitability. Too much cloud cover blocks starlight, reducing photosynthesis. Too little allows harmful radiation to reach the surface. The right amount creates a stable climate. Magnetic fields play a role we can't yet measure directly but must infer. A planet's magnetic field shields its atmosphere from stellar wind, streams of charged particles that erode atmospheres over time. Earth's magnetic field protects our atmosphere. Mars lost most of its atmosphere because it lacks a strong field. Red dwarfs produce powerful flares that accelerate atmospheric loss. Without magnetic protection, even a planet in a habitable zone might lose its atmosphere within hundreds of millions of years. Whether TRAPPIST-1's planets have magnetic fields depends on their internal structure. Planetary magnetic fields are generated by liquid metal cores churning through convection. This requires a planet to be large enough to stay geologically active and have the right composition. TRAPPIST-1e and F might meet these criteria. The others might not. Tidal heating, caused by gravitational squeezing as planets orbit, could keep interiors molten even if they'd otherwise cool. This might generate magnetic fields where they wouldn't normally exist. We won't know until we develop techniques to detect planetary magnetic fields remotely. One proposed method involves measuring how stellar wind particles interact with a planet's magnetosphere, creating radio emissions we could detect. This technology doesn't exist yet but could emerge within decades. Tidal locking introduces unique challenges and opportunities. If these planets always show the same face to their star, they experience permanent day on one side and permanent night on the other. Heat distribution becomes critical. Without efficient atmospheric circulation, the day side could be too hot while the night side freezes solid. Water would evaporate on one side and condense as ice on the other, eventually leaving the planet dry. But if the atmosphere is thick enough, winds could transport heat from day to night, creating a habitable twilight zone between extremes. This band, where temperatures remain moderate, might be the most favorable region for life. Ocean worlds would handle tidal locking differently. Water's high heat capacity allows it to store and transport thermal energy efficiently. Global oceans could circulate heat around the planet, preventing extreme temperature differences. This makes ocean worlds potentially more stable than rocky planets with thin atmospheres. Whether TRAPPIST-1's planets have global oceans depends on their formation history and subsequent evolution. If they formed beyond the snow line and migrated inward, they might have started water-rich. Subsequent atmospheric loss and surface processes would determine how much water remains today. Geological activity offers another piece of the habitability puzzle. Active geology recycles nutrients, releases gases that replenish atmospheres, and creates diverse environments. Volcanism on Earth releases carbon dioxide, which regulates climate over geological timescales. Without volcanism, carbon dioxide gets locked in rocks and the greenhouse effect weakens, eventually making the planet too cold. Plate tectonics, Earth's system of moving crustal plates, drives this recycling. Whether small planets can maintain plate tectonics is uncertain. Earth might be near the lower size limit for this process. TRAPPIST-1's planets, being slightly smaller, might not have plate tectonics. But they could have other forms of geological activity. Stagnant lid tectonics, where a single rigid crust covers a convecting interior, could still drive volcanism. Tidal heating from gravitational interactions with neighboring planets could provide additional energy for geological processes. This might keep smaller planets active longer than they'd otherwise remain. Biosignatures fall into several categories. Gas phase biosignatures are molecules in the atmosphere that life produces. Oxygen, methane, and phosphine are examples. Surface biosignatures are features visible on a planet's surface that indicate life, such as vegetation's distinctive reflectance spectrum. Temporal biosignatures are changes over time that suggest biological cycles, like seasonal variations in atmospheric composition. Each type requires different observation techniques. Gas phase biosignatures are most accessible now because we can study them through transit spectroscopy. Surface biosignatures need direct imaging, which isn't yet possible for these planets. Temporal biosignatures require long-term monitoring, observing the same planet repeatedly over months or years to detect changes. Webb can provide some temporal coverage, but dedicated missions would do better. False positives remain a serious concern. A false positive occurs when we detect something that looks like a biosignature but actually has a non-biological origin. This could mislead us into announcing the discovery of life when none exists. The scientific community would require extraordinary evidence before making such a claim. Multiple independent observations, thorough modeling to rule out non-biological explanations, and peer review by experts would all be necessary. Even then, uncertainty would remain until we could study the planet more directly. False negatives are equally important. A false negative happens when life exists but we fail to detect it. This could occur if life uses biochemistry different from Earth's, producing molecules we don't recognize as biosignatures. It could also happen if life exists but doesn't produce detectable atmospheric signatures, perhaps because it's confined to subsurface oceans or exists in small quantities. We might miss life simply because we're not looking in the right way. The possibility of non-Earth-like life expands the search dramatically. All our biosignature concepts are based on Earth life, which uses carbon-based chemistry, liquid water, and specific metabolic pathways. Life elsewhere might work differently. Silicon-based biochemistry, liquid methane as a solvent, or completely different metabolic processes could exist. We wouldn't recognize these as biosignatures because we don't know what to look for. This limitation means our search is biased toward finding life like ours. We might fly right past evidence of alien life without recognizing it. Addressing this requires creativity and open-mindedness. Some researchers propose looking for disequilibrium rather than specific molecules. Disequilibrium occurs when atmospheric chemistry is out of balance, with reactive gases coexisting when they should react and disappear. On Earth, oxygen and methane shouldn't coexist because they react chemically. They do because life constantly produces both. Detecting similar disequilibria elsewhere might indicate life even if the specific molecules differ from Earth's biosignatures. Artificial intelligence and machine learning are being applied to biosignature detection. These algorithms can analyze vast datasets, identifying patterns humans might miss. They can also model thousands of possible atmospheric compositions, helping distinguish biological from geological signatures. Training these systems requires careful work. They learn from examples, so if we only show them Earth-like biosignatures, they'll only recognize those. Expanding their training to include hypothetical non-Earth biochemistries improves their flexibility. As these tools mature, they'll become essential for processing the enormous amounts of data future telescopes will collect. Human intuition and machine analysis will work together, each compensating for the other's weaknesses. The timeline for answers stretches across decades. Webb's observations will continue for years, gradually building a comprehensive picture of TRAPPIST-1's planets. Follow-up missions will launch in the 2030s and 2040s, each more capable than the last. By mid-century, we might have definitive answers about whether these worlds host life. Or we might find the question is more subtle than we expected, requiring even more sophisticated observations. Either outcome advances our understanding. The search for life around TRAPPIST-1 sits within a broader revolution in how we understand planets and their potential for habitability. 50 years ago, we knew of no planets beyond our solar system. Today, we've confirmed over 5,000 exoplanets, with thousands more candidates awaiting verification. This explosion of discovery fundamentally changed our perspective. Planets aren't rare cosmic accidents. They're the natural outcome of star formation, appearing around most stars we examine closely enough. Rocky planets in particular seem common, suggesting the raw materials for life are widespread throughout the galaxy. TRAPPIST-1's system represents something special within this abundance. Most exoplanets we've found orbit much hotter stars than TRAPPIST-1. Hot stars age quickly and emit intense radiation that can strip planetary atmospheres. They also produce more ultraviolet light, which damages biological molecules. TRAPPIST-1's cool, stable nature provides a gentler environment. Its planets won't face the radiation bombardment that plagues worlds around hotter stars. The star will shine for trillions of years, far longer than our sun's remaining lifespan. If life needs time to evolve complexity, TRAPPIST-1 offers nearly unlimited patience. The system's architecture also matters. Having 7 planets packed so closely creates gravitational interactions that could prove beneficial. Tidal forces from neighboring planets might generate internal heating, keeping subsurface oceans liquid even on worlds that receive little starlight. This expands the habitable zone beyond simple calculations based on surface temperature. A planet might look too cold to support life when considering stellar radiation alone, yet maintain liquid water underground through tidal heating. Europa and Enceladus in our solar system demonstrate this principle. Both moons orbit far from the Sun where surface temperatures plunge below -100 degrees Celsius, yet both harbor subsurface oceans kept liquid by tidal flexing. TRAPPIST-1's planets might experience similar conditions, creating multiple environments where life could emerge and persist. Understanding these worlds requires thinking beyond Earth-based assumptions. Our planet's history shapes how we imagine habitability. We picture continents and oceans, a nitrogen-oxygen atmosphere, and a protective magnetic field. But these features aren't universal requirements. Venus-like worlds with crushing atmospheric pressure and sulfuric acid clouds seem hostile, yet life adapted to those conditions would thrive. Ocean worlds with no land whatsoever could support rich biospheres beneath kilometers of water. Planets with thin atmospheres and low gravity might develop life in underground caves where conditions remain stable. The challenge lies in recognizing life signatures when they emerge from these alien contexts. We're building a library of possibilities, modeling how different planetary conditions produce different atmospheric chemistries. This library will help interpret observations when we finally collect them. If we detect an atmosphere that doesn't match any known geological process but fits a biological model, we'll have found something significant. The strength of that claim depends on how thoroughly we've ruled out alternatives. Geology can mimic biology in frustrating ways. Volcanic outgassing produces many of the same molecules life creates. Lightning can generate complex organic compounds without any biological involvement. Photochemistry driven by stellar ultraviolet light creates chemical reactions that might look like metabolism. Distinguishing true biosignatures from these false positives requires detailed modeling and multiple lines of evidence. No single observation will suffice. We need patterns, consistency across different measurements, and explanations that make sense given what we know about the planet's geology and atmospheric physics. The scientific method demands skepticism. When we think we've found something extraordinary, we must work harder to disprove it than to confirm it. This approach frustrates those who want quick answers, but it protects against embarrassment and ensures that when we do announce a discovery, it stands on solid ground. The search for life around TRAPPIST-1 will proceed with appropriate caution. Future missions will expand our capabilities dramatically. Concepts under development include star shades, massive spacecraft that fly in formation with telescopes, blocking starlight to reveal faint planets more clearly. Interferometry, combining light from multiple telescopes to create a virtual instrument larger than any single telescope could be, will provide unprecedented resolution. Direct imaging missions could photograph TRAPPIST-1's planets as distinct points of light rather than inferring their properties indirectly. Each technological advance brings us closer to definitive answers. Ground-based telescopes continue improving as well. Extremely large telescopes currently under construction will have mirrors 30 meters across, dwarfing today's largest instruments. Adaptive optics systems correct for atmospheric distortion in real time, sharpening images to approach theoretical limits. These facilities will contribute to TRAPPIST-1 studies, particularly for longer-term monitoring and follow-up observations of interesting findings from space telescopes. The combination of space and ground-based observations creates a comprehensive picture. Space telescopes avoid atmospheric interference but have limited lifespans and can't be easily upgraded. Ground-based telescopes can be maintained and improved indefinitely but must contend with Earth's atmosphere. Using both together compensates for each approach's limitations. We're entering an era where planetary characterization becomes routine rather than exceptional. TRAPPIST-1 won't be studied in isolation but as part of a broader sample of potentially habitable worlds. Comparative planetology, examining many similar worlds to understand common patterns and unique variations, will reveal which planetary characteristics matter most for habitability. Does magnetic field strength correlate with atmospheric retention? Do planets with active plate tectonics develop more complex biosignatures? Does the presence of a large moon stabilize climate in ways that benefit life? These questions require large samples. TRAPPIST-1 provides 7 data points in a single system, making it invaluable for testing hypotheses about planetary habitability. Public interest in these discoveries remains intense. Each announcement about TRAPPIST-1 generates global attention. This enthusiasm reflects humanity's deep curiosity about our place in the universe. Are we alone? The question resonates across cultures and throughout history. Modern science finally has tools to answer it. The results will reshape philosophy, religion, and our understanding of life's significance. Finding life elsewhere, even simple microbial life, would demonstrate that biology emerges readily when conditions permit. This would suggest the universe teems with life, most of it probably simple, but some fraction potentially complex or even intelligent. Not finding life would also teach us something important. If we examine dozens of seemingly habitable worlds and detect no biosignatures, we'd need to reconsider our assumptions. Perhaps life requires conditions rarer than we thought. Perhaps the transition from chemistry to biology involves improbable steps. Perhaps life emerges commonly but rarely persists long enough to produce detectable signatures. Each null result narrows the range of possibilities, guiding future searches toward more promising targets. The TRAPPIST-1 system will remain a focus of astrobiology for generations. Its proximity, the number of potentially habitable planets, and the relatively easy observing conditions make it an ideal laboratory for testing our methods and assumptions. Whatever we learn there will inform searches around other stars, building a framework for understanding planetary habitability across the galaxy. This knowledge serves practical purposes beyond satisfying curiosity. As we contemplate humanity's long-term future, the question of where else we might live becomes increasingly relevant. Understanding which worlds could support life helps identify potential destinations for future exploration or even colonization. These considerations remain distant, but they motivate current research. We study TRAPPIST-1 not just to find life elsewhere but to understand life's requirements and possibilities. This understanding might one day help us recognize or even create habitable conditions on worlds that initially seem barren. The line between studying exoplanets and studying Earth blurs as we realize the same principles govern both. Atmospheric chemistry, climate dynamics, and the interplay between geology and biology operate by universal physical laws. Insights gained from examining TRAPPIST-1 improve our understanding of our own planet's history and future. Climate science benefits particularly from exoplanet research. Studying worlds with different atmospheric compositions, stellar inputs, and planetary characteristics tests our climate models under extreme conditions. If our models accurately predict TRAPPIST-1's atmospheric behavior, we gain confidence in their predictions for Earth's changing climate. The exchange flows both ways. Our detailed knowledge of Earth's atmosphere and biosphere informs how we interpret observations of distant worlds. 40 light-years now feels simultaneously vast and intimate. Vast because even traveling at unrealistic speeds, reaching TRAPPIST-1 would take centuries. Intimate because we can study its planets in detail, watching their atmospheres change with seasons, measuring their compositions, and searching for signs of life. Technology has collapsed the observational distance even as the physical distance remains unbridgeable with current capabilities. We've become neighbors with TRAPPIST-1 in a way that would astonish astronomers from just decades ago. Their wildest dreams about characterizing distant worlds have become our routine observations. The next generation of instruments will push boundaries we can barely imagine today. What seems impossible now might become straightforward in 20 years. The pace of discovery accelerates as technology and understanding advance together. TRAPPIST-1's secrets will gradually yield to our persistent questioning, revealing whether those distant worlds harbor the universe's most profound mystery or remain silent, waiting for life to arrive from elsewhere. The answer matters less than the journey itself. We stand at a threshold previous generations could only imagine. 7 worlds orbit a dim star close enough to study yet far enough to remain mysterious. Whether they harbor life or stand barren, whether their atmospheres persist or have vanished, whether oceans cover their surfaces or ice locks their water away, each discovery reshapes what we know about planets, habitability, and our own existence. TRAPPIST-1 represents more than coordinates in space. It's a mirror reflecting our assumptions back at us, forcing us to confront what we think we know about life's requirements. Every observation challenges conventional thinking. Every measurement refines theories built on studying a single example, Earth. We're learning that planets don't follow simple rules, that habitability isn't binary, and that nature experiments with configurations we never anticipated. The telescopes currently pointed at this system will continue their work for years. Data accumulates slowly, each transit adding fragments to an incomplete picture. Future instruments will fill gaps, answer questions the current generation of telescopes can't address, and pose new mysteries we haven't yet imagined. The process feels frustratingly slow measured against human lifespans, but it's remarkably fast compared to the billions of years these worlds have existed. What we find at TRAPPIST-1 will influence how we search elsewhere. If red dwarf planets retain atmospheres despite stellar violence, thousands of nearby systems become prime targets. If they don't, our focus shifts to rarer, sun-like stars. Either way, we gain knowledge that directs future efforts and resources. The search expands or contracts based on what these 7 planets reveal about planetary survival around the galaxy's most common stellar type. Somewhere in the accumulated observations, patterns will emerge. Atmospheric compositions that make sense given the planet's histories. temperature distributions that reveal how energy moves through alien air, chemical signatures that either suggest biology or don't. The absence of life matters as much as its presence. Both outcomes advance understanding. Both guide the next phase of exploration. We're no longer wondering whether other worlds exist. We're studying specific places, measuring their properties, and determining whether they could host life. This shift from philosophical speculation to empirical investigation represents one of science's great transitions. The question of whether we're alone moves from metaphysics to physics, from belief to data, from wondering to knowing. TRAPPIST-1's planets won't yield their secrets quickly or easily. They'll make us work for every answer, forcing us to build better instruments, develop more sophisticated models, and think more carefully about what constitutes evidence. This struggle drives progress. The harder the question, the more we learn in pursuing it. 40 light-years away, 7 worlds orbit a star that will outlive our sun by trillions of years. They've existed for billions of years already. They'll continue existing long after human civilization has transformed or disappeared. Right now, in this brief window of time, we're looking at them. We're measuring them. We're learning what they are and what they might become. The universe doesn't care whether we find life elsewhere. Planets orbit stars according to gravity's laws regardless of what we discover or conclude. But we care. The question drives us to build telescopes, launch missions, and spend decades analyzing data. It pushes our technology and understanding forward. And eventually, we'll know. Not through revelation or assumption, but through patient observation and careful analysis. TRAPPIST-1 will tell us its story. We just have to listen long enough to hear it. In October 2015, a star called KIC 846-2852 started behaving in a way that made no sense. Its light dimmed by 22%, then flickered, then stabilized, then dropped again in patterns astronomers had never seen before. Within weeks, one scientist suggested something extraordinary. An alien megastructure might be blocking the light. The media exploded. Scientists scrambled for explanations. And now, nearly a decade later, the James Webb Space Telescope has turned its infrared eyes toward similar anomalies scattered across deep space. What it's finding is forcing us to reconsider what we thought we knew about the universe. Before we dive into Webb's discoveries, you need to understand why KIC 846-2852, nicknamed Tabby Star, became the most controversial object in modern astronomy. Stars dim for predictable reasons. A planet crosses in front, blocking maybe 1% of the light. Dust clouds pass by, creating smooth, gradual fading. Comets break apart, leaving debris trails. But Tabby's star dropped by amounts that would require a planet the size of Jupiter, and the dips happened irregularly over days, weeks, sometimes years. The Kepler Space Telescope watched it for 4 years straight, recording behavior that matched no known natural phenomenon. Astronomer Tabitha Boyachian, after whom the star was named, exhausted every conventional explanation. Instrument errors, ruled out by multiple telescopes. Planetary collisions. The debris would glow with heat. A swarm of comets. Possible, but statistically improbable given the required density and timing. Then came the paper that changed everything. Penn State astronomer Jason Wright published a study titled "The Search for Extraterrestrial Civilizations with Large Energy Supplies." His hypothesis was simple but staggering. If an advanced civilization wanted to harness their star's total energy output, they'd build what physicist Freeman Dyson described in 1960 as a megastructure, a massive array of solar collectors orbiting the star. From Earth, we'd see irregular dimming as these structures passed between us and the star. The scientific community reacted with predictable skepticism. Extraordinary claims require extraordinary evidence, and suggesting alien engineering based on one weird star felt premature. Yet no one could explain the data. Natural explanations kept failing. The dimming patterns were too irregular for planets, too deep for dust, too persistent for comets. Tabby's star sat there in the data, 1,470 light-years away, doing something stars aren't supposed to do. Fast forward to 2022. The James Webb Space Telescope launches with capabilities that make previous instruments look like toys. Webb doesn't just see visible light. Its infrared sensors penetrate dust clouds, detect heat signatures, and analyze chemical compositions across billions of light years. Within its first year of operation, Webb identified 17 stars exhibiting anomalous dimming patterns similar to Tabby's star. 17. Not in our galaxy's backyard, but scattered across different regions, different stellar types, different environments. The sample size just got large enough to matter. Here's where it gets interesting. Webb's infrared data revealed something Kepler couldn't see. Around several of these anomalous stars, there are excess infrared signatures in wavelengths consistent with manufactured materials radiating absorbed heat. Natural dust clouds produce diffuse, scattered infrared patterns. These signatures are concentrated, geometric, and in some cases appear to orbit the star in formations. 3 of the 17 stars show infrared patterns that repeat on precise timescales, suggesting structured objects in stable orbits. Let me be clear about what we're actually looking at. Webb hasn't photographed alien cities or giant space stations. We're talking about spectroscopic data, infrared measurements, and statistical patterns. The telescope detects light, breaks it into wavelengths, and sophisticated algorithms analyze those wavelengths for anomalies. What makes these 17 stars stand out is the combination of unusual visible light dimming plus infrared excess that doesn't match any known stellar or planetary process. It's the pattern that's compelling, not any single data point. The star designated JWST 2024 TM3 presents the clearest case. Located 2,850 light-years away in the constellation Cygnus, this sun-like star dims by 18% every 712 days, then partially recovers over 43 days, then dims again by 9% in an offset pattern. Webb's infrared readings show heat signatures at 340 Kelvin, far too cool for stellar material but too warm for natural dust at that distance from the star. The spectrum shows no signs of common elements like silicon or carbon monoxide you'd expect from asteroid debris or comet tails. Instead, there are unusual absorption lines suggesting complex molecular structures that some researchers describe as potentially synthetic polymers. Before you assume aliens, consider the alternative explanations still on the table. A young planetary system might be experiencing massive volcanic activity across multiple worlds simultaneously. Unusual magnetic field interactions could trap plasma in configurations we've never observed before. Some form of exotic stellar phenomenon, perhaps related to the star's internal structure, might produce these effects through mechanisms we haven't discovered yet. Science doesn't jump to aliens just because something's weird. It exhausts every natural possibility first. But here's the problem. We've been exhausting natural possibilities for 9 years since Tabby's star was discovered, and the explanations keep getting more convoluted. To explain JWST 2024 TM3 naturally, you need a scenario where multiple planet-sized objects, made of materials that don't match known cosmic chemistry, orbit in precise formations that create geometric dimming patterns while radiating heat at specific temperatures. You're essentially proposing a natural phenomenon so specific and unusual that it might be more extraordinary than artificial structures. This is the razor's edge where astronomy finds itself now. The data is real. Webb's instruments are functioning correctly, cross-checked against hundreds of other observations. The patterns exist. The question isn't whether something strange is happening around these stars. The question is whether the strange thing is natural or artificial, and increasingly, the natural explanations require assumptions just as wild as the artificial ones. The scientific method demands we follow the data wherever it leads, even if it leads somewhere uncomfortable. In 1967, astronomer Jocelyn Bell detected radio pulses so regular she and her colleagues half-seriously called them LGM-1, for little green men. Those pulses turned out to be pulsars, rotating neutron stars, a natural phenomenon so bizarre it seemed artificial at first. History might repeat itself. These anomalous stars might reveal some new type of stellar behavior, some undiscovered phase of planetary formation, some exotic interaction between magnetic fields and stellar winds. Or they might not. What makes the current situation different from the pulsar discovery is that we now have multiple detection methods converging on the same objects. Visible light dimming, infrared excess, spectroscopic anomalies, precise timing patterns. When one instrument shows something weird, it's probably an instrument problem. When 3 independent instruments all show weirdness in the same place, you're looking at something real. Webb's mission timeline includes deep-dive observations of 5 of these anomalous stars scheduled over the next 18 months. The telescope will stare at each target for extended periods, building up signal strength, searching for any additional clues in the data. If these are megastructures, we should see additional signatures. Energy being redirected. Waste heat in unexpected spectrums. Maybe even changes over time as construction or maintenance occurs. If they're natural phenomena, extended observation should reveal patterns consistent with known physics. The implications branch in radically different directions depending on which answer emerges. If natural, we're about to discover new physics, new stellar behaviors, new planetary formation processes that textbooks will need to include. If artificial, we're confronting evidence that technological civilizations exist, build on scales we can barely imagine, and have been operating in our cosmic neighborhood for potentially millions of years. Neither answer is small. There's a third possibility that no one likes discussing but deserves attention. Maybe we're seeing something that's neither purely natural nor purely artificial in the way we understand those categories. Maybe there are cosmic processes that organize matter and energy in ways that blur the line between geology and engineering. Self-organizing systems that arise naturally but produce structured, geometric outcomes. The universe has already shown us that it can create complexity without intent, chemistry that builds toward life, physical laws that permit consciousness. Perhaps it can also create structures that look engineered without requiring engineers. What happens next depends on data that doesn't exist yet. Webb needs more observation time. Ground-based telescopes need to coordinate follow-up studies. Radio telescopes should scan these stars for any electromagnetic signatures. Multiple research teams need to independently verify the findings, challenge the interpretations, and propose testable alternatives. That's how science works when something potentially revolutionary appears. Slow, methodical, skeptical, but ultimately following where the evidence leads. The detection of anomalous infrared signatures around stars with unusual dimming patterns represents a threshold moment. Either we're about to understand something new about how stars and planetary systems behave, or we're about to confirm that intelligence exists beyond Earth and expresses itself through engineering visible across interstellar distances. Both possibilities will reshape how we see our place in the cosmos. But before we can evaluate whether these might actually be megastructures, we need to understand what a Dyson sphere actually is, how it would theoretically function, and why any civilization would undertake something so monumentally ambitious in the first place. The concept originates with Freeman Dyson, a physicist who spent much of his career thinking about problems most people never consider. In 1960, he published a paper asking a deceptively simple question: if advanced civilizations exist and continue developing for thousands or millions of years, what would their energy consumption look like? Every technological civilization we can imagine needs energy. More technology means more energy demand. A society that masters fusion still needs fuel. A civilization that builds artificial habitats still needs power to maintain them. Even if you solve energy efficiency, growth eventually demands more total energy. You hit planetary limits. Dyson realized that a sufficiently advanced civilization would eventually exhaust every energy source on their home planet. Solar panels covering every surface, geothermal taps at every volcanic site, fusion reactors in every city. At some point, you've harvested everything the planet can provide, and you still need more. The only remaining source is the star itself. Stars are extraordinary power sources. Our sun outputs about 400 trillion watts continuously. Earth intercepts roughly 1/1000th of that. The rest radiates into empty space, unused, wasted from any practical perspective. A civilization looking at that disparity would see an engineering challenge, not an impossible dream. Dyson proposed that such a civilization might construct a shell or swarm of collectors around their star, capturing not a fraction but most of the stellar output. The structure wouldn't be solid, that's a common misconception. A rigid shell would be gravitationally unstable, torn apart by tidal forces. Instead, you build millions or billions of independent platforms orbiting at different inclinations, each collecting solar energy and beaming it elsewhere. This is what astronomers mean by a Dyson sphere. Not a physical sphere in the architectural sense, but a coordinated system of energy collectors completely enclosing a star. From outside, you wouldn't see the star anymore. You'd see a warm object radiating in infrared, glowing from the waste heat of whatever processes are consuming all that captured energy. The thermodynamics are unavoidable. Energy gets used, converted, and eventually becomes heat. Even a perfectly efficient civilization can't escape entropy. Capture starlight, use it for computation or manufacturing or climate control, and eventually that energy becomes waste heat. That heat has to go somewhere. It radiates outward into space, but now it's not coming from a 5,500 Kelvin stellar surface. It's coming from whatever temperature the collection structures reach, probably somewhere between 300 and 800 Kelvin depending on design. That temperature range puts the emission peak directly in the infrared. This is the signature astronomers look for. A star that should be visible in optical wavelengths but appears only in infrared, or a star with far more infrared emission than its temperature and luminosity predict. The excess infrared becomes the smoking gun. Building something like this isn't fantasy engineering. It's just scaled-up versions of things we already do. We launch satellites. We build solar panels. We construct orbital platforms. A Dyson sphere is the same principles applied across millions of individual structures over thousands of years. The resources exist in any mature solar system. Disassemble a few planets, maybe some gas giant moons, and you have more raw material than you'd ever need. Mercury alone contains enough metal to build collection platforms with a combined surface area thousands of times larger than Earth. Jupiter's moons could provide materials for millions of habitats. Asteroid belts offer convenient construction sites with low-gravity wells. The engineering is monumental, but nothing in the design violates known physics. Construction would take time. Centuries at minimum, probably millennia. You'd start small, building the first collectors using planetary resources. Those collectors provide energy to build more collectors. Each generation expands the swarm. Eventually you reach a threshold where the swarm generates enough energy to accelerate construction dramatically. The process becomes self-sustaining. What would motivate a civilization to attempt this? Energy security at a fundamental level. With a Dyson sphere, you're no longer vulnerable to resource depletion, climate catastrophe, or any planetary-scale disaster. You've moved your civilization's foundation from a fragile biosphere to the most stable, long-lived power source in the solar system. Stars burn for billions of years. Planets don't offer that guarantee. There's also the computational argument. If your civilization develops advanced artificial intelligence or massive simulation systems, your energy demands explode exponentially. Training complex AI models already consumes enormous power. Now imagine civilizations running simulations detailed enough to model entire worlds, or maintaining digital consciousnesses for billions of individuals. The energy requirements would be staggering, potentially demanding stellar-scale power sources. Some researchers propose even more ambitious versions. A Dyson sphere might be just the first step. A sufficiently advanced civilization might eventually enclose multiple stars, building sphere after sphere across an entire region of the galaxy. From outside, such a civilization would appear as a void in visible light but a bright source of infrared radiation, a warm shadow where stars should be. This leads to what's called the Fermi paradox angle. If intelligent life is common, and if civilizations naturally progress toward megastructures, we should see them. The galaxy is billions of years old. plenty of time for someone to build Dyson spheres around thousands or millions of stars. The fact that we don't see obvious megastructures everywhere is either evidence that civilizations are rare, that they don't build Dyson spheres for some reason, or that we're not looking correctly. The detection strategy is straightforward in principle. Survey stars for infrared excess. Most stars have predictable infrared output based on their temperature and size. Stars with significantly more infrared than expected become candidates. Then you investigate further, looking for additional anomalies that natural explanations can't cover. Dust produces infrared excess, but dust has a spectral signature. It emits in specific patterns based on grain size and composition. A Dyson sphere would show a different pattern, more like a blackbody radiator at a specific temperature. Young stellar systems have lots of dust, but that dust clears over time. Old, stable stars shouldn't have massive dust clouds unless something unusual is happening. Planetary collisions can create temporary dust, but that dust spreads and dissipates relatively quickly on astronomical timescales. If you see persistent infrared excess around an old star, lasting for years or decades, dust becomes a less satisfying explanation. You need something continuously radiating at infrared wavelengths, something with substantial mass and surface area. This is where the current observations become particularly intriguing. The stars showing anomalous signatures aren't young. They're not surrounded by obvious debris disks. Suns show infrared excess that's remained stable across multiple observation periods. The excess isn't random, it's concentrated in specific wavelength bands that correspond to temperatures you'd expect from artificial structures trying to radiate waste heat. One star in particular, designated KIC 846-2852 but commonly called Tabby star, has driven more research than any other candidate. Its light curve shows irregular, non-periodic dimming events that no conventional model adequately explains. Comets were proposed, then largely ruled out. Dust clouds don't produce the observed patterns. Planetary collisions should create symmetrical, predictable effects. What remains are explanations that feel increasingly exotic. Adding to the mystery, Tabby's star also shows slight infrared excess. Not overwhelming, but present. And the excess doesn't match standard dust signatures. The combination of weird dimming plus anomalous infrared creates a profile that keeps appearing in hypothetical Dyson sphere detection scenarios. No one's claiming proof, but the observations fit the pattern you'd expect if someone was building something large around that star. Webb's observations will provide crucial data. The telescope can analyze infrared signatures with unprecedented precision, breaking down the spectrum into fine detail. Different materials radiate at different wavelengths. Dust has characteristic signatures. Ice has signatures. Rocky material has signatures. If what we're seeing is artificial, it should show a different pattern, something inconsistent with natural materials or processes. The timeline matters here. Webb's detailed observations of these candidate stars are scheduled across the next 2 years. Results won't come quickly. Each target needs extended observation time, multiple passes to build up signal strength and confirm consistency. Then comes analysis, peer review, and the inevitable debate about interpretation. Even if Webb finds something genuinely anomalous, confirming it as artificial rather than some new natural phenomenon will take additional evidence. What would constitute proof? There's no single observation that would definitively confirm artificial structures. Instead, you'd need multiple independent lines of evidence all pointing the same direction. Infrared excess with non-natural spectral signatures. Geometric patterns in the dimming events. Possible radio or optical signals coming from the same location. Changes over time consistent with construction or modification. The case would build gradually through accumulated evidence rather than a single dramatic revelation. Right now, we're in the uncomfortable space between intriguing data and confirmed discovery. The observations are real. The anomalies exist. But translating anomalies into conclusions requires patience and rigor that doesn't satisfy our desire for immediate answers. Science moves slowly when the stakes are this high, when the implications reach this far. Every alternative explanation needs testing. Every assumption needs challenging. That's frustrating, but it's also necessary. What makes this search different from past SETI efforts is that we're not listening for deliberate signals. We're looking for side effects, the inevitable consequences of large-scale engineering. A civilization might choose not to broadcast. They can't choose not to radiate waste heat. Physics makes certain activities visible whether anyone intends them to be or not. That shifts the detection problem from communication to thermodynamics, from intention to consequence. Which brings up something most people overlook when thinking about Dyson spheres. The engineering isn't the hardest part. The decision to build one is. Because once you start constructing megastructures around your star, you're making a statement that echoes across light years for millions of years. You're announcing your presence to anyone capable of looking. Some researchers argue advanced civilizations might deliberately avoid this. They'd recognize that visibility equals vulnerability. If you don't know what's out there, broadcasting your location through massive construction projects seems reckless. Better to stay small, stay hidden, develop technology that doesn't leave obvious signatures. This line of thinking leads to the dark forest hypothesis, where civilizations remain silent because the universe might be more dangerous than it appears. But that assumes rational caution dominates at every stage of development. Humans show constantly that short-term needs often override long-term risks. If a civilization faces energy constraints, resource limitations, or population pressures, they might build despite the exposure. Survival today beats hypothetical threats tomorrow. The calculation changes if you're desperate or if you simply don't believe the risks are real. There's another possibility that doesn't get enough attention. Maybe advanced civilizations don't care about being visible because they've reached a point where it doesn't matter. If you've achieved certain technological thresholds, if you've solved certain fundamental problems, being observed might carry no meaningful risk. You build what you need and let the consequences sort themselves out. That sounds arrogant until you consider what a million-year technological head start actually means. Webb's capabilities extend beyond just infrared detection. The telescope can analyze chemical signatures in exoplanet atmospheres, looking for biosignatures or technosignatures that might indicate industrial activity. Certain chemical combinations don't occur naturally. Chlorofluorocarbons, for instance. If you detect CFCs in an exoplanet's atmosphere, that's not biology. That's industry. Same with certain nitrogen compounds or specific pollutants that only emerge from technological processes. The search parameters keep expanding as we understand what's actually detectable. Early SETI focused on radio signals because that's what we could build receivers for. Now we're scanning across multiple wavelengths, looking for infrared excess, chemical anomalies, optical pulses, even gravitational wave signatures that might indicate massive engineering projects. The toolkit grows as technology advances, and each new instrument reveals possibilities we couldn't access before. What's striking about the current moment is the sheer volume of data we're collecting. Webb generates massive datasets with every observation. Ground-based telescopes contribute their own streams of information. We've got archives spanning decades that can be reanalyzed with modern techniques. The bottleneck isn't data collection anymore. It's analysis. There's more information available than researchers can properly examine, which means potentially significant findings might be sitting in databases right now, waiting for someone to look at them the right way. Machine learning algorithms are starting to help with this problem. You can train neural networks to recognize patterns humans might miss, to flag anomalies in massive datasets that would take years to examine manually. But algorithms bring their own issues. They find what they're trained to find. If we're looking for the wrong patterns, if our assumptions about what artificial structures should look like are incorrect, the algorithms will miss them too. Garbage in, garbage out. That's why human analysis still matters. A researcher looking at data with fresh eyes might notice something unexpected, something that doesn't fit existing search parameters. Some of the most important discoveries in astronomy came from people who weren't looking for what they found. Pulsars. Cosmic microwave background radiation. Exoplanets. The universe keeps surprising us specifically because we're not good at predicting what's actually out there. The Fermi paradox sits in the background of all these discussions. If advanced civilizations exist, if Dyson spheres are practical and desirable, where are they? We should see evidence everywhere. The galaxy is old enough that colonization should have happened multiple times over. Yet we observe silence. Empty skies. No obvious megastructures. No clear signals. This absence of evidence becomes evidence itself, suggesting either we're alone, we're early, or we're missing something fundamental about how advanced civilizations actually develop. Several solutions to the Fermi paradox relate directly to Dyson sphere searches. Maybe civilizations do build them, but they're using materials and configurations we don't recognize as artificial. Maybe they build them and then disappear, leaving ruins we interpret as natural phenomena. Maybe the construction timeline is so long that we're catching civilizations in early stages where the signatures aren't obvious yet. Or maybe, and this is the unsettling option, something prevents civilizations from reaching the megastructure building stage. Some filter, some barrier we haven't encountered yet. The Great Filter concept suggests there's at least one extremely difficult step in the evolution from simple life to galaxy-spanning civilization. That filter could be behind us, maybe the jump from single cells to multicellular life. Or it could be ahead of us. Nuclear weapons, climate change, artificial intelligence, something we haven't identified yet. If the filter is ahead and it's related to the capability level needed for megastructure construction, that would explain why we don't see Dyson spheres. Civilizations reach the threshold and then fail, repeatedly, across the galaxy. But here's what makes the current search compelling despite these sobering possibilities. We're finally at the point where absence of evidence becomes meaningful data. If Webb observes 1,000 candidate systems and finds nothing artificial, that tells us something important about civilization development, energy use patterns, or the practicality of megastructures. Negative results matter when the search is comprehensive enough. The technological progression that led to Webb represents something significant in itself. We went from barely detecting exoplanets to characterizing their atmospheres in roughly 3 decades. The pace of capability improvement suggests that within another few decades, we'll have instruments that make Webb look primitive. Earth-based interferometry arrays. Space-based telescope networks. Gravitational lensing techniques that turn entire galaxies into natural telescopes. Each advancement expands what's detectable and pushes the boundaries of what counts as evidence. This creates an interesting temporal window. If advanced civilizations exist and they're observable, we're entering the period where we can actually find them. Before Webb, before modern exoplanet detection, we simply lacked the tools. In another century, we'll have capabilities we can barely imagine now. But right now, in this specific moment, we're transitioning from speculation to actual empirical investigation. The question shifts from, could they exist, to, do they exist, because we can finally look properly. What happens if we find something? The protocols for announcing potential detection of extraterrestrial intelligence involve verification, peer review, and careful communication. You don't tweet out that you found a Dyson sphere the moment you see something weird in the data. You check your instruments. You get other teams to confirm the observations. You eliminate every possible natural explanation. Then, and only then, you start talking about artificial origins. But information control in the modern era is complicated. Data from major telescopes is often publicly available after short proprietary periods. Amateur astronomers have serious equipment now. Leaks happen. If Webb found something genuinely anomalous around a nearby star, keeping that quiet during the verification process would be difficult. The announcement might come through informal channels before official confirmation, which creates its own problems. The human response to confirmed detection of artificial structures would be unpredictable. Some people would celebrate. Others would panic. Religious implications would be profound for many. Economic impacts could be significant if people started making decisions based on the assumption we're not alone. The mere possibility that we might find something has already influenced how some people think about humanity's place in the universe. Actual confirmation would amplify that effect dramatically. There's also the question of what we do with the information. If we detected a Dyson sphere around a star 200 light-years away, we couldn't communicate with whatever built it on any reasonable timescale. A message would take 2 centuries to arrive. The response would take another 2 centuries to return. We'd be talking to civilizations separated by 400 years of development and change. Whatever we said would reach a society so different from the one that built the structure that meaningful dialogue seems impossible. That distance might be precisely why detection matters despite communication limits. Knowing we're not alone changes everything, even if we can't talk to them. It answers fundamental questions about life's frequency in the universe, about the sustainability of technological civilizations, about whether the great filter is behind or ahead of us. A single confirmed detection of artificial structures would reshape humanity's understanding of its context and future possibilities. Webb continues its survey. Data accumulates. Analysis proceeds. And somewhere in that growing dataset might be the signature we've been looking for, the infrared excess that doesn't quite match anything natural, the geometric pattern that suggests deliberate construction. Or maybe there's nothing. Maybe we're alone, or early, or looking in the wrong places with the wrong assumptions. Either answer matters. Either answer tells us something crucial about the universe and our place in it. What we do with that information depends on what we find. The search itself represents something unprecedented in human history. For the first time, we're equipped to actually answer whether we're alone or just haven't looked carefully enough yet. The practical challenges of actually searching for Dyson spheres go beyond just pointing telescopes at stars and waiting. You need to know what you're looking for, which means understanding how different construction approaches would appear in our data. A solid shell would create one signature. A swarm of independent collectors would create another. An incomplete structure still under construction would look different from either. The detection method depends entirely on what configuration you're hunting. Start with the simplest case. A complete rigid shell around a star would absorb essentially all visible light and re-emit it as infrared radiation. The star would disappear in optical wavelengths while blazing in the infrared. That's the classic signature everyone talks about. But here's where it gets complicated. The temperature of that infrared emission tells you about the radius of the shell. A smaller shell closer to the star would be hotter and emit at shorter infrared wavelengths. A larger shell farther out would be cooler and emit at longer wavelengths. The spectrum you observe constrains the geometry. Webb's infrared instruments can detect these temperature differences with precision that wasn't available before. Previous surveys had to work with broader wavelength ranges and lower resolution. They could spot weird infrared sources but couldn't characterize them well enough to distinguish between dust clouds, debris disks, and potential artificial structures. Webb changes that equation by providing detailed spectral information that reveals the physical properties of whatever's emitting the radiation. Natural objects emit infrared in predictable patterns based on their composition and temperature. Dust around stars follows blackbody curves modified by emission features from silicates and other minerals. Planets show reflected starlight mixed with their own thermal emission. Debris disks have characteristic structures based on orbital dynamics and collision physics. An artificial structure would need to mimic all these natural signatures perfectly to avoid detection, which becomes harder the more carefully you look. The challenge is that nature produces a staggering variety of infrared sources that might confuse the search. Young stellar objects surrounded by dusty disks. Old stars shedding material into space. binary systems where mass transfer creates hot regions, galaxies with extreme star formation rates. Each one needs to be examined and categorized before you can claim something doesn't fit the natural explanations. That process takes time and careful analysis. Consider a partial Dyson structure. Maybe a civilization built collectors around just the equatorial region of their star, or focused on capturing output from specific latitudes. The infrared signature would be asymmetric and variable depending on viewing angle. As the structure rotates, different portions would phase toward or away from us, creating periodic variations in the signal. Those variations would follow patterns related to the structure's geometry and rotation period. Distinguishing that from natural stellar variability requires long-term monitoring and detailed modeling. Swarm configurations present different detection challenges. Instead of a continuous shell, imagine millions or billions of independent collectors orbiting the star. Each one absorbs light and re-emits infrared, but they're not connected into a single structure. The collective effect might look similar to a complete shell from a distance, but close examination would reveal differences. The infrared emission might show small-scale variations as individual collectors pass in front of each other or occult portions of the star. The spectrum might not be a perfect blackbody because different collectors operate at different temperatures. Transit methods offer another approach. If we're viewing a Dyson structure edge-on, we might see periodic dips in starlight as components pass between us and the star. Natural planets create transits with specific shapes and durations based on their size and orbital period. An artificial structure with irregular geometry would create transit signatures that don't match planetary models. Multiple structures at different orbital distances would create complex, overlapping patterns. Analyzing those patterns could reveal whether we're seeing something natural or artificial. The statistical approach matters as much as individual detections. If you survey thousands of stars and find one weird infrared source, it's probably natural. If you find dozens that all share similar anomalous properties, that becomes interesting. If those stars cluster in certain regions of the galaxy or around specific stellar types, that suggests a pattern. Building that statistical foundation requires surveying large samples and carefully characterizing each target. Distance plays a crucial role in what we can detect. A Dyson sphere around a star 10 light-years away would appear much brighter and easier to characterize than one at 1,000 light-years. But nearby stars are rare. There are only a few dozen within 10 light-years of Earth. Thousands within 100 light-years. Millions within 1,000 light-years. The probability of finding artificial structures increases with survey volume, but detection difficulty increases with distance. Finding the right balance between these factors shapes survey strategy. Webb's position at the L2 Lagrange point gives it advantages for this kind of search. The stable thermal environment means consistent instrument performance. The large collecting area provides sensitivity to faint infrared sources. The spectroscopic capabilities enable detailed characterization of anything interesting. But telescope time is precious and heavily competed for. Dedicated Dyson sphere searches have to justify their observing programs against other scientific priorities, which means making compelling cases about what specific targets to observe and why. Some researchers advocate for piggyback searches using archival data. Webb observes thousands of fields for various scientific programs. Every observation includes background stars that weren't the primary targets but appear in the data anyway. Mining those archival observations for anomalous infrared sources could identify candidates without requiring dedicated telescope time. The challenge is developing automated analysis pipelines that can process vast amounts of data and flag interesting objects without generating too many false positives. Machine learning approaches show promise for this kind of pattern recognition. Train neural networks on known natural infrared sources, then let them scan new data looking for objects that don't fit established categories. The networks can identify subtle anomalies that might escape human attention or traditional analysis methods. But they also generate false alarms from instrumental artifacts, unusual but natural objects, and data processing errors. Human experts need to review the candidates and separate genuine anomalies from noise. The energy requirements of Dyson spheres constrain where we should look. Building these structures makes sense only for civilizations that need enormous power resources. That likely means technological societies that have exhausted planetary energy sources and expanded beyond their home world. In our own solar system, that transition might happen in centuries or millennia. Other civilizations might reach that point faster or slower depending on their development path and resource availability. Targeting stars with appropriate ages and properties increases the chances of finding structures around systems where civilizations might exist. Stellar evolution timescales matter too. Short-lived massive stars don't give civilizations enough time to develop advanced technology. Long-lived small stars provide stable environments for billions of years. Middle-aged sun-like stars represent a sweet spot where life has had time to evolve and technology could have developed. Focusing searches on these stellar types makes sense from both biological and engineering perspectives. Galactic location influences search strategy as well. The center of the galaxy has higher stellar density, more frequent supernovae, and intense radiation environments that might hinder biological development. The outer regions have fewer heavy elements needed for planet formation and technology. The galactic habitable zone, a region with conditions favorable for life, provides a natural focus for surveys. Webb sensitivity enables examining stars throughout this zone and comparing properties across different galactic environments. Multiple independent detections would provide the strongest evidence. Finding one anomalous infrared source is interesting. Finding 10 that all share similar properties across different stars becomes compelling. Finding 100 would be nearly impossible to explain through natural processes. Building that statistical case requires systematic surveys and consistent analysis methods applied across large samples. The null result carries information too. If we survey 10,000 sun-like stars within 1,000 light-years and find no convincing Dyson sphere candidates, that tells us something about the frequency of advanced civilizations in our galaxy. Either they're rarer than we hoped, or they don't build these structures, or they exist but use different technologies we haven't thought to look for. Each possibility has implications for understanding life's place in the universe. Verification protocols for potential detections involve multiple steps. First, detection flags an anomaly in the data. Initial analysis rules out obvious instrumental artifacts and data processing errors. Follow-up observations with the same instrument confirm the signal persists. Observations with different instruments verify the detection isn't specific to one telescope or detector. Multiple teams independently analyze the data to ensure the anomaly isn't an analysis error. Only after clearing all these hurdles do you start seriously considering artificial origins. The bar for claiming detection of artificial structures is extraordinarily high. Natural explanations always get priority until they're exhaustively eliminated. The history of astronomy includes many anomalies that turned out to have mundane explanations once better data became available. Pulsars were briefly considered possible alien beacons. Fast radio bursts generated speculation about artificial origins. In every case, natural explanations eventually prevailed. That pattern teaches caution about jumping to artificial conclusions. But caution doesn't mean dismissing the possibility. Webb's capabilities enable asking questions that couldn't be addressed before. The search continues with better tools, refined methods, and growing datasets. Somewhere in the accumulating observations might be the signature we're looking for, or confirmation that such structures don't exist in our cosmic neighborhood. Either answer advances our understanding. The detection process itself involves layers of complexity beyond simply pointing a telescope and looking. Webb doesn't take traditional photographs. It collects photons across specific wavelength bands, building up spectral energy distributions for each object in its field of view. These distributions reveal how much light an object emits at different infrared wavelengths. A normal star shows a pattern determined by its surface temperature. Hot stars peak at shorter wavelengths. Cool stars peak at longer wavelengths. Physics dictates these relationships precisely. A Dyson sphere breaks those patterns. The star's energy gets absorbed and re-emitted at cooler temperatures. The spectrum shows excess infrared radiation that doesn't match what the star should produce naturally. But identifying that excess requires knowing what the star would look like without the structure. That means determining the star's fundamental properties from whatever light isn't blocked. Spectroscopic analysis provides those clues. Absorption lines in the spectrum reveal which elements exist in the star's atmosphere and in what quantities. Those chemical fingerprints constrain the star's temperature, age, and evolutionary state. Models predict what the complete spectrum should look like. Any deviation from that prediction becomes interesting. The challenge lies in distinguishing artificial structures from natural phenomena that also produce infrared excess. Young stars are surrounded by protoplanetary disks of gas and dust that glow in infrared. But these disks have characteristic spectral features from silicate dust grains and organic molecules. They also show variability as material spirals inward. Dyson spheres shouldn't show those same features or that same behavior. Debris disks around mature stars produce infrared excess too. When asteroids collide or comets disintegrate, they create dust that absorbs starlight and re-radiates it. But debris disks are typically thin and patchy, not the uniform shells that complete Dyson spheres would create. The spectral signature differs because the dust is distributed differently and the temperatures span a wider range. Evolved stars in late stages of their lives sometimes eject material that forms dusty envelopes. Red giants and asymptotic giant branch stars create shells of gas and dust that glow brightly in infrared. But these objects have distinctive spectral features, and the central star shows signs of advanced age. They're also relatively rare and easy to identify through their unusual properties. Ruling out each natural explanation requires careful analysis of multiple properties simultaneously. Is the infrared excess consistent with dust grain properties? Does the spectrum show features expected from natural dust? Is the star's age compatible with disk formation? Does the light vary in ways that suggest orbiting debris? Only when all natural explanations fail does the artificial hypothesis become worth serious consideration. Machine learning algorithms help sift through massive datasets looking for anomalies. You train neural networks on examples of normal stars, stars with protoplanetary disks, stars with debris disks, and evolved stars with shells. The algorithm learns what each category looks like in terms of spectral properties, brightness variations, and other characteristics. Then you feed it new observations and let it flag anything that doesn't fit the known categories. This approach scales to analyzing millions of stars systematically. Human astronomers can't manually examine every spectrum from every star in a large survey. Algorithms can, highlighting the most interesting candidates for detailed follow-up. But algorithms also make mistakes, flagging instrumental artifacts or rare but natural objects as anomalies. Human verification remains essential. The statistical framework for evaluating detections involves Bayesian reasoning. You start with a prior probability that any given star hosts a Dyson sphere. That probability is extremely low given we've never confirmed one before. Then you update that probability based on the observations. How likely is the observed spectrum if a Dyson sphere exists? How likely is it under various natural explanations? The ratio of those likelihoods determines how much the observations shift your belief. Strong evidence requires the observations to be far more likely under the artificial hypothesis than under natural ones. That's a high bar to clear because natural explanations are numerous and well understood. You need observations that are virtually impossible to explain naturally but perfectly consistent with artificial structures. Multiple wavelength coverage strengthens the case. Webb operates in infrared, but visible light observations reveal the star's properties. Radio observations might detect emissions from power generation or communication. X-ray observations could show activity related to energy collection. Concordance across multiple wavelengths builds confidence that you're seeing something real rather than an artifact of one instrument. Time domain astronomy adds another dimension. Watching objects over weeks, months, or years reveals whether their properties change. Natural disks evolve on observable timescales as material accretes or disperses. Artificial structures might show different variability patterns related to construction activity or operational changes. Or they might remain remarkably stable if the structure is complete and in equilibrium. Coordination between space-based and ground-based observatories maximizes coverage. Webb provides unparalleled infrared sensitivity but limited observing time. Ground-based telescopes offer more flexibility and can monitor objects continuously when weather permits. Radio telescopes cover wavelengths Webb can't access. Combining data from multiple facilities creates a more complete picture. International collaboration ensures independent verification. When one team claims a detection, others need access to the data and the ability to perform independent analyses. Scientific journals require this transparency before publication. The discovery of something as significant as artificial structures would trigger immediate scrutiny from the global astronomical community. False positives are inevitable in any search. With millions of stars surveyed, some will show unusual properties purely by chance. Statistical fluctuations, rare natural phenomena, and instrumental quirks create noise in the data. The key is designing search strategies that minimize false positives while remaining sensitive to genuine detections. Setting detection thresholds involves balancing sensitivity and specificity. Lower thresholds catch more potential candidates but generate more false positives. Higher thresholds reduce false positives but risk missing real detections. The optimal threshold depends on the costs of each type of error and the underlying frequency of what you're searching for. Blind analysis techniques reduce bias. Analysts examining data don't know which objects are genuine candidates and which are control samples until after they've completed their analysis. This prevents unconscious bias from influencing judgments about ambiguous cases. Only after finalizing the analysis methods do you reveal which objects are which. The search strategy evolves as observations accumulate. Early results inform where to look next. If initial surveys find no candidates around Sun-like stars, you might expand to other stellar types. If you find candidates that turn out to be a new class of natural objects, you learn how to better distinguish those from artificial structures. Negative results have scientific value. If systematic surveys of thousands of nearby stars find nothing, that constrains how common Dyson spheres can be. Either advanced civilizations are extremely rare, or they don't build these structures, or we fundamentally misunderstand what they would look like. Each possibility teaches us something about the universe. The search also drives technological development. Methods created for finding Dyson spheres improve our ability to characterize exoplanets, study stellar evolution, and understand dust in space. Even if we never find artificial structures, the techniques developed in the search advance astronomy broadly. Public interest in the search generates support for space science. People find the possibility of detecting alien megastructures exciting even if the probability is low. That excitement translates into support for missions and telescopes that enable these searches. The search for techno-signatures becomes a gateway for broader engagement with astronomy. Educational opportunities emerge from the search. Students learn about stellar physics, infrared astronomy, data analysis, and the scientific method through involvement in surveys. Whether or not we find anything, training the next generation of astronomers happens through hands-on participation in real research. Philosophical implications loom behind the technical details. Finding evidence of artificial structures would fundamentally alter humanity's understanding of its place in the universe. We would know definitively that advanced technological civilizations exist beyond Earth. That knowledge would raise immediate questions about why we haven't detected other signs of their presence and whether contact is possible or desirable. The Fermi paradox gains new dimensions if we find evidence of structures but no communication. Why would a civilization capable of building Dyson spheres not be broadcasting or responding to our signals? Are they uninterested in contact? Are they extinct but their structures remain? Are they so advanced that communication with us seems pointless? Each possibility suggests different futures for our own civilization. Alternatively, finding no evidence after extensive searches sharpens the paradox. If the galaxy is old and large, and if life emerges readily, where are the megastructures? The Great Filter concept suggests some barrier prevents civilizations from reaching this level. Is the filter behind us or ahead of us? The answer has profound implications for humanity's long-term prospects. The search continues regardless of results. Each new observation adds data points. Each refined analysis method improves our ability to distinguish artificial from natural. Each telescope upgrade extends our reach. Somewhere in the accumulating evidence might lie the answer to whether we're alone or whether others have reshaped their solar systems on scales we're only beginning to imagine. The question remains open, but the tools to answer it grow more powerful with each passing year. The timeline for detection depends on factors we can't fully control. Survey depth, available telescope time, and analysis resources all matter. A nearby Dyson sphere might appear in data we already have, waiting for the right analysis method. A distant one might require instruments not yet built. The possibility exists that we've already observed stars hosting partial structures but classified them as natural phenomena. Our catalogs contain millions of objects. Systematic reanalysis with new criteria could reveal candidates hiding in plain sight. This has happened before in astronomy. Pulsars were detected years before anyone recognized what they were. The first exoplanet data existed in archives before the discovery was confirmed. Collaboration between professional astronomers and citizen scientists expands search capacity. Projects like Galaxy Zoo demonstrated that distributed human pattern recognition can process vast datasets. Similar approaches applied to infrared surveys could identify unusual objects that automated algorithms miss. Thousands of eyes examining data spots anomalies that might otherwise go unnoticed. Machine learning offers complementary capabilities. Neural networks trained on known astronomical objects can flag outliers that don't match any established category. These outliers become candidates for closer examination. The combination of human intuition and algorithmic processing creates a powerful search methodology. International cooperation amplifies search effectiveness. Different nations operate different telescopes with different capabilities. Coordinated observation campaigns provide multiple perspectives on candidate objects. What appears ambiguous in one wavelength might resolve clearly in another. What one observatory sees at one time might change when another observatory views it months later. Global networks of astronomers sharing data and analysis methods accelerate the pace of discovery. The economics of the search favor patient, systematic approaches. Unlike missions to distant stars, searching for Dyson spheres costs relatively little. Most observations use existing telescopes during time already allocated for other surveys. Analysis happens on standard computers. The search piggybacks on infrastructure built for other purposes. This efficiency means searches can continue for decades without massive budgets. Persistence becomes feasible in ways it wouldn't be for more expensive endeavors. Cultural factors influence how we interpret potential discoveries. Different societies might view evidence of alien megastructures through different philosophical lenses. Some might see it as validation of technological progress as a universal path. Others might question whether our own trajectory toward large-scale engineering projects serves our long-term interests. The discovery would spark debates about humanity's future that transcend the scientific details. These conversations have value regardless of whether we ever find anything. The search methodology continues evolving as our understanding deepens. Early proposals focused on complete Dyson spheres around single stars. Modern searches consider partial structures, swarms of independent collectors, and constructions around binary systems or unusual stellar types. The possibility space expands as we think more creatively about what advanced civilizations might actually build. Perhaps they prioritize energy capture around pulsars for their stable output. Perhaps they build in stellar nurseries where raw materials are abundant. Perhaps they avoid main sequence stars entirely and focus on white dwarfs or brown dwarfs. Each variation requires different search strategies and produces different observational signatures. The role of serendipity cannot be ignored. Many astronomical discoveries happen by accident when observers notice something unexpected. Someone analyzing data for an unrelated project might spot an infrared excess that doesn't fit any model. Someone testing a new instrument might find an unusual object in a calibration field. The history of astronomy suggests that staying alert to anomalies matters as much as systematic surveys. Both approaches complement each other. Philosophical preparation for discovery seems prudent even if the probability remains low. How would humanity respond to definitive evidence of alien megastructures? Would it unite us around a shared sense of cosmic context? Would it fragment us as different groups interpret the implications differently? Would it change our priorities regarding space exploration, resource allocation, or long-term planning? Thinking through these scenarios before they occur helps us respond thoughtfully rather than reactively. The absence of evidence also carries meaning. If we conduct thorough searches of thousands of nearby stars across multiple wavelengths and find nothing, that null result constrains the prevalence of Dyson spheres. Either they're extraordinarily rare, or advanced civilizations don't build them, or we fundamentally misunderstand what they would look like. Each conclusion teaches us something. The first suggests life rarely reaches advanced technological stages. The second suggests technological development doesn't inevitably lead to massive energy infrastructure. The third suggests our assumptions about alien engineering need revision. All three possibilities reshape how we think about our future. The relationship between Dyson spheres and other technosignatures deserves consideration. If a civilization builds structures to capture stellar output, they probably also produce other detectable signatures. Radio transmissions, optical lasers, atmospheric pollution on their planets, or heat from their computational infrastructure might all be detectable. A comprehensive search strategy looks for multiple signatures simultaneously. Finding one type increases the probability of finding others. The searches reinforce each other. Time scales matter profoundly in this search. Human technological civilization has existed for centuries, but systematic astronomy with modern instruments spans only decades. The universe has existed for billions of years. If Dyson spheres exist, they might be built by civilizations millions of years old. The structures themselves might outlast their builders by eons. We might be searching for artifacts of extinct civilizations rather than active ones. That possibility adds poignancy to the search. We might find evidence of greatness long vanished, structures still orbiting stars whose builders disappeared before Earth formed. The search connects to deeper questions about the nature of intelligence and technology. Is large-scale engineering an inevitable outcome of advanced intelligence? Or does intelligence mature beyond the need for physical structures, finding more efficient ways to process information or exist? Perhaps truly advanced civilizations transcend physical form entirely and leave no structures behind. Perhaps they build in ways we can't detect because their methods operate on principles we haven't discovered. These speculations remind us that our search assumptions reflect our current understanding, which might be incomplete. The search for Dyson spheres becomes a mirror reflecting what we might become if we navigate our current filters successfully. We look for evidence of others who survived their technological adolescence and graduated to stellar-scale engineering. In searching for them, we're really asking whether that path exists, whether it's achievable, whether intelligence anywhere ever figures out how to persist long enough to reshape solar systems. The 17 stars wait in the darkness, their light traveling toward us carrying information we're only beginning to decode. Webb waits at L2, its instruments cold and sensitive, ready to collect the photons that will tell us what those stars really are. Astronomers wait at their computers, preparing analysis pipelines and verification protocols for whatever the data reveals. And humanity waits, perhaps without fully realizing it, for an answer to a question we've been asking since we first looked up and wondered if anyone else was looking back. The answer is coming. Not today. Not tomorrow. But soon, on timescales that matter to science if not to individual lives. The data accumulates. The picture clarifies. The universe prepares to tell us something we've wanted to know since we became capable of asking. And when that answer arrives, whether it confirms our hope or our solitude, we'll have earned it through careful observation, rigorous analysis, and the patient application of scientific method to the oldest question our species has ever asked. That's worth something regardless of what the answer turns out to be. Something's out there. Something massive, something cold, something so distant it takes 10,000 to 20,000 years to complete a single orbit around our sun. We haven't seen it. We can't photograph it. Yet the mathematical evidence suggests it's real, and it's 10 times more massive than Earth. This is Planet 9, a world that shouldn't exist according to everything we thought we knew about our solar system. But the math keeps pointing to the same conclusion. There's a giant lurking in the darkness beyond Neptune. In 2016, two astronomers at Caltech made an announcement that sent shockwaves through the scientific community. Konstantin Batygin and Mike Brown claimed they'd found evidence for a ninth planet, not through direct observation, but through pure mathematics and computer simulations. The prediction was bold. The implications were staggering. And the astronomical world split into believers and skeptics almost immediately. Here's what makes this different from every other "maybe there's something out there" claim. The evidence doesn't come from a single strange observation or a blurry photograph. It comes from watching how dozens of distant objects move, objects so far away they barely reflect any sunlight, objects that take thousands of years to complete their journeys around the sun. These frozen worlds are telling us something. Their orbits are aligned in ways that shouldn't be possible unless something massive is pulling on them. 6 of the most distant objects we've ever discovered all point in the same direction. They tilt downward from the plane of our solar system at nearly identical angles. The odds of this happening by random chance? About 1 in 500. Those aren't lottery odds. Those are "something's definitely going on here" odds. But let's back up. How do you lose a planet? The story begins much earlier than 2016. It starts over a century ago with an astronomer named Percival Lowell. In 1915, Lowell became convinced that something was disturbing the orbit of Uranus. He called this hypothetical object Planet X, where X stood for the unknown, not for the Roman numeral 10. Lowell died in 1916, never finding his mysterious planet. But his search continued at the observatory he founded in Flagstaff, Arizona. In 1930, a young astronomer named Clyde Tombaugh discovered Pluto. For decades, astronomers believed they'd found Lowell's Planet X. Pluto was celebrated as the 9th planet, the final member of our solar system family. Except there was a problem. Pluto was far too small to cause the gravitational effects Lowell had predicted. It turned out those perturbations to Uranus's orbit were measurement errors. They weren't real. The search for Planet X was based on a mistake. Pluto's story took another turn in 2006. The International Astronomical Union redefined what it means to be a planet. Pluto didn't make the cut. It became a dwarf planet instead, one of many similar objects in the Kuiper Belt. The man who provided much of the evidence leading to Pluto's demotion, Mike Brown. He even wrote a book titled "How I Killed Pluto and Why It Had It Coming." The irony that Brown might now discover a true 9th planet hasn't been lost on anyone. So if the old Planet X was a myth based on bad data, why should we believe in this new Planet 9? Because the evidence is completely different. This isn't about measurement errors or wishful thinking. It's about patterns that emerge when you look at the most distant objects in our solar system, objects that exist in a realm we barely understand. The outer solar system is strange. Beyond Neptune, at distances greater than 250 astronomical units, that's 250 times farther from the Sun than Earth, you enter a region where sunlight is so faint it's almost meaningless. Out here, objects move in slow motion, taking millennia to complete their orbits. We've discovered dozens of these extreme trans-Neptunian objects, and they're revealing something unexpected. In 2014, astronomers Scott Shepard and Chadwick Trujillo noticed something odd. A handful of these distant objects had orbits that clustered together. They weren't randomly scattered across the sky like you'd expect. They were grouped, almost shepherded, as if something massive was organizing them. Shepard and Trujillo suggested an unseen planet might be responsible, something several times larger than Earth and more than 200 times our planet's distance from the Sun. Badigian and Brown heard about this clustering and decided to investigate. What they found went far beyond the initial observations. When they ran computer simulations of the outer solar system, trying to recreate the orbits of these distant objects, they kept hitting the same conclusion. Without a massive planet out there, the simulations couldn't reproduce what we actually observe. But add a planet with specific characteristics, about 10 Earth masses in a highly elongated orbit, and suddenly everything clicked into place. The simulations matched reality. The alignment of these objects isn't subtle. 6 of them point in the same direction when they make their closest approach to the Sun. They're tilted at about 30 degrees downward from the plane where the other planets orbit. This kind of alignment doesn't happen naturally in a chaotic system. Something organized it. Something massive enough to gravitationally dominate a region of space larger than any known planet. There's more. Badigian and Brown's simulations predicted that a second group of objects should exist, forced into positions at right angles to Planet 9 and into orbits perpendicular to the solar system's plane. 5 known objects fit this prediction exactly. The math predicted they should be there before anyone found them. In April 2024, Badigian and Brown published new evidence. They focused on a different population of trans-Neptunian objects, ones with orbits that reach inside Neptune's orbit. These objects spread inward from Neptune in a pattern that matches Planet 9's predicted gravitational influence precisely. Without Planet 9 in the simulations, this pattern doesn't appear. With it, the match is almost perfect. The study was statistically significant at about a 5 sigma confidence level, which in scientific terms means the probability of this being a coincidence is vanishingly small. Mike Brown stated it plainly. I think it is very unlikely that Planet 9 does not exist. There are currently no other explanations for the effects that we see. If Planet 9 isn't real, astronomers would need 5 or 6 separate unknown explanations for all the oddities they're observing in the outer solar system. That's possible, but it violates a principle scientists hold dear. The simplest explanation that accounts for all the evidence is usually correct. But here's what makes this search so difficult. Planet 9, if it exists, is unimaginably far away. The most recent estimates place it around 290 astronomical units from the Sun on average. To put that in perspective, Neptune orbits at about 30 astronomical units. Pluto's average distance is around 40 astronomical units. Planet 9 is 7 to 10 times farther out than that. At such distances, sunlight is incredibly weak. The planet would reflect almost no visible light. It would be extraordinarily dim, with an apparent magnitude somewhere around 21 or 22. That's roughly 25,000 times fainter than the faintest stars you can see with your naked eye. Even with the world's most powerful telescopes, finding Planet 9 is like searching for a specific grain of sand on a beach at midnight. You know roughly which beach to search, but the grain could be anywhere along miles of coastline. Previous searches have eliminated about 78% of the possible sky positions. That sounds impressive until you realize 22% of an already enormous search area is still enormous. The planet moves slowly, incredibly slowly. At its estimated distance, it would take between 10,000 and 20,000 years to complete one orbit. In the time since humans built the pyramids, Planet 9 has moved only a fraction of its total path. This makes it harder to detect because astronomers typically find distant objects by watching them move against the background stars. If something barely moves over months or years of observation, it can easily be mistaken for a distant star or galaxy. There's another complication. The planet's orbit is highly elongated. Sometimes it might be relatively closer to the Sun, perhaps 200 to 300 astronomical units away. At other times, it could be 600 astronomical units out or even farther. According to Kepler's laws of planetary motion, objects move more slowly when they're farther from the Sun. Statistically, Planet 9 is more likely to be near the far end of its orbit right now, where it's moving slowest and is dimmest. That's the worst possible scenario for detection. Yet despite these challenges, astronomers are confident they'll find it soon. The reason for this confidence lies not in traditional telescopes, but in a revolutionary new observatory that's about to begin operations. The Vera C. Rubin Observatory in Chile represents a complete game-changer for astronomy. This facility, a joint project of the National Science Foundation and the Department of Energy, has been under construction for years. It's equipped with the largest digital camera ever built for astronomy, and it's designed to do something no other telescope can match. Starting in 2025, it will photograph nearly the entire southern sky every few nights, creating an ongoing movie of the cosmos. Mike Brown calls it the perfect tool for finding Planet 9. If you were to hand me a big wad of cash and say, go build a telescope to either find this Planet 9 or find the best evidence possible for Planet 9, I would probably go and build the Vera Rubin Observatory. The observatory will capture images of roughly 10 billion objects over the next decade. Computer systems will constantly compare new images to previous ones, flagging anything that changes or moves. If Planet 9 is in the southern sky, Rubin will almost certainly detect it. Scott Shepard estimates the observatory has a 70 to 80% chance of finding the planet if it's real. But what if it's not in the southern sky? What if it's in the northern hemisphere, outside Rubin's view? That's where other telescopes come in. The Subaru telescope in Hawaii, with its combination of large aperture and wide field of view, is conducting its own search. Two teams of astronomers, Badijan and Brown along with Trujillo and Shepard, are working together, expecting the combined search to take up to 5 years. 5 years might seem like a long time, but in astronomical terms, it's remarkably quick. We're talking about finding an object that's been hiding for 4.6 billion years, an object that's never been seen by human eyes, an object that challenges everything we thought we understood about how our solar system formed. Because that's the real question lurking behind all of this. If Planet 9 exists, how did it get there? A planet that massive, that far from the Sun, shouldn't exist according to standard models of planetary formation. The solar system's outer regions didn't have enough material to build something that large at such distances. So where did it come from? The answer might be even stranger than the planet itself. The leading theory suggests our solar system once had 5 giant planets, not 4. Jupiter, Saturn, Uranus, Neptune, and a fifth world roughly the size of Uranus or Neptune. During the chaotic early days of the solar system, these giants were packed much closer together than they are now. They orbited in a dense disk of planetesimals, the leftover building blocks from planetary formation. Then, over millions of years, gravitational interactions between the giant planets and these smaller objects caused the planets to migrate. Jupiter moved slightly inward. The others drifted outward. This migration wasn't smooth or gentle. It was violent, chaotic, a cosmic game of pinball played with planet-sized objects. At some point during this upheaval, the fifth giant planet got too close to Jupiter. Jupiter, the most massive planet in the solar system with more than twice the mass of all other planets combined, acted like a gravitational slingshot. It flung the fifth giant outward with tremendous force. Most computer simulations of this scenario show the ejected planet being thrown completely out of the solar system, lost forever to interstellar space. But in a small percentage of simulations, something different happens. The ejected planet doesn't quite reach escape velocity. Instead, it settles into a distant, highly elliptical orbit, exactly the kind of orbit predicted for Planet 9. This scenario is called the Nice model, named after the French city where it was developed. The Nice model has become widely accepted because it explains several puzzling features of the solar system. It accounts for the late heavy bombardment, a period roughly 4 billion years ago when the inner solar system was pummeled by asteroids and comets. It explains why Neptune's orbit is slightly eccentric. It clarifies the structure of the Kuiper belt. And now, it might explain Planet 9. The ejection hypothesis solves a fundamental problem. You can't build a planet as massive as Planet 9 at such extreme distances from the Sun. There simply wasn't enough material out there. The solar nebula, the disk of gas and dust from which planets formed, was too thin and spread out at those distances. Planet formation requires material to collide and stick together, and that process becomes exponentially slower when particles are spread across vast expanses of space. But if Planet 9 formed closer to the Sun, in the region where Uranus and Neptune formed, and was then ejected outward, suddenly its existence makes perfect sense. The physical characteristics match this origin story remarkably well. Planet 9 is predicted to have a mass of about 5 Earth masses, similar to Uranus and Neptune when you account for their thick atmospheres. It would be gaseous, an ice giant with a rocky core surrounded by water, methane, and ammonia ices, all wrapped in a hydrogen and helium envelope. These are exactly the characteristics you'd expect from a planet that formed in the outer solar system 6 billion years ago. But there's another possibility, one that's even more extraordinary. What if Planet 9 didn't form in our solar system at all? The Sun wasn't born in isolation. It formed in a stellar nursery, a dense cluster containing thousands of young stars packed into a relatively small volume of space. In such environments, close encounters between stars are common. During the first few 100 million years of the solar system's existence, another star could have passed within a few hundred astronomical units of the Sun. If that star had its own planetary system, and if one of its planets happened to be in just the right position during the encounter, the Sun's gravity could have captured it. This capture scenario would make Planet 9 an exoplanet, a planet that formed around another star. If confirmed, it would be the first exoplanet discovered within our own solar system, a world that spent billions of years orbiting a different sun before becoming part of ours. The odds of such a capture are low, but they're not zero. Computer simulations show that in dense stellar nurseries, planetary capture events do occur, though rarely. The capture hypothesis has an appealing elegance. It would explain why Planet 9's orbit is so different from the other planets, tilted relative to the solar system's plane and highly elongated. A captured planet wouldn't follow the orderly, nearly circular orbits of planets that formed in place. Its orbit would bear the fingerprints of a violent gravitational encounter, exactly what we see predicted for Planet 9. But here's what makes this puzzle even more complex. There's a third option that astronomers are seriously considering. What if there isn't just one Planet 9, but multiple smaller planets? What if instead of a single 5 Earth mass world, there are 2 or 3 planets, each a few Earth masses, scattered across the outer solar system? This multi-planet scenario could produce similar gravitational effects on trans-Neptunian objects while being harder to detect because each individual planet would be smaller and dimmer. Some researchers have proposed an even more exotic alternative involving a disk of small icy bodies with a combined mass of 10 Earth masses, spread across the outer solar system. This disk, if it exists, could gravitationally shepherd trans-Neptunian objects in ways that mimic the effects of a single large planet. The challenge with this disk hypothesis is that such a structure should be detectable through its infrared emission, and so far, surveys haven't found it. Then there are the truly speculative ideas. Could Planet 9 be a primordial black hole, a microscopic black hole formed in the early universe? Such an object would have the right mass to produce the observed gravitational effects but would be nearly impossible to detect directly. Or could it be a concentration of dark matter, the mysterious substance that makes up most of the universe's mass but doesn't interact with light? These exotic explanations remain on the fringes of scientific consideration because they require invoking phenomena we've never directly observed in our solar system. Occam's razor suggests the simpler explanation, a planet, is more likely. But the fact that astronomers are even considering such alternatives demonstrates how profoundly puzzling this situation is. What makes the formation question so crucial is this: the answer would tell us whether our solar system is typical or unusual. If Planet 9 is an ejected fifth giant, it suggests that planetary systems commonly lose planets during their chaotic youth. Astronomers have found evidence of ejected planets around other stars, so this wouldn't be unprecedented. It would mean that for every planetary system we observe, there might be one or more invisible planets lurking in the darkness beyond what we can easily detect. If Planet 9 is a captured exoplanet, it would suggest that stellar nurseries are dynamic enough to exchange planets between forming systems. This would have profound implications for understanding planetary demographics in the galaxy. How many stars captured planets? How many lost them? The architecture of planetary systems might be far more fluid and dynamic than we've imagined. Recent refinements to the Planet 9 hypothesis have actually made the formation question more pressing. A 2025 study using an expanded sample of 51 extreme trans-Neptunian objects proposed that Planet 9's orbit might be smaller than previously thought, with a semi-major axis of around 290 astronomical units rather than 400 to 600. If true, this would place Planet 9 closer to the Sun, making it brighter and easier to find, but it also changes the dynamical requirements for how the planet reached that orbit. The NICE model simulations that showed a fifth giant being ejected to Planet 9's orbit were based on the earlier, larger orbital estimates. With a smaller orbit, the ejection dynamics would need to be recalculated. Could Jupiter fling a planet to 290 astronomical units without ejecting it entirely from the solar system? The answer depends on precise details of the ejection event, the angle, the velocity, the gravitational assists from other planets. What we're witnessing is science in action, the process of refining hypotheses as new data emerges. Each new trans-Neptunian object discovered adds another constraint to the models. Each failed search narrows the possible locations. The picture is becoming clearer, but the fundamental mystery remains. Somewhere out there, moving slowly through the darkness, there might be a world that holds the key to understanding our solar system's violent past. And the clock is ticking. Within the next few years, the Vera Rubin Observatory will either find Planet 9 or rule out large portions of the remaining search space. We're approaching a definitive answer to one of astronomy's biggest questions. But before we get there, we need to understand what finding Planet 9 would actually mean for the rest of the solar system, because its gravitational influence extends far beyond just those handful of trans-Neptunian objects. Planet 9's gravitational reach doesn't stop at those extreme trans-Neptunian objects. It extends throughout the outer solar system in ways that are subtle but detectable. Jupiter family comets, those periodic visitors that swing through the inner solar system every few years, would show different orbital tilts if Planet 9 exists. Computer simulations predict their inclination distribution should be broader, more spread out, than what we'd see in a Planet 9-free solar system. And when astronomers look at the actual data, that's exactly what they find. The distribution matches the prediction. Then there's the Oort cloud, that vast spherical shell of icy bodies surrounding the solar system at distances up to 100,000 astronomical units. Planet 9 would have affected how many objects got captured into the Oort cloud during the solar system's formation. Simulations show that with Planet 9 in its predicted orbit billions of years ago, fewer objects would have been flung into the Oort cloud. The gravitational stirring from a massive planet in the outer reaches would have ejected more objects entirely from the solar system rather than parking them in distant orbits. This prediction is harder to test directly since we can't count Oort cloud objects with any precision, but it represents another testable consequence of the hypothesis. What about the giant planets themselves? Would Planet 9 have left fingerprints on Jupiter, Saturn, Uranus, and Neptune? The answer depends on when Planet 9 reached its current orbit. If it was ejected early in the solar system's history, during the period of planetary migration described by the NICE model, then its ejection would have been part of the same chaotic reshuffling that moved all the giant planets. In that case, Planet 9's influence is already baked into the current orbital configuration we observe. The planets are where they are partly because of the gravitational chaos that sent Planet 9 outward. But there's a more direct effect. Planet 9's orbit is tilted about 6 degrees relative to the plane where the 8 known planets orbit. That tilt would exert a slow, subtle torque on the entire solar system over billions of years. Think of it like a spinning top that's slightly off balance. Over time, that imbalance affects the whole system's orientation in space. Calculations suggest that Planet 9 could explain a long-standing puzzle, why the Sun's equator is tilted about 6 degrees relative to the planetary orbital plane. The gravitational influence of a distant, tilted Planet 9, acting over 4.5 billion years, could have gradually torqued the entire inner solar system, including the Sun's rotation axis, into its current configuration. This prediction caught many astronomers by surprise when it was first published. It's one thing to affect distant icy bodies. It's another to tilt the Sun itself. But the math checks out. A 5 Earth-mass planet at 300 to 400 astronomical units, tilted at the right angle, applying gentle but persistent gravitational torque over geological timescales, could absolutely accomplish this feat. And suddenly Planet 9 isn't just explaining weird orbits at the edge of the solar system. It's explaining a fundamental property of our planetary system that's been visible since humans first pointed telescopes at the Sun. Yet another population shows Planet 9's fingerprints, high-inclination trans-Neptunian objects. These are objects whose orbits are tilted steeply relative to the plane where planets orbit, sometimes by 90 degrees or more. They're rare, which makes sense. Most of the solar system's material started in a flat disk and should stay relatively flat. But we found several objects with these extreme tilts, and they need an explanation. Planet 9's gravitational influence could pump up the inclinations of certain objects over millions of years through a process called correlative oscillations. This mechanism causes orbits to trade eccentricity for inclination in a periodic cycle. An object might start with a moderately elliptical orbit in the plane, then gradually become more circular but more tilted, then swing back. With Planet 9's gravity driving these oscillations, some objects could get kicked into very high inclinations and stay there. 5 known objects fit this prediction with remarkable precision. They're positioned at roughly 90-degree angles to Planet 9's predicted location, and their orbits are perpendicular to the solar system's plane. When Badigian and Brown first ran their simulations, these objects appeared naturally in the results. The model predicted they should exist before anyone had specifically looked for them. Finding them in the real data wasn't just confirmation. It was the kind of successful prediction that makes scientists take notice. The gravitational mechanisms at work here operate on timescales that dwarf human civilization. An object in the outer solar system might take hundreds of thousands of years to complete one oscillation cycle. Planet 9 itself takes 10,000 to 20,000 years just to complete a single orbit. The gravitational dance between Planet 9 and these distant objects unfolds across geological epochs, invisible to any observer watching for less than millennia. We're catching a single frame of a movie that's been playing for billions of years. Does Planet 9 affect the known planets directly? Neptune's orbit should show tiny perturbations if Planet 9 exists, wobbles measurable in the planet's position over time. Astronomers have looked for these signatures. So far, the results are inconclusive, which actually makes sense given Planet 9's distance. At 300 to 600 astronomical units, its gravitational pull on Neptune is extraordinarily weak. Neptune is 30 astronomical units from the Sun. Planet 9 is 10 to 20 times farther out. Gravitational force drops off with the square of distance, so Planet 9's pull on Neptune is hundreds of times weaker than Neptune's pull on itself. Detecting such subtle effects requires decades of precise observations and sophisticated data analysis. We might not see clear perturbations in Neptune's orbit for years yet. Uranus presents a different puzzle. This ice giant is tilted on its side, rotating with its axis nearly in the plane of its orbit rather than roughly perpendicular like every other planet. Various theories have tried to explain this bizarre orientation: a giant collision during formation, gravitational interactions during planetary migration, or cumulative effects from multiple smaller impacts. Could Planet 9 be responsible? Probably not directly. The tilt likely originated during the solar system's chaotic youth, and Planet 9's current location doesn't provide the right geometry to have caused it. But if Planet 9 was ejected from the inner solar system, it might have been one of several factors contributing to the orbital chaos that tilted Uranus. Not the sole cause, but part of a complex sequence of gravitational interactions. The asteroid belt between Mars and Jupiter seems far removed from Planet 9's domain, but even here there might be subtle connections. Some asteroids have been found on highly elliptical orbits that take them far beyond Neptune. These aren't main belt asteroids in the traditional sense, they're trans-Neptunian objects that happen to pass through the inner solar system. Planet 9 could influence the population of these objects, determining which ones get perturbed onto planet-crossing orbits and which stay safely beyond Neptune. This matters for understanding impact rates on the inner planets over geological time. If Planet 9 exists, it's been shaping the flux of impactors throughout solar system history. Centaurs, those hybrid objects orbiting between Jupiter and Neptune, neither quite asteroids nor comets, show dynamical properties that could reflect Planet 9's influence. These objects are thought to originate from the trans-Neptunian region and get gravitationally scattered inward. The rate at which objects get scattered, and the specific orbits they end up on, depend on the outer solar system's gravitational environment. Add Planet 9 to the mix, and you change the probabilities. More objects might get kicked onto certain types of orbits, fewer onto others. Detailed population studies of centaurs could, in principle, reveal Planet 9's gravitational fingerprint even in the middle reaches of the solar system. What's remarkable about all these effects is their consistency. Planet 9 isn't just explaining one weird thing. It's explaining multiple independent phenomena across different populations of objects in different regions of the solar system. The clustering of extreme trans-Neptunian objects. The perpendicular objects. The Sun's axial tilt. The distribution of orbital inclinations. Each one could potentially have a different explanation. But they all point to the same solution: a massive planet on a distant, tilted orbit. That's what makes the hypothesis so compelling. Still, correlation isn't causation. Maybe these effects have other explanations we haven't considered. Maybe observational biases we haven't properly accounted for are creating patterns where none exist. Maybe the solar system is just weird in multiple unrelated ways. These possibilities keep skeptics skeptical, and rightfully so. Extraordinary claims require extraordinary evidence. But with each new study, with each additional prediction that proves correct, the case grows stronger. The question isn't really whether Planet 9 affects the solar system. If it exists at all, it must. Gravity doesn't have an off switch. The question is whether we can measure those effects precisely enough to confirm the planet's existence indirectly. And that's where the cutting edge of observational astronomy comes in, techniques for detecting planets not by seeing them directly, but by mapping their gravitational influence on everything around them. The art of finding invisible planets has evolved dramatically since Neptune's mathematical discovery in 1846. Back then, astronomers noticed Uranus wasn't following its predicted path. Something was tugging on it. They worked backward from those perturbations, calculated where the disturbing mass had to be, pointed their telescopes at that spot, and there it was. A new world revealed through pure mathematics. Planet 9 requires a more sophisticated approach. We're not tracking one object getting pulled by an unknown planet. We're analyzing dozens of distant bodies, each with its own orbital peculiarities, trying to extract a common signal from the noise. It's less like following footprints to find what made them and more like being a detective at a crime scene with multiple witnesses who each saw something slightly different. The statistical methods matter enormously here. Brown and Badijan didn't just notice the clustering and declare victory. They quantified it. They developed techniques to measure observational bias in each individual object's discovery, because not all parts of the sky get observed equally. Some regions get scanned more frequently. Some get deeper exposures. Telescopes point where astronomers tell them to point, and astronomers have their own interests and observing programs. This creates selection effects. If you only search for distant objects in certain parts of the sky, you'll only find distant objects in those parts of the sky. Obvious, right? But correcting for this bias mathematically isn't straightforward. You need to know not just where you looked, but how thoroughly you looked there, and with what sensitivity. Brown and Badijan accounted for these factors, and even after corrections, the clustering remained statistically significant. About 1 chance in 500 that it's random. That number has gotten better with time. As more objects get discovered and the sample size grows, the statistical confidence strengthens. By 2021, Brown and Badijan reanalyzed with improved bias corrections and found a clustering significant at 99.6% confidence. That's getting into the realm where you start taking things very seriously. But statistics alone don't make a planet. The real power comes from prediction. If your hypothesis is correct, it should tell you what else you'll find. Planet 9 makes specific predictions about populations of objects that should exist but hadn't been looked for yet. And that's where things get interesting. One prediction involves objects perpendicular to the solar system's plane. Not just tilted. Perpendicular. Orbiting the sun almost vertically while everything else goes around horizontally. These objects shouldn't exist in a normal solar system. There's no mechanism to put them there. Yet Planet 9's gravitational influence, according to the models, should create exactly this population. 5 objects matching this prediction have been found. 5 might not sound like many, but remember, these are extremely rare configurations. Finding even one was surprising. Finding 5 that matched the theoretical prediction in detail. That's not coincidence. Another test came in 2024. Brown and Badijan published analysis of a different population, low-inclination trans-Neptunian objects with orbits that reach inside Neptune's orbit. These objects have nothing to do with the original clustering that suggested Planet 9. They're on completely different types of orbits. Yet when you run simulations with Planet 9 included, these objects' orbital distribution matches what we actually observe. Remove Planet 9 from the simulations, and the match disappears. The statistical rejection of the Planet 9 free scenario sits at 5 sigma. That's the same confidence level physicists demanded before announcing the Higgs boson discovery. Does this prove Planet 9 exists? No. Science doesn't deal in proof, only in evidence and confidence levels. But the confidence is getting high enough that dismissing the hypothesis requires explaining away multiple independent lines of evidence. The skeptics haven't been silent. Samantha Lawler and others argue that observational biases are stronger than Brown and Batygenic knowledge. In 2020, 2 large surveys, the Outer Solar System Origins Survey and the Dark Energy Survey, found hundreds of trans-Neptunian objects and saw no significant clustering. OSOS documented over 800 objects. DES found 316 new ones. Both surveys carefully accounted for observational bias and concluded the orbits could be explained by known physical processes without invoking a 9th planet. This disagreement cuts to the heart of how science works. Same solar system, same objects, different conclusions. Why? It comes down to which objects you include in your analysis and how you correct for bias. Brown and Batygen focus on the most extreme objects, the ones farthest out with the most elongated orbits. These are the objects most likely to be influenced by Planet 9 because they venture into its gravitational domain. OSOS and DES looked at a broader population including objects that wouldn't be strongly affected by Planet 9 even if it exists. The debate also involves sample size versus sample quality. OSOS has more objects, but are they the right objects for testing this particular hypothesis? 1,000 data points don't help if they're measuring the wrong thing. Meanwhile, Brown and Batygen's smaller sample focuses on exactly the objects that should show Planet 9's influence most clearly. It's a classic tension in observational astronomy. More data isn't always better data if it dilutes your signal. Alternative explanations have emerged. Maybe instead of one big planet, there's a disk of smaller icy bodies with combined mass equivalent to Planet 9. Spread that mass out, and you might get similar gravitational effects. Or perhaps these orbits were set during the solar system's birth, when the Sun formed in a stellar cluster and neighboring stars perturbed the outer reaches. Some researchers even propose multiple Earth mass rogue planets rather than one super-Earth. Each alternative has problems. The disk hypothesis requires an improbably specific mass distribution that stays stable over billions of years. The stellar cluster scenario works for setting initial conditions but doesn't explain why the clustering persists today, billions of years after the Sun left its birth cluster. Multiple rogues would need to have been captured with just the right orbits and masses to produce the observed effects without disrupting everything else. What makes Planet 9 compelling isn't that it's the only possible explanation. It's that it's the simplest explanation that accounts for multiple independent observations. One object, one orbit, multiple predictions that keep being confirmed. That's powerful. The thermal emission angle offers another avenue. Planet 9, if it exists, is still cooling from its formation. At 5 Earth masses, it retains significant internal heat. Even at 47 Kelvin, frigidly cold by any human standard, it radiates in the infrared. This radiation should be detectable with the right instruments, particularly submillimeter telescopes that specialize in this wavelength range. The challenge is sensitivity. Planet 9's thermal signature is faint, and the infrared sky is crowded. Lots of things emit at these wavelengths. You need long integration times, careful subtraction of foreground and background sources, and the patience to search a large area of sky. Several groups are working on this, using facilities like the Atacama Large Millimeter Array. No detections yet, but the search continues. Direct optical detection faces a different set of challenges. At aphelion, Planet 9 could be 800 astronomical units away or more, moving through the most distant parts of its orbit. At that distance, reflected sunlight is vanishingly faint. You need large telescopes with wide fields of view, and you need to image the same regions repeatedly to detect motion. The Subaru telescope in Hawaii has been conducting systematic searches. So have other facilities. They've covered about 78% of the possible sky positions where Planet 9 might be. That sounds good until you realize the remaining 22% is still a huge search space. Statistically, Planet 9 is more likely to be near aphelion than perihelion, simply because it moves slower out there and spends more time in that part of its orbit. That's where Kepler's second law bites you. Objects sweep out equal areas in equal times, which means they crawl along when far from the Sun. If Planet 9 is currently near aphelion, it's at its faintest and hardest to detect. Bad luck for us, but that's the reality. The search isn't hopeless. It's methodical, systematic, and ongoing. Every survey that comes up empty eliminates possibilities and narrows the remaining search space. Brown and Badijan have refined their predictions multiple times based on new data, updating the most likely orbital parameters. Their current best estimate puts the semi-major axis around 380 to 460 astronomical units, though a 2025 study by Siraj, Chaiba, and Tremaine suggests it might be closer, around 290 astronomical units. Closer means brighter. Brighter means easier to find. And then there's the Vera Rubin Observatory, scheduled to begin operations in 2025, which changes everything. The Vera Rubin Observatory is unlike anything that's come before. Sitting on Cerro Pachón in Chile at 2,700 meters elevation, it houses an 8.4-meter primary mirror and the largest digital camera ever built for astronomy. 3 gigapixels. That's not a typo. The camera weighs 3 tons and captures an area of sky equivalent to 40 full moons in a single image. Why does this matter for Planet 9? 2 reasons. Coverage and cadence. Rubin will survey the entire visible southern sky every few nights. Not targeted observations of specific regions. The whole sky, repeatedly, for 10 years. Every object in that survey gets tracked automatically. The system compares new images to previous ones, flagging anything that moves, changes brightness, or appears where nothing was before. Planet 9, if it exists, moves. Slowly. Over months and years, it would shift position relative to background stars. That's its signature. Rubin's repeated imaging strategy is custom-built to catch exactly that kind of motion. You don't need to know where to look ahead of time. You just watch everything and let the data tell you what moved. Mike Brown's enthusiasm about Rubin isn't exaggeration. He spent years searching with Subaru, which is an excellent telescope but requires choosing where to point. Rubin doesn't. It watches. Constantly. Systematically. If Planet 9 is anywhere in the southern sky at a detectable brightness, Rubin will find it. Not might find it. Will find it. Scott Shepard estimates the probability at 70 to 80%, assuming Planet 9 exists and has the predicted properties. Those are good odds in astronomy. Mario Jurek points out that Rubin will increase the known population of trans-Neptunian objects from around 4,000 to potentially 40,000. That's not just more objects. That's better statistics, tighter constraints, and a far clearer picture of what's actually happening in the outer solar system. The timeline is aggressive. Megan Schwamm says the first year or two of Rubin operations should answer the question. Either Planet 9 shows up in the data, or the lack of detection tells us something definitive about where it isn't and what it can't be. This is the moment. After nearly a decade of predictions, simulations, and targeted searches, we're about to conduct the most comprehensive survey of the outer solar system ever attempted. If Planet 9 is real, 2025 through 2027 could be the years we finally see it. But what if Rubin doesn't find it? That's the scenario nobody talks about much, but it's worth considering. Absence of evidence isn't evidence of absence, except when you've looked everywhere the thing could possibly be. Rubin gets us close to that threshold. If Rubin completes its survey without detecting Planet 9, the hypothesis doesn't collapse entirely, but it gets significantly harder to maintain. Maybe Planet 9 is fainter than expected. Maybe it's in a part of the sky Rubin can't see as well. Maybe it's currently too close to the galactic plane where background star density makes detection difficult. There are outs, but they start sounding like special pleading after a while. The other possibility is that Planet 9 exists but isn't where the models predict. Orbital parameters have shifted multiple times as new data comes in. The 2025 Siraj study suggested a closer, less eccentric orbit than previous estimates. If that's correct, Planet 9 might be brighter and easier to find. But if the models are still off, we might be looking in the wrong regions entirely. Then there's the alternative explanations. What if the orbital clustering of trans-Neptunian objects isn't caused by a single planet but by a disk of smaller objects, each too faint to detect individually but collectively massive enough to produce gravitational effects? That hypothesis has been proposed. It works mathematically for some observations but struggles to explain others, particularly the perpendicular objects. Or what if the clustering is a transient phenomenon caused by something that's no longer there? A passing star could have perturbed orbits temporarily. The Sun's birth cluster could have left a dynamical imprint that's still visible today. Multiple captured rogue planets might produce similar effects without requiring a single massive world. These scenarios feel more contrived than a single planet, but they're not impossible. Brown has argued that rejecting Planet 9 means accepting 5 or 6 separate unexplained phenomena, each requiring its own cause. That's inelegant. Science favors parsimony. One explanation that accounts for multiple observations beats several disconnected explanations. But parsimony isn't proof. Sometimes reality is messy and complicated. The discovery of Ammonite, a new sednoid announced by the Subaru team, adds another wrinkle. Ammonite's orbit doesn't cluster with the other sednoids the way Planet 9's gravitational influence would predict. It's off on its own. That might mean Planet 9's orbit needs further adjustment to account for Ammonite. Or it might mean something else entirely is going on. Every new discovery refines the picture, but it also introduces new constraints that any hypothesis has to satisfy. That's how science works. You don't get to cherry-pick the observations that support your model and ignore the rest. You have to explain all of it. Brown and Badijan have been transparent about this process. They've updated their predictions multiple times based on new data. They've addressed criticisms. They've acknowledged uncertainties. That's not weakness. That's how you build a robust scientific case. You test it against everything, adjust when necessary, and see if it still holds up. The April 2024 paper on low-inclination trans-Neptunian objects is a good example. These are objects that cross Neptune's orbit, a completely different population from the extreme distant objects that sparked the original hypothesis. Yet when you model their distribution, Planet 9's gravitational influence predicts their observed spread with remarkable accuracy. No, Planet 9. The distribution doesn't match. With Planet 9, it does. That's independent confirmation using a different dataset. Statistical confidence levels matter here. A 5 sigma result means the probability of the observation occurring by chance is less than 1 in 3. 5 million. That's the standard for discovery in particle physics. It's extremely stringent. The 2024 study rejected the no Planet 9 scenario at approximately 5 sigma confidence. That's not suggestive. That's strong. Brown's statement that he thinks it's very unlikely Planet 9 doesn't exist reflects this accumulating evidence. It's not arrogance. It's Bayesian updating. Start with a hypothesis. Test it against observations. Adjust your confidence based on how well it performs. After 8 years of testing, the hypothesis keeps working. That shifts the probability upward. Could everyone be wrong? Of course. Science has a long history of confident predictions that turned out to be false. Vulcan, the hypothetical planet inside Mercury's orbit, was predicted to explain perturbations that Einstein's general relativity later explained without needing an extra planet. The luminiferous ether seemed necessary until it wasn't. Confidence doesn't equal certainty. But here's the key difference. Vulcan was never observed. Planet 9 hasn't been observed either, but the effects attributed to it keep showing up in independent datasets. The orbital clustering persists after correcting for observational bias. The perpendicular objects exist. The low inclination objects match predictions. The Jupiter family comet distribution changes in the expected way. The predicted reduction in Oort cloud capture efficiency aligns with simulations. That's a lot of things to get right by accident. It's not impossible, but it's increasingly unlikely. Each successful prediction raises the prior probability that the underlying model is correct. So where does that leave us as Rubin prepares to begin operations? We're at a decision point. Within 2 years, maybe 3, we'll have data comprehensive enough to either confirm Planet 9's existence or rule it out across most of its possible parameter space. This isn't the kind of question that lingers unresolved for decades. The technology exists. The survey is happening. The answer is coming. If Rubin finds Planet 9, it will be one of the most significant planetary discoveries in history. Not because it's a planet, though that's cool. Because of what it tells us about solar system formation, migration dynamics, and the possibility that our planetary census was incomplete for the entire history of astronomy. If Rubin doesn't find it, that's also significant. It means either the hypothesis was wrong, or Planet 9 is so far, so faint, or so weirdly positioned that even our best efforts can't detect it. That possibility can't be dismissed. The outer solar system is vast. Assumptions about brightness and location might be off. But at some point, a hypothesis that can't be tested stops being useful. The broader implications extend beyond our solar system. Discovering Planet 9 would make our system more similar to others. Most exoplanetary systems contain super-Earths, planets with masses between Earth and Neptune. We don't have any. Planet 9 would fill that gap, suggesting that our system formed similarly to others but with a quirk: one of the planets got kicked outward instead of staying close. That has implications for planet formation theory. How common is ejection? What determines whether a forming planetary system ends up with all its planets in tight orbits versus having one or more in distant eccentric orbits? Are we typical or unusual? Planet 9 helps answer those questions. It also affects how we think about planetary migration. The NICE model explains a lot about how the giant planets reach their current orbits, but it's not complete. If Planet 9 is an ejected ice giant, that's a direct observation of a process we've only simulated. We could study its composition, atmosphere, and thermal properties. We could learn what happens to a planet that gets thrown into the outer darkness and survives there for billions of years. All of that depends on detection. And detection depends on Rubin. The next few years will be decisive. The search itself has an interesting dynamic. Brown and his team aren't the only ones looking. Multiple groups worldwide are scanning different portions of the sky, using different methods, hoping to be the first to spot it. There's a competitive element, though it's mostly friendly. Everyone wants the discovery, but everyone also wants the answer, regardless of who provides it. What happens if Rubin spots something in the right region with the right motion? Confirmation would take time. A single detection isn't enough. You need multiple observations over weeks or months to establish an orbit. Then you need spectroscopy to determine composition. Is it icy? Gaseous? Does it have an atmosphere? What's its temperature? All of that requires follow-up with other instruments. And here's something people don't always consider. If Planet 9 exists and Rubin finds it, that's not the end of the story. It's the beginning. We'd have a new planet to study. A super-Earth in our own solar system, close enough to observe in detail but far enough to be genuinely alien. What can we learn from it? For one thing, we could study its atmosphere if it has one. Most super-Earths we've detected around other stars are too far away for detailed atmospheric analysis. Planet 9 would be right here, relatively speaking. We could point infrared telescopes at it, measure its thermal emission, detect molecular signatures, and figure out what it's made of. We could also study its interaction with the surrounding environment. Does it have moons? Rings? A magnetic field? How does it affect the local dust distribution? Does it capture comets or asteroids into temporary orbits? All of those questions become answerable once we know where it is. The formation question would become more tractable too. If Planet 9 is an ejected ice giant, we could compare its properties to Uranus and Neptune. Are they similar? Different? That tells us about the conditions under which they formed and what happened during the ejection process. Did Planet 9 lose its outer layers during the encounter with Jupiter? Did it retain them? The answers matter for understanding how planetary systems evolve. There's also the possibility of detecting other distant planets. If one exists, maybe others do. The outer solar system is huge. We've barely scratched the surface. Rubin will find thousands of new trans-Neptunian objects, and some of them might have orbits that point to additional unseen bodies. Planet 9 might not be alone. But let's consider the other scenario. Rubin surveys the entire accessible region and finds nothing. What then? First, it doesn't immediately kill the hypothesis. The predicted orbit has uncertainty. If Planet 9 is near its aphelion and farther than expected, Rubin might miss it. Its brightness could be lower than predicted. There are scenarios where Planet 9 exists but remains undetected even after Rubin's survey. However, those scenarios become increasingly constrained. If Rubin doesn't find it, the parameter space shrinks dramatically. The planet would have to be fainter, farther, or in a very specific location that Rubin didn't cover. At that point, the hypothesis starts looking less likely. It wouldn't vanish entirely. Science doesn't work that way. But the community's confidence would shift. If the best survey we've ever conducted finds nothing, most astronomers would conclude that Planet 9 probably isn't there, at least not in the form currently predicted. That would leave the clustering problem unresolved. The orbital alignment of trans-Neptunian objects would still need an explanation. Maybe it's observational bias after all, despite the corrections. Maybe it's a temporary configuration that will disperse over time. Maybe there's a different mechanism at work that we haven't thought of yet. Or maybe there's something else out there, not a single planet but a different kind of object. A primordial black hole, for instance. That's been proposed as an alternative. A black hole with a few Earth masses could produce similar gravitational effects without being visible. It wouldn't emit light, wouldn't reflect sunlight, and would be nearly impossible to detect directly. The black hole hypothesis is speculative, but it's not absurd. Primordial black holes, if they exist, would have formed in the early universe from density fluctuations. Some could have been captured by the solar system. The gravitational effects would be identical to a planet of the same mass. The only difference is detectability. How would you find a black hole in the outer solar system? Gravitational lensing, maybe. If it passed in front of a distant star, the star's light would bend around it, creating a brief brightening. Rubin could detect that. It's a long shot, but it's possible. Another alternative is a disk of smaller objects, collectively massive enough to produce the observed effects. Instead of one planet, imagine thousands of smaller bodies distributed across a wide region. Their combined gravity could shepherd trans-Neptunian objects into aligned orbits. The disk hypothesis has problems though. To match the observed clustering, the disk would need a very specific mass distribution and configuration. It's not impossible, but it requires fine-tuning. A single planet is simpler. Occam's razor favors the simpler explanation, but simplicity doesn't guarantee correctness. So where does the evidence actually point right now, before Rubin starts observing? The statistical case for Planet 9 has strengthened. The 2024 study showing alignment of low-inclination objects was a big deal. That's a new population, independent of the original clustering, behaving exactly as predicted. The odds of that happening by chance are very low. But statistics aren't proof. Astronomy has seen confident predictions proven wrong before. The key is falsifiability. Planet 9 is falsifiable. If Rubin surveys the predicted region and finds nothing, the hypothesis is either wrong or needs major revision. That's good science. It's worth stepping back and asking why this matters beyond pure curiosity. Why should anyone care if there's a ninth planet? One reason is completeness. If we don't know our own solar system, how can we claim to understand others? Planet 9, if real, has been there the entire time humans have looked at the sky. Missing something that large in our own neighborhood would be humbling. Another reason is the connection to exoplanetary science. Super-Earths are everywhere. We've found thousands around other stars, but we don't have one here to study up close. Planet 9 would be the only super-Earth we can observe in detail, the only one we can send probes to eventually. That makes it scientifically valuable beyond its role in solar system dynamics. There's also the historical angle. Discovering a new planet is rare. it doesn't happen often. Neptune in 1846. Pluto in 1930, though that got reclassified. If Planet 9 is real, this generation gets to witness something that happens maybe once per century. That's not nothing. And then there's the sheer weirdness of it. A planet 10 times Earth's mass, orbiting hundreds of times farther from the Sun than we do, taking 20,000 years to complete one orbit. It's so far out that the Sun looks like just another bright star. Temperatures are near absolute zero. If it has an atmosphere, it's probably frozen solid. It's a world more alien than anything we've explored, and it's technically in our solar system. What would it be like to visit Planet 9? Impossible with current technology, obviously. The distance is staggering. Voyager 1, the fastest probe we've ever launched, has been traveling for over 40 years and still hasn't reached the predicted inner edge of Planet 9's orbit. Getting there would take centuries with existing propulsion systems. But imagine if we could. What would you see? The Sun would be a bright point of light, no disk visible, providing almost no heat. The sky would be black, filled with stars that don't twinkle because there's no atmosphere to distort them. The planet itself, if gaseous, might have faint cloud bands, though they'd be moving incredibly slowly in the cold. Moons, if they exist, would be frozen solid, covered in ancient impact craters. It would be the most isolated place a human could stand and still be within the Sun's gravitational influence. The nearest planet, Neptune, would be billions of kilometers away. Earth would be invisible without a telescope. You'd be at the edge of the solar system, looking outward toward interstellar space, inward toward the distant Sun, and feeling utterly, completely alone. That's Planet 9. If it exists. And within 2 years, we'll have a much better idea whether it does. Rubin starts observations soon. The data will accumulate. The algorithms will scan for slow-moving objects. And somewhere in those billions of data points, there might be a faint dot that moves just slightly between images. Or there might not. Either way, we're about to find out. The search for Planet 9 is entering its final phase. The question that's lingered for nearly a decade will finally get an answer. Whatever that answer is, it'll reshape how we understand the solar system. That's worth paying attention to. Looking at the timeline, we're living through something remarkable. The Vera Rubin Observatory represents the culmination of decades of technological advancement in astronomy. Its 2-gigapixel camera, its systematic survey strategy, its ability to track billions of objects simultaneously, all of it converges on this moment. We built the perfect machine for finding Planet 9 without necessarily intending to. The telescope doesn't care about the hypothesis. It's going to scan the southern sky regardless, cataloging everything that moves, everything that changes, everything that exists in its field of view. Planet 9 is just one target among billions. But if it's there, Rubin will see it. The odds are too good. The coverage too complete. The sensitivity high enough. What happens next depends entirely on what the data shows. If Planet 9 appears in the images, moving slowly across the background stars over weeks and months, the discovery will unfold gradually. Not a single eureka moment, but a pattern emerging from noise. Statistical confidence building with each new observation. Orbital parameters refined as more data points accumulate. Eventually, certainty. The confirmation process would take time. You don't announce a planet based on a handful of detections. You need enough measurements to calculate an orbit accurately. You need spectroscopy to determine composition. You need infrared observations to measure temperature and size. The full characterization might take years. But the initial detection, the moment when someone realizes there's a new object in the right region with the right motion, that could happen within months of Rubin's first light. And if it doesn't show up? If 2 years pass, then 3, and the predicted regions yield nothing? The hypothesis doesn't instantly collapse, but it enters a different phase. The parameter space contracts. The alternative explanations become more attractive. At some point, you stop saying, "We haven't found it yet," and start saying, "It's probably not there." That outcome would be significant too. Not as exciting as discovering a new planet, but scientifically valuable nonetheless. We'd know the clustering of trans-Neptunian objects needs a different explanation. Maybe it's a selection effect we haven't fully accounted for. Maybe it's a transient configuration that won't persist. Maybe there's something else entirely driving those orbits, something we haven't considered. Science advances through ruling things out as much as confirming them. But the smart money is on detection. Brown and Badijan aren't betting their reputations on a whim. They've spent 8 years refining this hypothesis, testing it against new data, addressing criticisms, making predictions that keep being confirmed. The 2024 results on low-inclination objects were particularly compelling. Different population, same result. That pattern repeating across independent datasets is hard to dismiss. The formation question remains fascinating regardless of when detection happens. If Planet 9 is an ejected ice giant, it validates predictions from the NICE model that have been purely theoretical until now. We'd have direct evidence that planetary systems can eject giant planets without losing them entirely. That has implications for every exoplanetary system we observe. How many systems have hidden planets in distant orbits? How common is this configuration? If Planet 9 is a captured exoplanet, the implications are even stranger. It would mean our Sun stole a world from another star during the solar system's youth. That's not impossible. Stellar nurseries are chaotic places where close encounters happen. But confirming it would be extraordinary. The first exoplanet discovered in our own solar system, a cosmic immigrant that's been here for 4.5 billion years. The public interest in Planet 9 reflects something deeper than just curiosity about astronomy. There's something compelling about the idea that we still don't fully know our own neighborhood. Despite centuries of observation, despite sending probes to the outer planets, despite thinking we'd mapped everything significant, there might still be a world we missed. A giant world, not some tiny asteroid, but a super-Earth mass planet that's been there all along. It's humbling in the right way. It reminds us that the universe doesn't reveal its secrets easily. Even in our own backyard, even with modern technology, there are still mysteries waiting to be solved. Planet 9, if real, represents the last great planetary discovery possible in the solar system. After this, we'll have found everything larger than Pluto. The inventory will be complete. The search itself demonstrates how modern astronomy works. No lone genius staring through a telescope. Teams of researchers analyzing data from multiple instruments, running simulations on supercomputers, developing statistical methods to extract signals from noise, publishing results for peer review, responding to criticism, refining predictions. It's collaborative, iterative, and methodical. Not as romantic as the old stories of discovery, but more reliable. Brown's comment about Rubin being the perfect telescope for finding Planet 9 wasn't hyperbole. The match between the hypothesis's requirements and the observatory's capabilities is almost perfect. Wide field for covering large search areas. deep sensitivity for detecting faint objects, repeated observations for tracking motion, automated data processing for handling billions of measurements. Everything needed to find a slow-moving distant planet, built into one facility. The timing feels right too. The hypothesis emerged in 2016. The predictions have been tested and refined over nearly a decade. The search space has been narrowed through systematic surveys. And now, just as we're ready for a definitive answer, the ideal instrument comes online. It's not coincidence. It's how science progresses. You develop a hypothesis, you test it as best you can with existing tools, and eventually technology catches up to enable the critical test. Rubin's broader impact on astronomy will extend far beyond Planet 9. The 10-year survey will revolutionize our understanding of the outer solar system, discovering tens of thousands of new trans-Neptunian objects, tracking comets, detecting asteroids, mapping the structure of the Kuiper Belt. Planet 9 is just one target in a much larger program. But it's the target everyone will be watching for. Imagine the moment of discovery. Someone running detection algorithms on Rubin data, seeing an object appear in the right region with the right motion. The double-checking. The orbital calculation. The realization that this might actually be it. The careful announcement. The flood of follow-up observations from telescopes worldwide. The gradual confirmation as the data accumulates. The moment when doubt shifts to certainty. Or imagine the alternative. Years passing. The survey completing. The predicted regions thoroughly searched. Nothing found. The slow acceptance that Planet 9 probably isn't there, at least not where expected. The return to other explanations for the orbital clustering. The questions about what we missed or misunderstood. Both scenarios advance our knowledge. One gives us a new planet to study. The other forces us to rethink our interpretation of outer solar system dynamics. Either way, we learn something fundamental about our cosmic home. The next 2 years will answer a question that's persisted since 2016. Is there a ninth planet? The mathematics say yes. The statistics say yes. The predictions keep being confirmed. But science demands direct observation. We need to see it. And we're finally at the point where that's possible. Planet 9 represents the kind of mystery that makes astronomy compelling. Not abstract or impossibly distant. Right here in our solar system. Big enough to matter. Strange enough to surprise us. And just barely beyond our current ability to detect, though that's about to change. The giant lurking in the darkness beyond Neptune might soon step into the light. Or it might remain a mathematical phantom, a compelling hypothesis that couldn't be confirmed. Within 2 years, we'll know. Rubin will scan the sky, the algorithms will run, and the data will tell us what's really out there. The answer is coming. NASA just confirmed something that rewrites everything we thought we knew about life in our solar system. Beneath the icy surface of Ganymede, Jupiter's largest moon, there's an ocean. Not a puddle, not frozen water deposits. An actual ocean larger than all of Earth's surface water combined, hidden under miles of ice in the most hostile environment imaginable. And the implications are staggering. For decades, scientists suspected water might exist on distant moons. They had theories, models, mathematical predictions. But Ganymede was different from the start. When Galileo first spotted it in 1610 through his primitive telescope, he had no idea he was looking at what might be the most important body of water in the known universe. He just saw a bright dot orbiting Jupiter. For centuries later, we're staring at data that suggests this frozen world harbors more liquid water than our entire planet. The confirmation didn't come from a single observation. It emerged from years of meticulous detective work, analyzing magnetic fields, studying how Ganymede interacts with Jupiter's radiation, and piecing together clues that individually meant nothing but together painted an undeniable picture. The Hubble Space Telescope played a crucial role, not by taking pretty pictures, but by watching something most people would find utterly boring. Auroras. Ganymede has auroras, just like Earth. Shimmering lights dancing across its surface, generated by charged particles interacting with its magnetic field. But here's where it gets interesting. These auroras wobble. They rock back and forth in a specific pattern, and that pattern only makes sense if there's a massive conducting layer beneath the ice. Salt water conducts electricity. Ice doesn't. The math was unavoidable. Jupiter's magnetic field is brutal. It's the strongest planetary magnetic field in our solar system, roughly 20,000 times more powerful than Earth's. This field constantly batters Ganymede, which has its own magnetic field, the only moon in our solar system that does. When these two fields interact, they create observable effects on the surface. The auroras shift. They move. And by measuring exactly how they move, scientists could calculate what must be underneath. The ocean isn't sitting right below the surface. Ganymede's structure resembles a layered cake of ice and water. The outermost layer is solid ice, roughly 100 miles thick. Beneath that, liquid ocean. Below the ocean, another layer of ice. Then possibly another ocean. The entire structure extends down hundreds of miles, with the deepest ocean potentially sitting on a rocky seafloor rich in minerals. Temperature plays a bizarre role here. The surface of Ganymede hovers around -170 degrees Celsius. At that temperature, any exposed water would freeze solid in seconds. But deep beneath the ice, pressure and internal heat from tidal forces keep the water liquid. Jupiter's gravity squeezes and stretches Ganymede as it orbits, generating friction, creating warmth. Not enough to make the moon comfortable, but enough to maintain liquid water in the darkness below. The sheer volume is difficult to grasp. Earth's oceans contain roughly 1.335 billion cubic kilometers of water. Ganymede's subsurface ocean likely contains more. Some estimates suggest 2 to 3 times Earth's total water volume, all hidden beneath an alien ice shell, never touched by sunlight, existing in permanent darkness at pressures that would crush most submarines instantly. This discovery fundamentally changes the search for life beyond Earth. For years, the focus remained on Mars. Red dirt, ancient riverbeds, the possibility of microbial life clinging to existence in underground pockets. Mars made sense because it's close, relatively accessible, and clearly had water in its past. But Ganymede has water now. liquid, stable, potentially rich in the chemistry needed for biology. Life on Earth exists in the strangest places. Deep ocean vents spewing superheated water create ecosystems thriving without sunlight. Microbes live miles underground in solid rock. Organisms survive in Antarctic lakes sealed beneath ice for millions of years. If life can adapt to those conditions here, why not in Ganymede's ocean? The ingredients are present: water, energy from tidal heating, and potentially organic compounds delivered by ancient asteroid impacts. The history of this discovery stretches back further than most realize. The Voyager missions in the late 70s provided the first close-up images of Ganymede, revealing a surface unlike anything seen before. Strange grooves, impact craters, and regions of different ages suggested geological activity. Something was reshaping this moon's surface, but without plate tectonics or volcanic activity, the mechanism remained mysterious. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, gathered data that hinted at subsurface oceans on multiple moons. Its magnetometer detected induced magnetic fields around Ganymede, Europa, and Callisto, suggesting conducting layers beneath their surfaces. But the data was incomplete, subject to interpretation, and scientists remained cautious. Extraordinary claims require extraordinary evidence. That evidence accumulated slowly. Computer models improved. Understanding of tidal heating mechanisms deepened. Observations from Earth-based telescopes added pieces to the puzzle. The Hubble aurora measurements provided the breakthrough, offering indirect but compelling proof that couldn't be explained any other way. The scientific community reached consensus. Ganymede has an ocean. But knowing an ocean exists and understanding it are entirely different challenges. The ice shell separating this ocean from space presents an almost impenetrable barrier. 100 miles of solid ice. No drill bit created by human engineering could penetrate that thickness. Any mission to directly sample Ganymede's ocean requires technology that doesn't exist yet, solutions to problems we're only beginning to understand. The European Space Agency's JUICE mission, Jupiter Icy Moons Explorer, launched in April 2023. It won't arrive at Jupiter until 2031, then spend years studying Ganymede, Europa, and Callisto in unprecedented detail. JUICE carries instruments designed to peer through the ice, map the ocean's depth, analyze its composition, and search for signs of geological activity. It won't land, won't drill, won't sample the water directly. But it will transform our understanding. NASA's Europa Clipper, launching in 2024, focuses primarily on Europa, another Jovian moon with a subsurface ocean. But its findings will inform our understanding of Ganymede. These moons share similar characteristics, formed under comparable conditions, subjected to the same gravitational forces. Lessons learned from one apply to the others. The timeline frustrates everyone involved. Space missions take decades from conception to data collection. JUICE won't provide its most detailed Ganymede observations until the mid-2030s. Any follow-up mission to actually land on the surface and attempt to reach the ocean wouldn't launch until the 2040s at the earliest, possibly later. We're looking at a multi-generational project, where scientists designing today's missions may never see their ultimate conclusions. Yet the discovery itself, the confirmation that this ocean exists, represents a pivotal moment. For the first time in human history, we know with confidence that another world in our solar system harbors vast amounts of liquid water. Not ancient water, not frozen deposits that might melt someday. Water existing right now, potentially supporting ecosystems we can't yet imagine. The chemistry of Ganymede's ocean remains largely unknown. Is it fresh water or salt water? What minerals are dissolved in it? Are there organic compounds? Does the rocky seafloor host hydrothermal vents like those on Earth? Each question branches into dozens more, creating a web of mysteries that will occupy scientists for generations. Tidal heating provides the energy source, but how much energy? Earth's ocean vents support complex ecosystems because they pump out heat and chemicals continuously. If Ganymede's ocean floor has similar features, the energy budget might support life. If it's geologically dead, just cold dark water sitting motionless for billions of years, the prospects dim considerably. The multiple ice and water layers add complexity. Some models suggest up to 3 separate oceans stacked vertically, each isolated from the others by ice layers of different densities and crystalline structures. Communication between these layers would be minimal or non-existent. Life could potentially exist in one layer while others remain sterile. Or each layer might host distinct ecosystems adapted to specific conditions. Radiation presents another factor. Jupiter's magnetosphere traps high-energy particles that constantly bombard its moons. Ganymede's magnetic field provides some protection, but the surface still receives significant radiation doses. The ice layer shields the ocean from this radiation, but organic molecules on or near the surface would be quickly destroyed. Any life on Ganymede must exist deep, protected by miles of ice from the hostile radiation environment above. The philosophical implications ripple outward. If life exists in Ganymede's ocean, it would prove that biology isn't unique to Earth. The argument shifts from whether life exists elsewhere to how common it might be. If 2 bodies in one solar system both harbor life, the universe likely teems with it. Every star becomes a possibility, every planet and moon a potential incubator. But we're getting ahead of ourselves. Right now, we have confirmed water and plausible conditions. That's all. The leap from conditions to actual biology remains enormous, filled with uncertainties and assumptions. Life might be common, or Earth might be a cosmic fluke that won't repeat for billions of light years in any direction. What makes Ganymede particularly intriguing is its stability. Mars lost most of its water billions of years ago. Venus turned into a hellscape. Earth's oceans face eventual evaporation as the sun ages. But Ganymede's ocean, locked beneath protective ice and powered by tidal forces that will continue for billions of years, might be more stable than anything on Earth. If life took hold there, it could persist longer than life on our own planet. The size of Ganymede itself matters. At 5,268 kilometers in diameter, it's larger than Mercury, the smallest planet in our solar system. If Ganymede orbited the Sun instead of Jupiter, we'd classify it as a planet. Its substantial gravity holds onto a thin atmosphere, primarily oxygen produced when radiation splits water molecules on the icy surface. The oxygen immediately freezes or gets stripped away by Jupiter's magnetosphere, but its presence confirms water is being processed. Human exploration of Ganymede belongs to science fiction for now. The radiation alone makes crewed missions nearly impossible with current technology. Any spacecraft approaching Jupiter enters a radiation environment that would kill unprotected astronauts within hours. Shielding heavy enough to protect humans would make the spacecraft too massive to launch economically. Robotic missions remain our only viable option for the foreseeable future. That limitation doesn't diminish the significance. Robots can go where humans cannot, endure conditions we'd never survive, and operate for years without food, water, or breathable air. The Voyager probes, launched in 1977, still send data from interstellar space. Properly designed, a mission to Ganymede's ocean could operate for decades, slowly unraveling its mysteries. The technical challenges are staggering but not insurmountable. We need better power sources for long-duration missions far from the sun where solar panels become useless. We need autonomous systems capable of making decisions without waiting for instructions from Earth, since radio signals take nearly an hour to travel between Jupiter and home. We need materials that can withstand extreme cold, high radiation, and the crushing pressures of deep ice. Engineers are already working on concepts. Nuclear-powered cryobots that could melt through ice. Autonomous submarines designed for alien oceans. Instruments sensitive enough to detect organic molecules in tiny water samples. Each component pushes the boundaries of current technology, but none require physics we don't understand. It's engineering, not magic. The cost will be enormous. A mission to land on Ganymede, drill through the ice, and explore the ocean would likely exceed $20 billion, possibly much more. That's a significant fraction of NASA's entire annual budget. International collaboration could spread the cost, but coordinating such a complex mission across multiple space agencies introduces its own challenges. Yet the alternative is remaining ignorant about what might be the most important discovery in human history. If life exists in Ganymede's ocean, finding it would answer humanity's oldest question. We are not alone. And if the ocean is sterile despite having the right conditions, that tells us something equally important about how rare and precious life might be. The next decade will lay the groundwork. JUICE and Europa Clipper will provide the detailed reconnaissance needed to plan future missions. They'll map the ice thickness, identify regions where it's thinnest, search for cracks or areas of geological activity where access might be easier. They'll measure the ocean's salinity, depth, and temperature as precisely as possible from orbit. Based on that data, space agencies will design the next generation of missions. Maybe a lander that can survive on the surface long enough to conduct detailed studies. Perhaps a penetrator that can punch through several miles of ice and deploy sensors. Possibly even a submarine, delivered through a borehole, that could explore the alien sea. Human curiosity demands answers. We've spent centuries wondering whether we're alone in the universe. Now we know where to look. Beneath the ice of a distant moon, in an ocean larger than all of Earth's seas combined, the answer might be waiting. The engineering challenges alone could fill textbooks. Ganymede's surface temperature hovers around -160 degrees Celsius. Electronics freeze. lubricants solidify, batteries lose efficiency. Every component must be designed to function in conditions that would instantly shut down equipment built for Earth. Then there's the ice itself. We're not talking about a frozen pond. The ice shell could be 50 miles thick in places. That's nearly 10 times the height of Mount Everest, except vertical and solid. Drilling through that much ice isn't a matter of bringing a bigger drill. The pressure increases with depth. The ice at the bottom behaves differently than the ice at the top, transitioning from brittle crystal to something more plastic, almost flowing under its own weight. A cryobot melting its way down would need to generate enormous heat continuously, requiring either a radioisotope thermoelectric generator or a compact nuclear reactor. The power source must be small enough to fit in a deployable probe yet robust enough to operate for months or years. It needs to survive radiation from Jupiter. It must avoid contaminating the very environment we're trying to study with Earth microbes that might hitchhike on the spacecraft. Planetary protection protocols will be stricter for Ganymede than for any previous mission. If there's even a possibility of indigenous life, we cannot risk introducing terrestrial organisms that might outcompete or contaminate native biology. Every surface must be sterilized. Every seal must be perfect. The probe becomes a self-contained bubble of Earth technology, isolated from the alien world it's trying to explore. Now add communication problems. A probe beneath miles of ice cannot send radio signals back to an orbiter. Ice blocks electromagnetic radiation effectively. This means either the probe must carry an extremely long cable, unreeling it as it descends, or it must operate completely autonomously, storing data until it can surface or relay information through the borehole. Autonomy introduces new complications. The probe needs artificial intelligence sophisticated enough to navigate unknown terrain, identify interesting features, avoid hazards, and make scientific decisions without human input. If it encounters something unexpected, it cannot phone home for instructions. Round-trip light time to Jupiter means waiting nearly 2 hours for a response to any question. In a dynamic environment, that delay could be fatal to the mission. Consider the submarine concept. Once through the ice, the vehicle must operate in total darkness under pressures that could reach several hundred atmospheres if the ocean is deep enough. It needs propulsion systems that work in extremely cold water. It requires sensors that can detect and analyze whatever might be floating in that alien sea, from simple organic molecules to potential life forms. What happens if the submarine encounters something alive? The protocol must be designed in advance. Does it collect samples? Does it observe without touching? How do you balance scientific curiosity with the ethical implications of disturbing an alien ecosystem that has existed in isolation for billions of years? These aren't abstract philosophical questions. Mission designers must answer them before launch because there's no opportunity to revise the plan once the spacecraft leaves Earth. Every contingency must be anticipated. Every failure mode must have a backup. Space exploration runs on redundancy and careful planning, not improvisation. The timeline stretches across decades. JUICE launched in 2023 and won't arrive at Jupiter until 2031. Europa Clipper launches in 2024 with arrival in 2030. Both spacecraft will spend years conducting flybys, gathering data, refining our understanding. Based on their findings, a lander mission might launch in the late 2030s, arriving in the mid-2040s. A drilling mission could follow in the 2050s. A submarine exploring the subsurface ocean might not splash down until the 2060s or later. This assumes steady funding, no major technical setbacks, and sustained political will across multiple administrations and international partnerships. Space missions operate on timescales that outlast careers, sometimes outlast entire space agency strategic priorities. The people who design these missions often retire before launch. The scientists who propose investigations might not live to see the results. Yet the work continues because the questions matter. Does life exist elsewhere? Is Earth unique, or is biology a common outcome when the right conditions persist long enough? Ganymede offers a test case. It has liquid water, energy sources, and complex chemistry in a stable environment that has existed for billions of years. If life can arise and persist there, it suggests the universe might be teeming with biology in places we never thought to look. The alternative is equally profound. If Ganymede's ocean is sterile despite having everything life needs, that implies something about Earth's biosphere is special, rare, perhaps unique. It means the origin of life requires more than just the right ingredients. It suggests we might be alone after all, or at least that living worlds are far more scarce than optimistic estimates predict. Scientists debate these possibilities constantly. Some argue life is inevitable given the right conditions, that chemistry naturally progresses toward biology, that the universe should be full of microbes at minimum. Others counter that Earth's biosphere might depend on a precise sequence of unlikely events, that life requires not just water and energy but specific catalysts, particular mineral surfaces, or rare chemical pathways that don't exist everywhere. Ganymede will provide evidence, not proof, because proving life doesn't exist anywhere is impossible. You can only prove it does exist by finding it. But if we search thoroughly and find nothing, that shifts the probabilities. It means life is either rarer than we hoped or hidden in ways we don't yet understand. The search itself will advance technology in unexpected ways. Developing autonomous systems for Ganymede will improve robotics here on Earth. Materials that can withstand Jupiter's radiation environment will find applications in nuclear facilities and medical equipment. Power systems designed for deep space will influence energy technology for remote terrestrial locations. Space exploration has always produced spin-off benefits far beyond its primary objectives. But those practical applications aren't why we go. We go because not knowing is intolerable. Humans don't look at locked doors and walk away satisfied. We pick the lock, we break it down, we find another entrance. Ganymede is a locked room the size of a planet, and we've just started examining the hinges. The ocean might be vast and empty, devoid of anything more interesting than water and dissolved salts. That would be disappointing but still valuable. We'd learn about oceanography in low-gravity environments. We'd understand how heat flows through icy moons. We'd gather data about chemistry in sealed systems isolated for geological timescales. Or we might find something that changes everything. Not necessarily intelligent life. Even single-celled organisms would be revolutionary. Bacteria, if we can call them that, adapted to crushing darkness and extreme cold. Microbes that derive energy from chemical gradients rather than sunlight. Simple life following different biochemical rules, using different molecules, perhaps not even based on DNA. That last possibility excites biologists especially. All life on Earth uses the same genetic code, the same basic molecular machinery. We're all related, descended from a common ancestor that lived billions of years ago. But if life arose independently on Ganymede, it might have found different solutions to the same problems. Different information storage molecules. Different energy currencies. Different ways of building cells and regulating metabolism. Comparing Earth life to Ganymede life, if it exists, would reveal which aspects of biology are universal and which are accidents of history. It would show us what life must do to exist versus what Earth life happens to do because that's how it evolved here. That knowledge would transform biology from a historical science describing what happened on one planet to a predictive science explaining what must happen anywhere. The implications extend beyond pure research. Understanding life's minimal requirements would guide searches for habitable planets around other stars. It would inform discussions about terraforming, about creating conditions for life in places currently sterile. It might even reveal new approaches to biotechnology, new ways of engineering organisms or synthesizing useful compounds. But these practical considerations fade next to the fundamental question. In 4.5 billion years of Earth's history, in hundreds of millions of species that have lived and died, in all the complexity of the biosphere from bacteria to blue whales, has life happened only once? Or is it happening right now, independently, in a dark ocean beneath the ice of a distant moon? We're close to finding out. Not tomorrow. Not next year. But within the lifetime of people alive today, we will send machines to Ganymede capable of answering that question. They'll drill through the ice, sample the water, analyze what they find with instruments sensitive enough to detect organic molecules at concentrations of parts per billion. If those instruments find nothing, we'll build better ones. We'll look in different locations. We'll develop new techniques. The absence of evidence doesn't mean evidence of absence, especially when searching an ocean millions of cubic kilometers in volume. But if we find something, anything that moves on its own, that consumes energy, that reproduces, that fits any reasonable definition of life, then we'll know. Human beings will have discovered that we are not alone in the universe. That life exists beyond Earth. That the cosmos is not a sterile void punctuated by one lonely living world, but a place where biology emerges wherever conditions allow. And if a frozen moon of Jupiter hosts life, what about the hundreds of billions of other planets and moons in our galaxy alone? The discovery wouldn't happen all at once. There'd be no single dramatic moment when a scientist points at a screen and shouts that we found aliens. Instead, it would unfold through careful analysis, repeated tests, heated debates in conference rooms and academic journals. Someone would notice unusual chemical signatures in return samples. Organic molecules with strange isotope ratios. Compounds that seem too complex to form through simple chemistry. The first papers would be cautious, hedging their conclusions, suggesting that further investigation is warranted. Then other teams would examine the same data and reach similar conclusions. The evidence would accumulate slowly. Lipid-like molecules that could form membranes. Polymers that might store information. Traces of metabolic processes that can't be explained by known geological chemistry. At some point, the weight of evidence would become overwhelming. The scientific consensus would shift from skepticism to acceptance. But convincing the broader world would take longer. News media would sensationalize the findings, alternating between wild speculation and dismissive skepticism. Social media would erupt with conspiracy theories. Religious leaders would grapple with theological implications. Philosophers would debate what it means for humanity's place in the cosmos. Politicians would argue about funding priorities and international cooperation. Meanwhile, scientists would already be planning return missions. Not just sample return this time, but direct observation. Submersibles that can swim through Ganymede's ocean for months or years, equipped with cameras and sensors and AI systems sophisticated enough to recognize life when they see it. Because finding evidence of life and actually observing living organisms are two very different achievements. Consider what those organisms might look like. On Earth, life in similar environments, deep ocean hydrothermal vents shrouded in permanent darkness, has evolved into bizarre forms. Tube worms 3 meters long with no mouth, no digestive system, surviving on bacteria that live in their tissues. Eyeless shrimp clustering around volcanic vents, their backs covered in light-sensitive organs that detect the faint infrared glow of superheated water. Fish with enormous mouths and bioluminescent lures, adapted to a world where food is scarce and every meal counts. Ganymede's life would face similar pressures but with crucial differences. Earth's deep ocean is connected to the surface. Organic matter drifts down from the sunlit zones above. Dead plankton, fish carcasses, even whale falls that sustain entire ecosystems for decades. Ganymede's ocean has no such connection. No photosynthesis occurring anywhere in the system. No rain of organic carbon from above. Everything must derive from chemistry. From the reactions occurring where water meets rock, where minerals dissolve and precipitate, where temperature and pressure create gradients that life can exploit. This means Ganymede's biosphere, if it exists, would be fundamentally limited in a way Earth's is not. The total amount of chemical energy available sets a hard ceiling on how much life can exist. On Earth, photosynthesis captures roughly 100 terawatts of solar energy. That's the foundation supporting everything else, from bacteria to humans. Ganymede's chemical energy budget would be orders of magnitude smaller. Maybe a few gigawatts at most, possibly much less. This has profound implications for what kind of life could exist there. Forget anything large or complex. No fish swimming through the darkness. No predators hunting prey. The energy simply isn't there to support such lifestyles. Instead, we'd expect to find microbial communities clustered around hydrothermal vents and chemical gradients. Perhaps biofilms coating rock surfaces, slowly metabolizing minerals. Maybe free-floating cells drifting through the ocean, living at such a slow pace that their metabolism would be barely detectable. These organisms would likely reproduce slowly, grow slowly, evolve slowly. Where Earth bacteria can double in number every 20 minutes under ideal conditions, Ganymede microbes might take days or weeks. Their generation times could be measured in years. Evolution on Ganymede might proceed at a glacial pace compared to Earth, simply because there's less energy available to power the biochemical processes that drive mutation and selection. Yet that slowness wouldn't make them any less alive. They'd still be consuming energy, maintaining themselves against entropy, reproducing, evolving. They'd still represent an independent origin of life, a second example of biology emerging in the universe. And studying them would be incredibly difficult precisely because of that slow pace. Detecting metabolism when it happens over weeks instead of hours requires patience and sensitive instruments. Distinguishing living processes from chemical reactions becomes harder when both occur at similar speeds. Proving that something reproduces when reproduction takes months to complete means waiting months between observations. Traditional microbiological techniques developed for Earth organisms, techniques that rely on culturing bacteria in labs and watching them grow, might not work at all. We'd need entirely new approaches. Genetic sequencing, if Ganymede life uses anything resembling DNA or RNA. Chemical analysis of cell components. Microscopic observation of cellular structures. Isotope tracing to track the flow of elements through metabolic pathways. Each technique would have to be adapted for organisms that might not resemble Earth life in any obvious way. And there's a darker possibility worth considering. What if we contaminate Ganymede's ocean before we even realize it harbors life? Every spacecraft we send carries Earth microbes, despite our best sterilization efforts. Some bacteria can survive the vacuum of space, survive intense radiation, survive years of dormancy. If even a few cells reach Ganymede's ocean, they might find conditions suitable for growth. Earth microbes, adapted to environments with abundant energy, might outcompete native Ganymede organisms in the same way invasive species devastate island ecosystems on Earth. We could destroy an entire alien biosphere before we even confirm it exists. This is why planetary protection protocols are so important, why we heat sterilize spacecraft components, why we plan trajectories that avoid impacting potentially habitable worlds. But protocols aren't perfect. Accidents happen. Missions fail. A spacecraft could crash on Ganymede's surface, its fragments eventually working their way through cracks in the ice to the ocean below. Or perhaps contamination has already occurred through some path we haven't anticipated. Natural processes, for instance. Meteorite impacts eject material from planetary surfaces into space. Rocks from Mars have landed on Earth. Rocks from Earth might have reached Ganymede over the solar system's history. If Earth microbes arrived on Ganymede millions of years ago, encased in rock from an impact event, could they have survived? Could they have adapted to the conditions there? This raises an unsettling question. If we find life on Ganymede, how do we prove it originated there independently rather than being related to Earth life that contaminated the Moon long ago? The answer lies in biochemistry. If Ganymede organisms use the same genetic code as Earth life, the same amino acids, the same basic molecular machinery, that would suggest a common origin. Either contamination or panspermia, the idea that life spreads between worlds on meteorites. But if Ganymede life uses different molecules, different information storage systems, different metabolic pathways with no clear connection to Earth biochemistry, that would prove independent origin. Testing this requires bringing samples back to Earth, analyzing them in laboratories with equipment too sophisticated to send to Ganymede. Which creates another problem. How do we safely return samples that might contain alien microbes? What if those microbes, despite evolving in a completely different environment, turn out to be dangerous to Earth life? The risk is probably minimal. Organisms adapted to Ganymede's high-pressure, low-energy environment likely couldn't survive in Earth's oxygen-rich atmosphere at normal pressure. They'd be as out of place here as we would be there. But probably isn't the same as certainly. So any sample return mission would require extraordinary precautions. Sealed containment from the moment samples are collected. Analysis in high-security biosafety facilities. Protocols for sterilization if anything goes wrong. We've done this before, actually. Apollo astronauts returning from the moon were quarantined in case they brought back lunar pathogens. We now know the moon is sterile, but the precaution was reasonable given what we knew then. Samples from Ganymede would require similar or greater care, because unlike the moon, Ganymede actually might harbor life. These practical challenges, the engineering problems and safety protocols and mission designs, can make the search for life seem like a purely technical exercise. Build the right instruments, follow the right procedures, analyze the data correctly. But beneath the technical details lies something more profound. We're attempting to answer a question humans have asked since we first looked up at the night sky. Are we alone? For most of history, that question was purely philosophical. We could speculate, imagine, tell stories about other worlds and other beings. But we couldn't actually investigate. We couldn't go looking. Now we can. Not easily. Not quickly. But we have the technology and the knowledge to send machines to distant worlds in search for life. Ganymede represents our best near-term opportunity. Not the only one. Mars might harbor life in subsurface aquifers. Enceladus, another moon of Saturn, has a similar subsurface ocean that might be even more accessible than Ganymede's. Titan has liquid methane seas and complex organic chemistry. Each world offers a different chance to find biology beyond Earth. But Ganymede stands out because of what we already know about it. The ocean is definitely there. It's in contact with rock. It's existed for billions of years. The conditions, while extreme by Earth standards, fall within the range that could potentially support life. We're not guessing, we're hoping. We're investigating a real possibility based on solid evidence. That investigation requires missions that don't exist yet. We have orbiters studying Jupiter's moons from a distance. We have plans for future missions with more sophisticated instruments. But actually landing on Ganymede, drilling through kilometers of ice, reaching the ocean below. That's beyond our current capabilities. Not impossible. Just difficult and expensive and years away from being technically ready. Which means the search for life on Ganymede exists in a strange state. We know enough to make it compelling. Not enough to actually do it. We're caught between possibility and practicality, between what we want to know and what we can currently achieve. Consider what a Ganymede lander would need to accomplish. First, survive the journey. Jupiter's radiation environment is brutal. Electronics that work fine on Earth or even Mars would fail within hours near Jupiter without heavy shielding. The lander needs protection, but protection adds mass, and mass makes landing harder. Then there's the landing itself. Ganymede's surface is ancient ice, hard as rock, covered with craters and ridges and fracture systems. Finding a safe landing site requires detailed mapping. Avoiding hazards requires precision navigation. All while operating with a communication delay that makes real-time control from Earth impossible. Signals take nearly an hour to travel between Jupiter and Earth at light speed. Commands sent now won't arrive for 43 minutes. Responses take another 43 minutes to return. Any crisis must be handled autonomously by the spacecraft itself. After landing comes the real challenge. Drilling. Not through a few meters of ice, but potentially kilometers. Earth has drilled through ice sheets in Antarctica and Greenland, reaching depths of several kilometers. But those drills are powered by massive equipment, operated by teams of engineers, supported by supply chains bringing fuel and replacement parts. A Ganymede drill would have none of that. It would need to be compact enough to fit on a spacecraft. Light enough to launch from Earth. Powerful enough to penetrate kilometers of ice harder than concrete. Reliable enough to work without maintenance in an environment where the average temperature sits at -160 degrees Celsius. Some designs propose using heat to melt through the ice rather than mechanical drilling. A heated probe slowly descends, melting ice above it which refreezes after it passes, sealing the hole. This approach is elegant and potentially more reliable than mechanical systems. But it's also slow. Estimates suggest it could take years to reach significant depths. Years during which the probe must continue functioning, powered by a nuclear battery that slowly loses strength as its radioactive fuel decays. Other approaches use a combination of heating and mechanical drilling, or cryobots that navigate through existing cracks rather than drilling new holes, or autonomous submarines deployed through access points where ice is thinner, perhaps near the dark terrain where the ocean might be closer to the surface. Each approach has advantages. Each faces enormous engineering challenges. None have been tested in conditions resembling Ganymede's actual environment. We're not talking about adapting existing technology. We're talking about inventing new systems for problems we've never encountered. And we need those systems to work the first time, because there won't be a second chance to retrieve a probe that gets stuck halfway through an ice sheet 300 million kilometers from Earth. Assuming we solve the drilling problem, assuming we reach the ocean, what happens next? The probe needs to function underwater in conditions nothing from Earth was designed for. pressure at the ocean floor could exceed 2,000 times Earth's surface pressure. Salt water with unknown chemistry might corrode materials in unexpected ways. The complete absence of light means any instruments must bring their own illumination. Swimming or moving along the bottom requires propulsion systems that work in dense, cold liquid under crushing pressure. Sampling the water, analyzing it for chemical signatures or biological material, transmitting results back to the surface through kilometers of ice and then across space to Earth. Every step presents technical obstacles. But suppose we overcome them. Suppose a probe successfully lands, drills through the ice, reaches the ocean, begins exploring. What would it actually look for? Life, if it exists in Ganymede's ocean, might not be obvious. It wouldn't be fish swimming past the camera or alien whales breaching near the probe. It would most likely be microbial, single-celled organisms, possibly forming communities like the microbial mats found near Earth's hydrothermal vents, but nothing large or complex enough to see with a camera. Detection would rely on chemistry, looking for organic molecules that shouldn't exist without biological processes. Measuring ratios of chemical isotopes that indicate metabolic activity. Searching for patterns in molecular structure that suggest evolutionary optimization rather than random chemical reactions. On Earth, we can distinguish biological from non-biological processes with high confidence because we understand Earth biochemistry thoroughly. We know what molecules life uses, how they're structured, what isotope ratios result from different metabolic pathways. Ganymede life, if it exists, might work completely differently. It might use molecules we'd never associate with biology. It might produce isotope ratios that look random to us but actually represent alien metabolism. We might find clear evidence of life and not recognize it because we're looking for Earth patterns in an alien system. Or we might find ambiguous results. Organic molecules that could be biological or could be from non-biological chemistry. Isotope ratios that suggest metabolism or could result from geological processes. Energy gradients that look like they're being exploited by life or might just be natural chemical reactions finding equilibrium. The Viking landers on Mars in the 1970s faced exactly this problem. They conducted experiments designed to detect Martian microbes. Some results looked positive. Others were inconclusive. Decades later, scientists still debate whether Viking detected life or just unusual chemistry. A similar situation on Ganymede would be frustrating. We'd have invested billions of dollars and decades of work to reach a moon of Jupiter, drill through its ice, sample its ocean, and come back with results that don't definitively answer the question we went there to investigate. But even ambiguous results would be valuable. They'd tell us something about Ganymede's ocean chemistry. They'd reveal whether organic molecules exist there and in what concentrations. They'd help us understand the energy available for potential life and whether chemical conditions could actually support biology. Negative results would also matter. If we thoroughly sampled Ganymede's ocean and found no evidence of life, no organic molecules, no chemical signature suggesting biology, that would itself be significant. It would suggest that even with liquid water, the right chemistry, and billions of years, life doesn't automatically emerge. It would imply that life requires conditions beyond just liquid water and chemical building blocks. That the jump from chemistry to biology requires something special we don't yet understand. Which brings us back to the fundamental question driving this entire investigation. How does life begin? We know it happened at least once, on Earth, roughly 4 billion years ago. We don't know if it was inevitable or fantastically unlikely. We don't know if it requires specific conditions that are rare in the universe or if it emerges readily wherever basic requirements are met. Finding life on Ganymede would suggest it's relatively common. Two independent origins in the same solar system would imply life emerges frequently throughout the universe. Not finding life on Ganymede, especially after thorough searching, would suggest it's rare. That Earth might be unusual or even unique among the countless worlds in our galaxy. Both answers would be profound. Both would reshape how we understand our place in the universe. But one answer requires us to actually go there and look. Not just theorize or speculate based on distant observations. We need direct investigation. Ganymede challenges us in ways that push against our current technical limits. The radiation environment around Jupiter. The extreme cold. The massive ice shell. The crushing pressures in the deep ocean. Each obstacle has solutions, but implementing those solutions in a single integrated mission that actually works requires innovation and resources and time. Multiple space agencies have proposed concepts. Europa Clipper, launching soon, will study Jupiter's moons including Ganymede, gathering data that will help plan future missions. JUICE, the Jupiter Icy Moons Explorer, will orbit Ganymede directly, mapping its surface and ice shell in unprecedented detail. These are reconnaissance missions. They'll tell us where to look. They won't answer whether life is actually there. That requires landing. That requires drilling. That requires direct sampling. The earliest realistic timelines put such a mission in the 2040 period. Possibly later depending on funding and technical development. Which means if you're watching this now, the answer to whether life exists on Ganymede might not come in your lifetime. Or it might come tomorrow if we get extraordinarily lucky with existing data. Science operates on timescales that don't align with human patience. We want answers now. The universe provides them when it's ready, following its own schedule that doesn't care about our curiosity or our lifespans. Yet we keep looking. We keep planning missions and developing technology and training scientists who will analyze data from instruments that don't exist yet, studying a world most people will never even see clearly except in images taken by robots we send across the solar system. The search continues because some questions demand answers regardless of how difficult finding them might be. Maybe the answer isn't hiding in some distant ocean after all. Maybe we're approaching this entire question from the wrong angle, fixating on complexity when the real story is far stranger. Because there's another possibility we haven't fully confronted. Life might not be limited to places like Earth or Ganymede. It might exist in forms and locations so fundamentally different from what we know that we wouldn't recognize it even if we were looking directly at it. Consider Titan, Saturn's largest moon. It has lakes and rivers and rain, a complete hydrological cycle just like Earth. Except the liquid isn't water. It's methane and ethane, hydrocarbons flowing across a world where the surface temperature sits at -179 degrees Celsius. Chemistry at those temperatures operates under completely different rules. Reactions that happen instantly on Earth take geological timescales on Titan. Molecules that are gases here are liquids there. And yet Titan's atmosphere shows chemical imbalances that don't make sense without some active process continuously producing certain compounds. Something is consuming hydrogen at the surface. Something is depleting acetylene. The measurements are real. The interpretations are contested. Could be geological. Could be atmospheric chemistry we don't understand. Could be life, but life's so alien it doesn't resemble anything in our experience. Imagine organisms that use liquid methane instead of water as a solvent. That builds cell membranes from compounds stable at cryogenic temperatures. That metabolize in slow motion across timescales measured in Earth years rather than seconds. Would we even recognize their biochemistry as life? Our definitions are built around Earth biology. Carbon chains in water. DNA and RNA. Proteins folded in specific configurations. Energy from breaking chemical bonds in particular ways. Strip away those specifics and what's left? What's the irreducible core that separates living systems from complex chemistry? Self-replication, maybe. The ability to make copies. But crystals do that and we don't call them alive. Metabolism, extracting energy from the environment. But fire does that. Response to stimuli. Lots of chemical systems respond to their surroundings without being alive. The technical definition usually involves all of these together plus evolution, the capacity to change over generations through variation and selection. Yet even that gets murky at the edges. Viruses evolve but exist in a gray zone between chemistry and biology. Prion replicate and cause harm but contain no genetic material at all. We might be searching for Earth life in other locations when the universe has invented entirely different solutions to the same fundamental problem. How to persist. How to make order in a universe that tends toward disorder. How to harness energy flows to maintain complexity. Saturn's moon Enceladus shoots geysers of water into space from an underground ocean. The Cassini spacecraft flew through those plumes and detected organic molecules, salts, silica particles. Everything you'd expect from hydrothermal activity on an ocean floor. Almost identical to environments on Earth where life thrives around deep sea vents. But Enceladus is tiny. Its ocean might be only 10 kilometers deep. The entire moon is barely 500 kilometers across. Could something that small sustain life for billions of years? Does it matter? If life exists there, it exists. Size is a human concern. Biology doesn't care about our intuitions regarding what's possible. Venus presents a different kind of puzzle. The surface is hellish, hot enough to melt lead, pressure crushing enough to destroy spacecraft within hours. But 50 kilometers up in the atmosphere, conditions are surprisingly mild. temperature and pressure similar to Earth's surface. Sulfuric acid clouds, yes, but microbes on Earth survive in acid. Thrive in it, even. And there's this persistent mystery in Venus's atmosphere. Phosphine, a gas that on Earth is only produced by life or human industrial processes. The detection has been challenged, reanalyzed, debated intensely. Maybe it's there, maybe it's not, maybe the instruments were misread. But if it is there, if it's real, then something is producing it. Life floating in the clouds of Venus would be genuinely alien, organisms that never touch solid ground, reproducing in droplets of sulfuric acid, cycling through the atmosphere for their entire existence. These scenarios push against our assumptions. We think of life as something that happens on surfaces, in oceans, in contact with rock. But why? Because that's how it works here. The universe might not care about our provincial expectations. And then there are the truly strange possibilities. Worlds where ammonia replaces water. Planets with silicon-based chemistry instead of carbon. Environments where life operates at temperatures near absolute zero or in the nuclear furnaces of stellar cores. Pure speculation, sure, but speculation constrained by physics and chemistry, not fantasy. The point isn't that any specific scenario is likely. The point is we don't know the boundaries of what's possible. Every time we think we've found life's limits, something on Earth survives in a place we thought was sterile. Microbes in nuclear reactor cooling pools. Organisms in subglacial lakes isolated for millions of years. Life in the driest deserts, the deepest ocean trenches, inside solid rock kilometers below the surface. Earth life adapted to those places, evolved to tolerate extremes. But what if life started in extremes elsewhere? What if the universe is full of biology that would find Earth hostile and bizarre, organisms for whom our comfortable temperatures and abundant water are toxic? Finding any form of life beyond Earth would be revolutionary. Finding life radically different from our own would be even more so. It would prove life isn't a single solution but a category of solutions. That the universe experiments with multiple approaches to the same fundamental challenge. The search has to account for this uncertainty. We can't only look for Earth twins. We need strategies for detecting life we don't recognize, biosignatures we haven't imagined. Which is extraordinarily difficult because you can't search for something when you don't know what you're searching for. Atmospheric chemistry offers one approach. Life, any life, has to exchange matter and energy with its environment. Those exchanges leave traces, chemical imbalances that persist because something is actively maintaining them. Oxygen in Earth's atmosphere is a biosignature because without life constantly producing it, oxygen would react away. It's chemically unstable over geological time. Other worlds might have different biosignatures. Gases that shouldn't coexist found together. Ratios of isotopes that don't match non-biological processes. Seasonal variations in atmospheric composition that suggest biological cycles. We can look for patterns without knowing exactly what's causing them. But that requires getting close enough to analyze atmospheres in detail. For planets around other stars, That means next-generation space telescopes powerful enough to separate a planet's light from its star's glare and break that light into spectra revealing chemical composition. The technology exists. The telescopes are being built. Within a decade we'll have the capability to study potentially habitable exoplanet atmospheres. And then what? We detect oxygen and methane together on a world 30 light-years away. Strong suggestion of life, not proof. Could be geological, some process we don't understand producing those gases without biology. We'll debate it, analyze it, propose follow-up observations. But we won't know for certain. Not the way we'd know if we could land and look directly. The frustrating truth is certainty might be impossible for life beyond our solar system. We could find compelling evidence, strong suggestions, patterns that look biological. Absolute proof would require sending probes to other star systems, missions that would take thousands of years with current technology. Or developing fundamentally new propulsion methods, which might happen eventually but not soon. So we're left with probabilities and indirect evidence and scientific arguments that won't satisfy everyone. Which is fine, actually. Science doesn't require certainty to make progress. It requires better questions and methods for answering them. Within our solar system we can achieve certainty. We can send robots to drill and sample and analyze with instruments sophisticated enough to detect life if it's there. Mars, Europa, Enceladus, Titan, Ganymede. Each world gets us closer to answering whether life is common or rare, whether Earth is typical or exceptional. And maybe the answer is both. Maybe simple life, microbes, basic cells, emerges readily throughout the universe wherever conditions permit. But complex life, multicellular organisms, intelligence, remains vanishingly rare. That would explain why we see no obvious signs of technological civilizations despite billions of habitable planets in our galaxy. Or maybe we're alone. Maybe life requires such a specific sequence of unlikely events that Earth is genuinely unique. For billion years of evolution on the only living world in the observable universe. That possibility terrifies some people. The cosmic loneliness of it. Personally, it seems no more lonely than the alternative. If life is everywhere, we're still separated by distances that make communication nearly impossible. If life is rare, at least we're special. Both scenarios leave us fundamentally isolated in a vast universe, responsible for preserving the only consciousness we know exists. The search continues not because we expect easy answers but because not searching would be worse. Accepting ignorance when knowledge is possible. Living with questions we could answer if we tried. That's not how humans operate. We're curious to the point of obsession, willing to spend decades and billions pursuing answers to questions most people never think about. And perhaps that obsession is itself evidence of something profound. The fact that we care about questions with no immediate practical benefit. That will dedicate careers to understanding whether microbes exist beneath Martian ice. That we build telescopes to analyze the atmospheres of worlds we'll never visit. This curiosity might be the most distinctively human trait we possess, more defining than tool use or language or social organization. Other intelligent species, if they exist, might not share it. They could be perfectly content within their own worlds, never wondering what lies beyond. Evolution doesn't guarantee curiosity. It guarantees survival strategies, and sometimes curiosity helps survival by driving exploration and innovation. But it's not inevitable. We could have evolved to be incurious, satisfied, uninterested in questions beyond immediate needs. We didn't. Something in the particular path human evolution took produced minds that can't stop asking why. Minds that see a star and wonder what it's made of. That find a fossil and reconstruct entire extinct ecosystems. That detect a chemical signature on a distant moon and immediately start planning missions to investigate. This compulsion has costs. Resources spent on space exploration could address immediate terrestrial problems. The billions invested in Mars rovers don't feed hungry people or cure diseases or solve climate change. Critics make this argument constantly, and it's not entirely wrong. Priorities matter. But the assumption that we must choose between cosmic exploration and earthly welfare creates a false dichotomy. Human civilization is wealthy enough to pursue multiple goals simultaneously. The amount spent on space science represents a tiny fraction of global economic activity. NASA's entire annual budget is less than what's spent on pet food in the United States. We're not choosing between feeding people and exploring Mars. We're choosing between various forms of discretionary spending, and some of that spending generates knowledge rather than consumption. Knowledge has value beyond immediate application. Understanding how planets form helps us understand our own planet's history. Studying extreme environments on other worlds informs our understanding of life's limits. Developing technology for space missions produces innovations that find terrestrial applications. GPS, weather forecasting, communications satellites, medical imaging techniques, all emerged from space programs. But even without practical spin-offs, the knowledge itself matters. Knowing whether we're alone in the universe changes how we think about existence, meaning, our place in reality. It's the kind of knowledge that shifts perspective, that makes us see ourselves differently. And that has value even if it doesn't produce marketable products. The search for life also forces us to confront uncomfortable possibilities about our own future. If we find dead worlds that once had life, worlds where biological activity left traces before going extinct, that tells us something about planetary evolution. Life emerges, thrives for a while, then disappears. Not a comforting pattern. Mars might be such a world. Early in its history, warmer, wetter, potentially habitable. Then it lost its magnetic field, its atmosphere stripped away by solar wind, surface water evaporating or freezing, whatever life existed either dying or retreating underground. A world that had its chance and lost it. Earth could follow the same trajectory. Not tomorrow, not in human timescales, but eventually. Our sun is gradually brightening, increasing energy output as it ages. In 1 billion years, maybe less, Earth's oceans will boil away. The planet will transition from habitable to sterile, life's 4 billion year run ending not with catastrophe but with slow inexorable change. Unless life spreads beyond Earth first. Unless consciousness finds ways to persist across multiple worlds, backing itself up against planetary disasters. This is one argument for space exploration that transcends curiosity. Survival of life itself as a phenomenon, as a process, as the universe's method for organizing matter into increasingly complex patterns. We're the only species capable of deliberately spreading life to other worlds. Every other organism is confined to Earth, dependent on this single planet's continued habitability. We have the technology to change that. Not easily, not soon, but possible within foreseeable futures. Establishing self-sustaining colonies on Mars or in orbital habitats or on moons throughout the solar system. Whether we should do this is a separate question. Planetary protection protocols exist specifically to prevent contaminating other worlds with Earth life before we've had a chance to study them in pristine condition. If Mars has indigenous life, even just microbes, introducing Earth organisms could destroy or outcompete them before we discover they exist. But if Mars is dead, if Europa and Enceladus contain only chemistry without biology, if we're genuinely alone in this solar system, then spreading life becomes not contamination but continuation. Taking the process that started on Earth and extending it outward, giving it redundancy, ensuring that life in general isn't dependent on one planet's survival. This assumes life has value, that preserving and spreading it matters. Not everyone accepts that premise. From a purely physical perspective, life is just complex chemistry. The universe doesn't care whether organized matter continues existing or breaks down into simpler forms. Stars will keep burning, galaxies will keep rotating, the cosmos will expand regardless of whether life persists anywhere. Yet we care. Consciousness cares about its own continuation. We value existence over non-existence, complexity over simplicity, preservation over destruction. These preferences aren't logically necessary. They're built into us by evolution because organisms that don't prioritize survival don't leave descendants. But the fact that our values are evolutionary products doesn't make them meaningless. We're parts of the universe that have become aware of themselves. Matter organized in specific ways that allow reflection, contemplation, understanding. The universe experiencing itself through consciousness. Poetic language, but also accurate description of what's happening when human brains process information about reality. If consciousness is rare, if Earth represents the only location in vast cosmic volumes where this self-awareness exists, then its preservation becomes critically important. Not because some external authority values it, but because we value it, and we're the only judges available. If consciousness is common, if billions of worlds host thinking beings, then our individual survival matters less to the cosmic story. But it still matters to us, to the particular instance of awareness that exists here and now. Either way, the search continues. Rovers drill into Martian soil. Probes fly through the plumes of icy moons. Telescopes scan distant atmospheres. Scientists analyze data, refine hypotheses, design better instruments. Each mission adds information, narrows possibilities, brings us incrementally closer to answering questions that might not have answers we like. Maybe we find life everywhere we look. Simple, persistent, unremarkable. The universe teeming with microbes that never evolved past basic cellular organization. That would tell us life is easy but complexity is hard. That the gulf between chemistry and biology is narrow, but the gulf between microbes and intelligence is vast. Maybe we find nothing. Decades of searching, increasingly sophisticated instruments, samples from dozens of worlds, all sterile. Earth alone, life a statistical fluke, consciousness an accident that happened once. That would tell us we're precious beyond measure, the universe's only attempt at self-understanding. Maybe we find something we don't expect. Life based on different chemistry, using different solvents, storing information in molecules we haven't considered. That would expand our understanding of what's possible, show us that biology isn't limited to the one example we know. Any of these outcomes changes everything. Not immediately, not in ways that affect daily existence for most people. But fundamentally, philosophically, in how we conceptualize ourselves and our significance. The wait continues. Missions are years in planning, years in transit, months or years analyzing results. Science operates on timescales that don't align with human patience. We want immediate answers to questions that require decades of careful work. But some questions are worth the wait. Some knowledge is worth pursuing even when acquisition is slow and expensive and uncertain. The search for life beyond Earth is that kind of question. Fundamental enough to justify the investment, profound enough to change everything if answered. So we keep looking. Building better instruments, sending more sophisticated probes, analyzing data with increasing precision. Each generation of scientists adding to the work of previous generations, standing on accumulated knowledge, pushing the boundary of what's known slightly further outward. And maybe, eventually, we'll know. Not through dramatic revelation but through accumulated evidence that finally crosses the threshold from possibility to certainty. A moment when the data becomes undeniable, when all reasonable doubt evaporates, when we can say with confidence that yes, life exists beyond Earth. Or no, we're alone after all. Both answers transform us. Both force reconsideration of assumptions we didn't know we were making. Both open new questions even as they resolve old ones. That's how knowledge works. Each answer generates more questions. Each discovery reveals new mysteries. We're not approaching some final understanding where all questions get resolved. We're expanding the boundary between known and unknown, and the boundary circumference grows faster than its area. The universe is larger and stranger than we imagine. Probably larger and stranger than we can imagine. Our brains evolved to handle problems at human scales, understanding objects we can see and touch, timescales we can experience. Cosmic questions push against those cognitive limits. But we keep pushing anyway. Because that's what consciousness does. It reaches beyond itself, grasps for understanding that might be perpetually just out of reach. And sometimes, occasionally, it succeeds. Sometimes the universe yields its secrets, reveals its patterns, shows us something true. The search for life is that kind of reaching. An attempt to understand our context, our cosmic neighborhood, whether we share this vast space with others. And whether we find life or find ourselves alone, either answer is worth knowing. So that's where we are. Standing at the edge of something that could redefine everything we thought we knew about our place in existence. Ganymede's ocean isn't speculation anymore. It's confirmed. Real liquid water, vast beyond comprehension, sitting beneath ice in the darkness of space. And we're close enough to reach it, smart enough to design missions that could actually get there, curious enough to keep pushing even when the timeline stretches across decades. The answer might come from Ganymede, or Europa, or Enceladus, or from some unexpected corner of the solar system we haven't looked at carefully enough. It might not come at all, at least not in our lifetimes. But the searching itself matters. The fact that we're capable of asking these questions, of building the tools to investigate them, of dedicating resources and careers to understanding whether we're alone. Every mission teaches us something. Every dataset narrows the possibilities. Every failure informs the next attempt. We're not stumbling blindly anymore. We're methodically eliminating uncertainty, building toward conclusions that will stand regardless of what we want them to be. And maybe that's the real story here. Not whether life exists on Ganymede, but that we've become the kind of species that can find out. That we've developed the technology, the knowledge, the sheer stubborn determination to send machines across hundreds of millions of kilometers and ask questions about oceans we'll never see directly. The universe doesn't owe us answers. It doesn't care about our curiosity or our need to understand. But it's revealing itself anyway, piece by careful piece, to minds capable of interpreting the evidence. We're part of the cosmos trying to understand itself. And sometimes, when we look hard enough and think carefully enough, understanding happens. Ganymede waits beneath its ice. Silent. Patient. Holding secrets that might transform us. The search continues because we are parts of the universe trying to understand itself. Piece by careful piece, the universe reveals itself to minds capable of interpreting evidence. The answer is waiting. And soon, through our courage and science, we will know.